LEDs não obtêm a sua cor das capas de plástico. E dá pra ver, porque aqui tem um LED transparente que também brilha na cor vermelha. A cor da luz vem dos próprios eletrônicos. A capa só nos ajuda a diferenciar os LEDs. Em 1962, o engenheiro da General Electric Nick Kuranypro criou o primeiro LED visível. Ele brilhava um vermelho fraco. Alguns anos depois, engenheiros da Monsanto criaram um LED verde. Mas por décadas, só tivemos essas duas cores. Então LEDs só podiam ser usados em coisas como indicadores, calculadoras e relógios. Se pudéssemos fazer azul, misturaríamos vermelho, verde e azul para fazer branco e todas as outras cores. Destravando LEDs para todo tipo de iluminação no mundo, de lâmpadas a telefones, a computadores, a TVs, a outdoors. Mas a cor azul era quase impossível de criar usando LED. Durante os anos 60, toda grande empresa de eletrônicos do mundo, da IBM, a GE, até Bell Labs, competiu para criar o LED azul. Sabiam que valeria bilhões. Apesar do esforço de milhares de pesquisadores, nada funcionou. 10 anos após o LED original de Kuranypro virou 20, depois 30, e a esperança de usar LEDs para luz se esvaiu. Segundo um diretor da Monsanto, esses LEDs nunca substituirão a luz da cozinha. Seriam usados apenas em eletrodomésticos, painéis de carro e aparelhos de som, para ver se o som estava ligado. Isso poderia ser verdade hoje, se não fosse por um engenheiro que desafiou toda a indústria e fez 3 avanços radicais para criar o primeiro LED azul do mundo. Ajude Nakamura era pesquisador numa pequena empresa química japonesa chamada Deixe. Eles haviam expandido recentemente para a produção de semicondutores para uso na fabricação de LEDs vermelhos e verdes. Mas no final dos anos 80, a divisão de semicondutores estava por um fio, competiam contra firmas bem mais sólidas no mercado cheio e estavam perdendo. As tensões começaram a crescer. Funcionários jovens pediram a Nakamura para criar novos produtos, enquanto os mais velhos viam a sua pesquisa como desperdício de dinheiro. E na Deixe, dinheiro era escasso. O laboratório de Nakamura era composto na maior parte por máquinas que ele mesmo recolheu e soldou. Vazamentos de fósforo no seu laboratório causaram tantas explosões que seus colegas pararam de verificar como ele estava. Em 1988, os chefes de Nakamura estavam tão desiludidos com a sua pesquisa que pediram que se demitisse. Então, por desespero, levou uma proposta radical ao fundador e presidente da empresa, Nobuo Ogawa. O LED fugaz da cor azul no qual a Sony, a Toshiba e a Panasonic falharam. E se a Deixe pudesse se tornar a criadora do LED azul? Após sofrer perdas em seus semicondutores por mais de uma década, Ogawa se arriscou. Ele dedicou 500 milhões de ienes, ou 3 milhões de dólares, cerca de 15% do lucro anual da empresa, ao projeto audacioso de Nakamura. Todos sabiam que LEDs tinham o potencial de substituir lâmpadas, pois as lâmpadas, o símbolo universal de uma ideia brilhante, são na verdade péssimas em produzir luz. Elas funcionam passando corrente por um filamento de tungstênio que esquenta até brilhar, mas a maior parte da radiação eletromagnética é emitida como calor infravermelho. Somente uma fração insignificante é luz visível. Em contraste, a sigla LED significa diodo emissor de luz. O nome já é autoexplicativo. LEDs geram luz como principal função, então são bem mais eficientes. E um diodo é apenas um dispositivo com 2 eletrodos, que só permite corrente fluir num sentido. Então veja como um LED funciona. Quando se tem um átomo isolado, cada elétron desse átomo ocupa um nível de energia distinto. Você pode ver esses níveis de energia como assentos individuais de um estádio de hóquei. E todos os átomos do mesmo elemento, quando estão distantes entre si, têm níveis de energia disponíveis idênticos. Mas ao unir vários átomos para formar um sólido, algo curioso acontece. Os elétrons mais externos agora sentem a atração não só do seu próprio núcleo, mas também de todos os outros núcleos. E como resultado, os seus níveis de energia mudam. Então, ao invés de serem idênticos, se transformam numa sequência de níveis de energia próximos mas separados, uma banda de energia. A banda de energia mais alta com elétrons é a banda de valência. E a próxima faixa de energia mais alta se chama banda de condução, pensa nela como o nível da sacada. Em condutores, a banda de valência é parcialmente cheia. Isso quer dizer que com pouca energia térmica, elétrons podem pular para assentos vazios próximos. E se um campo elétrico é aplicado, podem saltar de um assento vazio ao outro e conduzir corrente no material. Em isolantes, a banda de valência está cheia, e a diferença de energia entre a banda de valência e a de condução, o gap de energia, é grande. Quando um campo elétrico é aplicado, nenhum elétron se move. Não há assentos disponíveis para se mover na banda de valência, e o gap de energia é grande demais para qualquer elétron saltar para a banda de condução. O que nos leva aos semicondutores. Os semicondutores são como isolantes, mas com um gap de energia menor. Isso indica que a temperatura ambiente, alguns elétrons têm energia suficiente para entrar na banda de condução e ocupar assentos vazios próximos, conduzindo corrente. Não só isso, os assentos vazios na banda de valência que deixaram para trás também podem se mover. Na verdade, são os elétrons próximos pulando para aqueles assentos vazios. Mas se você olhar de longe, é como se o assento vazio ou buraco tivesse se movendo como uma carga positiva na direção oposta aos elétrons na banda de condução. Sozinhos, semicondutores puros são pouco úteis. Para torná-los mais funcionais, você tem que adicionar átomos impuros na malha. Isso é conhecido como dopagem. Por exemplo, você pode adicionar poucos átomos de fósforo em silício. O fósforo é similar ao silício, então facilmente se encaixa na malha com um elétron de valência extra. Esse elétron existe num nível doador sob a banda de condução. Então, com energia térmica, todos esses elétrons saltam para a banda de condução e conduzem corrente. Como a maioria das cargas que podem se mover nesse tipo de semicondutor são elétrons negativos, esse tipo de semicondutor é chamado de tipo N, N de negativo. Mas devo salientar que o semicondutor ainda é neutro. Acontece que a maioria dos portadores móveis é negativa. Eles são elétrons. Então há também outro tipo de semicondutor onde a maioria dos portadores de carga são positivos, chamado de tipo P. Para criar silício tipo P, adicione um pouco de átomo, como boro. O boro se encaixa na malha, mas traz consigo um elétron de valência a menos que o silício, então cria um nível aceitador vazio logo acima da banda de valência. E com um pouco de calor, elétrons podem saltar para fora da banda de valência, deixando buracos para trás. São esses buracos positivos que na maior parte são responsáveis por conduzir corrente no semicondutor tipo P. Novamente, o material em geral é neutro, só que a maioria dos portadores de carga móvel são buracos positivos. As coisas ficam interessantes ao juntar um pedaço de semicondutor P e N. Sem nem ligar isso a um circuito, elétrons vão difundir de N para P e cair nos buracos no tipo P. Isso torna o tipo P um pouco negativamente carregado e o tipo N um pouco positivamente carregado. Então agora há um campo elétrico dentro de um pedaço inerte de material. Elétrons seguem difundindo até que o campo elétrico se torne tão grande que os impeça de atravessar. E agora estabelecemos a região de esgotamento, uma área sem portadores de carga móveis. Não há elétrons na banda de condução nem buracos na banda de valência. Se você conectar uma bateria ao contrário nesse diodo, ele só amplia a região de esgotamento até o seu campo elétrico se opor perfeitamente ao da bateria e nenhuma corrente flui. Mas se inverter a polaridade da bateria, a zona de esgotamento diminui, o campo elétrico reduz e elétrons fluem de N para P. Quando um elétron cai da banda de condução para um buraco na banda de valência, esse gap de energia pode ser emitido como um fóton. A mudança de energia do elétron é emitida como luz. É assim que um diodo emissor de luz funciona. O tamanho do gap de energia determina a cor da luz emitida. Em silício puro, o gap de energia é só 1,1 volts de elétron. Então o fóton liberado não é visível, é a luz infravermelha. Esses LEDs são usados em controles remotos como o da TV e você pode capturá-los com a câmera. Subindo o espectro, dá para ver porque os primeiros LEDs visíveis eram vermelhos e depois verdes, e porque o azul era tão difícil. Um fóton de luz azul exige mais energia e, portanto, um maior gap de energia. Na década de 80, após centenas de milhões terem sido gastos em busca do material ideal, todas as empresas de eletrônicos falharam. Mas ao menos os pesquisadores identificaram o primeiro requisito crítico, um cristal de alta qualidade. E independentemente do material usado no LED azul, ele exigia uma estrutura cristalina quase perfeita. Quaisquer defeitos na malha cristalina interrompem o fluxo dos elétrons. E então, em vez de emitir sua energia como luz visível, é dissipada como calor. O primeiro passo na proposta de Nakamura ao Gal era sumir para a Flórida. Ele conhecia um velho colega na Flórida cujo laboratório começava a usar uma nova tecnologia de criação de cristais chamada deposição química metalorgânica de vapor, ou MLCVD. Um reator MLCVD, basicamente um forno enorme, era, e ainda é, a melhor forma de produzir cristal limpo em massa. Funciona injetando moléculas de vapor do seu cristal em uma câmara quente, onde reagem com um material base chamado substrato para formar camadas. É crucial que a malha do substrato combine com a malha cristalina sendo construída sobre ela, para criar um cristal estável e liso. Isso é uma arte precisa. As camadas cristalinas frequentemente precisam ser tão finas quanto só alguns átomos. Nakamura se juntou ao laboratório por um ano para dominar MLCVD. Mas seu tempo lá foi péssimo. Ele não pôde usar o MLCVD funcional. Então passou 10 de seus 12 meses montando um novo sistema quase do zero. Pior ainda, colegas de laboratório o evitaram, pois Nakamura não tinha doutorado, nem artigos acadêmicos, já que a Nishia não permitia publicações. Os seus colegas de laboratório, todos doutores, o viam como um mero técnico. Essa experiência o impulsionou. Nakamura escreveu: "Sinto rancor quando fazem pouco de mim. Desenvolvi um espírito mais aguerrido. Não me deixaria ser vencido por tais pessoas." Ele voltou ao Japão em 1989 com duas coisas em mãos. Uma era uma encomenda para um novo reator MLCVD para Nishia, e a outra era um desejo fervoroso de obter o seu doutorado. Naquela época no Japão, dava para tirar doutorado sem ir à universidade, só publicando 5 artigos. Nakamura sempre soube que suas chances de inventar o LED azul eram pequenas, mas desta vez, ele tinha um plano B. Mesmo sem êxito, ele poderia obter seu doutorado. Mas agora a questão era, com o MLCVD dominado, qual material ele deveria pesquisar. Nessa altura, cientistas reduziram as opções para 2 principais candidatos, seleneto de zinco e nitreto de galho. Esses eram semicondutores com gaps de energia, teoricamente, na faixa da luz azul. O seleneto de zinco era a opção mais promissora. Quando cultivado num reator MLCVD, ele teve só 0,3% de incompatibilidade de malha com seu substrato arsenieto de galho. Portanto, o cristal de zinco seleneto tinha cerca de 1000 defeitos por centímetro quadrado, dentro do limite para funcionar em LED. O seu único problema era que, enquanto cientistas haviam descoberto várias formas de criar zinco selênio do tipo N, ninguém sabia como criar o tipo P. Em contraste, o nitrato de galho foi deixado por quase todos por 3 motivos. Primeiro, era bem mais difícil criar um cristal de qualidade. O melhor substrato para nitreto de galho era safira, mas a incompatibilidade de malha era de 16%. E isso resultava em mais falhas, acima de 10 bilhões por centímetro quadrado. O segundo problema era que, como o seleneto de zinco, cientistas só fizeram nitreto de galho do tipo N com silício. O tipo P era elusivo. E terceiro, para ser viável no mercado, um LED azul precisaria de uma potência de pelo menos 1000 microwatts. Isso é 2 ordens de grandeza além do que qualquer protótipo já havia alcançado. Então, entre os 2 candidatos, quase todos focavam no seleneto de zinco. Nakamura observou a área lotada e decidiu que para publicar 5 artigos sozinho, melhor focar em nitreto de galho, onde a competição era bem menos acirrada. O grande destaque desse material foi um desenvolvimento em 1972, quando o engenheiro da RCA, Robert Maroska, criou um pequeno LED azul de nitreto de galho, mas ele era fraco e ineficaz. Então a RCA cortou o orçamento do projeto, o chamando de beco sem saída. 20 anos depois, a visão científica não havia mudado. Quando Nakamura foi à maior conferência de física aplicada do Japão, as palestras sobre seleneto de zinco tinham mais de 500 participantes, palestras de nitreto de galho tinham 5. 2 desses 5 participantes eram os maiores especialistas mundiais em nitreto de galho, o Dr. Isamu Akasaki e seu ex-aluno de doutorado, o Dr. Hiroshi Amano. Em contraste com a base acadêmica de Nakamura, eles eram pesquisadores na Universidade de Nagoya, uma das melhores do Japão. Alguns anos antes, tiveram um avanço no primeiro problema do cristal de alta qualidade. Ao invés de cultivar nitreto de galho diretamente sobre safira, primeiro criaram uma camada base de nitreto de alumínio. Isso tem um espaçamento de malha entre a dos outros 2 materiais, facilitando o crescimento de um cristal limpo de nitreto de galho em cima. O único problema era que o alumínio causava complicações para o reator MOCVD, tornando o processo difícil de ampliar. Mas Nakamura nem estava perto nesse ponto. De volta a Nishia, ele não conseguia fazer o nitreto de galho crescer normalmente em seu novo reator MOCVD. Após 6 meses, ansioso por resultados, decidiu desmontar a máquina e criar uma versão melhor por conta própria. Seus 10 meses montando o reator na Flórida tornaram-se de repente inestimáveis. Ele seguia a mesma rotina todo dia. Chegue ao laboratório às 7 da manhã, passe a manhã soldando, cortando e refazendo a fiação do reator. Passe o resto do dia testando o reator modificado para ver o que ele faz. Às 7 da tarde, vá para casa, jante, se lave e durma. Nakamura seguia essa rotina todo dia, sem pausas ou feriados, com exceção pelo Ano Novo, o feriado mais importante no Japão. Após 1 ano e meio de trabalho contínuo, ele foi para o laboratório numa tarde de inverno em 1990. Como sempre, ele fez alguns ajustes pela manhã, cultivou uma amostra de nitreto de galho à tarde e a testou. Mas dessa vez, a mobilidade do elétron foi 4 vezes maior do que qualquer nitreto de galho já cultivado diretamente em safira. Nakamura considerou esse evento como o mais empolgante da sua vida. Seu truque foi adicionar um segundo bocal ao reator MOCVD. Os gases reagentes de nitreto de galho subiam na câmara quente, se misturando ao ar para formar um resíduo em pó. Mas o segundo bocal soltou um fluxo para baixo de gás inerte, fixando o primeiro jato no substrato para formar um cristal uniforme. Por anos, cientistas evitaram adicionar um segundo fluxo ao MOCVD, pois achavam que só traria mais turbulência. Mas Nakamura usou um bico especial, de modo que mesmo quando os jatos se uniam, continuavam nominais. Ele chamou a sua invenção de reator de fluxo duplo. Agora ele estava pronto para enfrentar Akasaki e Amano. Mas ao invés de copiar a camada tampão de nitreto de alumínio, o seu design de fluxo duplo permitiu criar um nitreto de galho tão suave e estável, que poderia ser usado como camada tampão no substrato de safira. Isso por sua vez gerou um cristal ainda mais puro de nitreto de galho, sem os problemas do alumínio. Nakamura agora tinha os cristais de nitreto de galho de maior qualidade já produzidos. Mas justo quando ele estava começando, tudo acabou dando errado. E enquanto estava na Flórida, Nobuo Ogawa se afastou da Nishia para se tornar presidente. Na sua época, Nobuo era um cientista audaz, criando os primeiros produtos da empresa. Por isso que ele apoiou os grandiosos planos de Nakamura até agora. Mas no seu lugar, o genro Ide Ogawa se tornou o CEO da empresa. E o jovem Ogawa tinha uma visão bem mais rígida. Um cliente da Nishia disse: ele tem uma mente de aço e se lembra de tudo. Em 1990, um executivo da Matsushita, fabricante de LEDs e maior cliente da Nishia, visitou a empresa para dar uma palestra sobre LEDs azuis. Nessa palestra, Ele afirmou que zinco seleneto é o futuro, declarando que nitreto de galho não tem vez. No mesmo dia, Nakamura recebeu um bilhete de Eide para parar já os trabalhos com nitreto de galho. Eide nunca apoiou a pesquisa e queria acabar com o que via como um imenso desperdício. Mas Nakamura amassou a nota e jogou fora. E ele fez isso várias vezes quando uma sequência de notas e ligações similares vinha da gestão da empresa. Por rancor, ele divulgou seu trabalho sobre o reator de fluxo duplo sem a Nishia saber. Era o seu primeiro artigo. Um caiu, faltam 4. Com a formação de cristais pronta, ele encarou o segundo desafio, criar nitreto de galho tipo P. Aqui, Akasaki e Amano superaram novamente. Criaram uma amostra de nitreto de galho dopada com magnésio. Mas a princípio não agiu como um tipo P como esperavam. No entanto, após a expor a um feixe de elétrons, se comportou como um tipo P, o primeiro tipo P de nitreto de galho do mundo após 20 anos de tentativas. O problema era que ninguém sabia por que funcionava, e irradiar cada cristal com elétrons era lento demais para a produção comercial. No início, Nakamura imitou a técnica de Akasaki e Amano, mas suspeitou que o feixe de elétrons era excessivo. Talvez tudo do que o cristal precisava era energia. Então ele tentou aquecer nitreto de galho dopado com magnésio a 400 graus Celsius num processo chamado de recozimento. O resultado? Uma amostra completamente tipo P. Isso funcionou até melhor que o feixe de elétrons superficial, que só tornava as superfícies das amostras tipo P, e apenas aquecer as coisas era um processo rápido e escalável. Seu trabalho também mostrou por que o tipo P era tão difícil. Para fazer nitreto de galho com emulsivide, forneça o nitrogênio da amônia. Mas a amônia contém hidrogênio também, onde buracos deveriam existir no galho nitrato dopado com magnésio. Esses átomos de hidrogênio vinham e se ligavam ao magnésio, tapando todos os buracos. Adicionar energia ao sistema liberou o hidrogênio do material, libertando os buracos novamente. Até então, Nakamura tinha o necessário para criar um LED azul protótipo, e o mostrou num workshop em Saint Louis em 1992, recebendo uma ovação de pé. Ele estava começando a se destacar. Mas mesmo tendo criado o melhor protótipo até agora, era mais um tom azul-violeta e ainda muito ineficiente com uma potência de luz de apenas 42 microwatts, bem abaixo do limiar de 1000 microwatts para uso prático. Na Nishia, a paciência do novo CEO havia se esgotado. Eide mandou ordens escritas para Nakamura parar de ajustar e tornar o que tinha num produto. O seu emprego estava em jogo. Mas nas palavras do próprio Nakamura, eu seguia ignorando a sua ordem, eu tive êxito pois não ouvia as ordens da empresa e confiava no meu julgamento. Nesse ponto, só lhe restava o terceiro obstáculo, fazer seu LED azul alcançar uma potência luminosa de 1000 microwatts. Um truque conhecido para elevar a eficiência dos LEDs era fazer um poço, uma camada fina de material na junção PN chamada de camada ativa, que reduz um pouco o gap de energia. Isso incentiva mais elétrons a caírem da banda de condução tipo N para buracos na banda de valência tipo P. A melhor camada ativa para nitreto de galho já era conhecida como nitreto de índio-galho, que não só facilitaria a travessia do gap de banda, mas também um straight bem na medida para trazer o seu hiato azul-violeta até o verdadeiro azul. Dessa vez, Akasaki e Amano não superaram Nakamura. Eles estavam presos tentando cultivar nitreto de índio-galho inicialmente. Amano lembrou, se dizia em geral que nitreto de galho e nitreto de índio não se misturam, como água e óleo. Mas Nakamura tinha uma vantagem, a sua habilidade de ajustar o seu reator emulsivide. Isso permitiu usar força bruta, ajustando o reator para bombear tanto o índio quanto possível sobre o nitreto de galho, esperando que ao menos um pouco aderisse. Para sua surpresa, a técnica funcionou, lhe garantindo um cristal limpo de nitreto de galho e índio. Ele rapidamente integrou essa camada ativa ao seu LED. Mas o poço funcionou bem demais e transbordou de elétrons, os vazando de volta às camadas de nitreto de galho. Não incomodado, dentro de alguns meses, Nakamura solucionou isto também, criando o oposto de um poço, um morro. Ele voltou ao seu reator mais uma vez para fazer nitreto de alumínio-galho, um composto com o maior gap de energia que podia bloquear elétrons de fugir do poço, uma vez lá dentro. A estrutura do LED azul ficou bem mais complexa do que alguém poderia imaginar. Mas ele estava completo. Em 1992, Shuji Nakamura possuía isso.
E eu mostrei para o presidente. Eu lhe disse: presidente, venha ao meu escritório, por favor. Lhe mostrei o LED azul e ele disse: nossa, isso é ótimo, não é mesmo? Fiquei tão contente. Saí comemorando do meu escritório.
Após 30 anos de busca por inúmeros cientistas, Nakamura conseguiu. Ele criou um LED azul brilhante e glorioso, que até de dia se podia enxergar. Tinha uma potência de luz de 1500 microwatts e emitia um azul perfeito a exatos 450 nanômetros. Era mais de 100 vezes mais brilhante que os antigos LEDs pseudo-azuis no mercado. Nakamura escreveu: senti como se tivesse alcançado o topo do Monte Fuji. A Nishia convocou uma coletiva em Tóquio para anunciar o primeiro LED azul verdadeiro do mundo. A indústria eletrônica ficou chocada. Um pesquisador da Toshiba comentou: todos foram pegos de surpresa. O efeito nas fortunas da Nishia foi imediato e explosivo. Pedidos chegaram em massa, e no final de 1994, estavam produzindo 1 milhão de LEDs azuis por mês. Em 3 anos, a renda da empresa quase havia dobrado. Em 1996, eles fizeram a mudança do azul para o branco colocando um fósforo amarelo sobre o LED. Esse químico absorve os fótons azuis e os reemite em um espectro amplo ao longo do espectro visível. Em pouco tempo, a Nishia vendia o primeiro LED branco do mundo, enfim abrindo a última fronteira tão duvidada da iluminação LED. Nos 4 anos seguintes, as suas vendas dobraram até 2001. O seu lucro quase atingia 700 milhões de dólares por ano. Mais de 60% vinham de produtos com LED azul. Hoje, a Nishia é um dos maiores fabricantes de LED do mundo, com receita anual na casa dos bilhões. E quanto a Nakamura, a quem a Nishia devia a quadruplicação das suas fortunas?
Eu aumentei o meu salário para 60 mil dólares depois de duplicar.
Ouvi dizer que era só 170 dólares.
170 para cada patente.
Então era 170 por patente.
Isso.
Isso acontecia enquanto o LED azul gerava centenas de milhões em vendas. Eiji Ogawa sempre havia visto a individualidade teimosa de Nakamura como um risco, não como uma força. A mensagem era clara. Em 2000, após mais de 20 anos na Nishia, Nakamura deixou a firma rumo aos Estados Unidos, onde propostas de trabalho chegavam sem parar. Mas os seus problemas com a Nishia continuavam. Ele começou a consultar para Cree, outra empresa de LED. A Nishia o processou por vazar segredos da empresa. Nakamura reagiu processando a Nishia por nunca compensá-lo adequadamente pela invenção, buscando 20 milhões de dólares. Em 2001, os tribunais japoneses decidiram por Nakamura e ordenaram a Nishia lhe pagar 10 vezes o pedido inicial. Mas a Nishia recorreu, e o caso foi eventualmente resolvido com uma indenização de 8 milhões de dólares. No fim, só deu para pagar os custos legais de Nakamura. E isso é tudo que ele recebeu por uma invenção que agora abrange uma indústria de 80 bilhões de dólares. De luzes da casa a luzes da rua. Ao assistir a esse vídeo no celular, computador ou TV, se você estiver na rua seguindo semáforos ou outdoors, é provável que você dependa de LEDs azuis. Podemos até estar exagerando na luz. Talvez você tenha ouvido alertas para evitar a luz azul das telas antes de dormir, pois ela pode alterar o seu ritmo circadiano. Tudo isso que eu disse vem do LED azul de nitreto de galho. Mas quanto à iluminação, quase não há desvantagens em um LED. Comparado a uma lâmpada incandescente ou fluorescente, LEDs são muito mais eficientes, eles duram muito mais, são mais seguros e totalmente personalizáveis. 30 anos após o primeiro LED branco, lâmpadas de ponta hoje permitem escolher entre 50 mil tons diferentes de branco. Mais importante, o seu preço caiu para apenas alguns dólares a mais que outros tipos de lâmpadas como a fosforescente, e com a eficiência deles, no uso médio diário e preço da eletricidade, você recupera esse custo em só 2 meses e continua a economizar por anos a seguir. O resultado é uma revolução na iluminação. Em 2010, só 1% das vendas de luzes residenciais no mundo eram LED. Em 2022, era mais da metade. Especialistas estimam que em até 10 anos, quase todas as vendas serão de LED. A economia de energia será enorme. Iluminação representa 5% das emissões de carbono. Mudar para LED pode poupar cerca de 1,4 bilhões de toneladas de CO2, o que seria equivalente a remover quase metade dos carros do mundo das ruas. Hoje, a pesquisa de Nakamura foca na próxima geração de LEDs, microLEDs e LEDs UV. O que eles estão fazendo lá dentro?
LEDs, lasers, dispositivos de energia. Essa é uma das melhores instalações nos Estados Unidos.
E isso é por sua causa.
Não.
Qual é o tamanho padrão de um LED?
300 vezes 200 microns.
O menor é 5 microns.
Isso é incrivelmente minúsculo.
Você pode usá-los para visores perto dos olhos como AR e VR.
Você poderia ter tipo um visor de retina bem aqui.
Sim,
O cabelo é dessa grossura?
sim.
E esse é um LED bem pequenininho. LEDs UV podem ser usados para esterilizar superfícies como em hospitais ou cozinhas. Apenas ligue as luzes UV e patógenos morrem em segundos.
Durante o Covid-19, as ações das empresas de LED UV dispararam, porque todo mundo esperava que fosse usar esses LEDs UV. Podemos esterilizar todo o Covid-19. Para diodo emissor, usamos nitreto de índio galho. Para UV, usamos nitreto de alumínio galho.
Tá.
Porque o gap de energia é bem maior.
Você acha que é isso que está vindo?
Tá tudo bem, ele funciona, mas o problema é o custo. Ele é muito alto. A eficácia é menos de 10%, mas se a eficiência se tornar mais do que 50%, o custo é quase comparável à lâmpada de mercúrio.
E você acha que vai acontecer? A eficiência vai subir?
Eu acho.
É uma questão de tempo.
Sim, eu acho.
E ele até enfrenta um dos maiores desafios da nossa época.
Me interesso por física.
Eu também.
Ainda me interesso por fissão nuclear, então iniciei uma empresa de fissão nuclear.
Sério?
Sim, ano passado.
Caramba!
Eu sei.
Em 2014, Nakamura, Akasaki e Amano ganharam o Nobel de Física pela criação do LED azul. Logo depois, Nakamura agradeceu a Nishia em público por apoiar o seu trabalho e até propôs visitar e se desculpar, mas recusaram a sua oferta. E hoje, a relação deles ainda é fria. Mas talvez ainda mais crucial que o Nobel. Quando Nakamura lançou seu LED azul em 1994, já havia publicado mais de 15 artigos e finalmente obteve o seu doutorado em engenharia. Hoje, ele publicou mais de 900 artigos. Durante toda a sua carreira e jornada, uma coisa nunca mudou. Qual a sua cor favorita?
Azul.
Sempre foi azul ou só após criar o LED?
Eu nasci em uma vila de pesca.
Vila de pesca.
Na frente de casa está o oceano. Sempre foi azul.
Enquanto eu conhecia a história de Nakamura, percebi que o diferenciava dos milhares de pesquisadores tentando desvendar o LED azul não era só o seu conhecimento, mas a sua determinação, raciocínio crítico e habilidade em resolver problemas. Onde outros viam becos sem saída, ele via possíveis soluções. Então, se você busca um jeito grátis e simples para começar a desenvolver essas habilidades, conheça o nosso patrocinador de hoje, Brilliant. Brilliant faz o melhor pensador e solucionador de problemas, ajudando a desenvolver habilidades reais em tudo, desde matemática e ciência de dados até programação e mais. Na Brilliant, você aprende na descoberta, tentando por si, e não só adquire conhecimento dos conceitos-chave, mas aprende a usá-los em situações reais, construindo a sua intuição e dando as ferramentas para resolver problemas no seu caminho. Há muito a aprender na Brilliant. Eles têm milhares de lições interativas sobre quase tudo que te desperta curiosidade. E como cada aula é breve, você pode tê-las em poucos minutos. Então, se você é como eu e fez uma resolução para aprender algo novo todo dia esse ano, a Brilliant vai de fato te ajudar a fazer isso, e você pode aprender em qualquer lugar pelo celular. Quando tiver um tempinho de sobra, poderá estar aguçando a sua mente. Então, para testar a Brilliant gratuitamente por 30 dias, visite brilliant.org/veritasium ou clique no link na descrição. E os 200 primeiros terão 20% de desconto na assinatura Premium anual da Brilliant. Agradeço a Brilliant por patrocinar esse vídeo e a você por assistir.
Okay, hello everyone. Well, thanks for joining me here today. We are going to be talking about getting to the fundamental theory of physics. Now, I never expected this. If you'd asked me even last fall, I would have said that I have an idea, but I don't know if it's going to work. And I'm really excited to say that it's working. And I think we now have a real path to the fundamental theory of physics. I think we've come a long way. We're not actually at the end. We're not there yet. And I'm sort of hoping that all of us together can really finish this job. So I want to tell you kind of here where we're at so far. I mean, it's been a long road for me. I first got interested in physics nearly 50 years ago now. And I started doing physics when I was a kid. I used to do physics for a living. But as many of you may know, I've spent most of my life sort of pursuing the idea of computation, which is a really powerful idea. And it's actually what's leading us to the physics we'll be talking about here today. And I've sort of spent my life alternating between doing science and doing technology with the idea of computation. And one of the things that happened as a result of that is that back in the 1980s, I started studying this kind of universe of simple programs. And I discovered this amazing thing that even when the programs that you're looking at are very simple, even when the rules you set up are very simple, the behavior you can get can be incredibly complicated. And that kind of discovery sort of put me on a path that led to all kinds of things. And it got me wondering about whether maybe that's how physics works. Maybe there's some very simple rule underneath everything that exists in our universe that leads to everything we see. And I kind of had a definite idea about how this might work back in the 1990s. And I started working on it. And I actually wrote about 100 pages about that idea and its consequences in this, well, they're here, this big book that I wrote back in 2002. And actually, in the end, as I now realize, I got really close to figuring out what we've now figured out, but I didn't figure it out back then. And I ended up hibernating this idea for a long time and doing things like Wolfram Alpha and Wolfram Language and so on. And I always wanted to get back to this, and I was always kind of thinking about it. And then a little over a year ago, I had kind of a little idea that got me a little bit more enthused. And then two young physicists, Jonathan Gorard and Max Piskanoff, who came to our annual summer school, got really excited about this and said, "You have to work on this, and we're going to help you do it." And that's what really got me started again. And we started really working on this last fall. And it was a totally amazing experience because, as I say, I've been interested in physics for 50 years. And there are all these things about physics that I've known about quantum mechanics, about relativity, all these kinds of things. And suddenly, it all started falling into place. It all started making sense. We started realizing how this stuff really works. And it was just great. And I want to try and tell you a little bit about that experience here today. Really, the thing that I think is most spectacular about it is how beautiful the whole thing is, how all these different pieces fit together in this really beautiful way. And I should say that what we've done would not in any way be possible without sort of all of the achievements of physics so far. I mean, basically what we're doing leverages particularly the two great developments of 20th century physics, general relativity and quantum field theory. Without those, we wouldn't be able to get to where we are. And and the other thing I want to say is that one of the things that's been really neat is that there have been lots of modern developments in physics and mathematics. And it turns out that an awful lot of those seem to fit beautifully together with the things that we figured out about physics. And so it isn't one of these cases where it's like something new is coming in, you throw out all the old stuff. It's, no, we have a kind of a new foundation, but all this other stuff that's been being worked on, it fits in beautifully. And I think it's going to be something very, very wonderful to see. Well, so I want to tell you all about this here today and hopefully get your help in finishing this job. Of course, the timing of this is totally weird because we're right now in the middle of this terrible pandemic. I mean, our company has been off curating data and doing modeling and helping where we can with pandemic kinds of things. But I figured that, among other things, while we're all stuck at home, people might enjoy some physics. And there's kind of a strange historical resonance with all of this, because back in 1665, there was also a plague, and a chap called Isaac Newton had to leave Cambridge University and go hang out at home. And while he was doing that, he kind of figured out the basic ideas of calculus and his theory of gravity. Well, we may not be able to match old Isaac, but while we're stuck in this pandemic, maybe we can all figure out physics. All right, so let me show you what we have so far. So what I'm going to do here is I'm going to go through sort of a basic outline. There's a lot to say, but I'll go through a basic outline. Then we'll have a Q&A here today. Then tomorrow we'll be doing a more technical Q&A for physicists and mathematicians, followed by one talking about more sort of philosophical implications. Then on Thursday we'll do a Q&A for computer science folks. And then we'll be starting kind of live streams of actually doing this project. We really want to make this as open a project as we can. And as part of that, we'll be live streaming our kind of working sessions and our discussions with other people about this project. And we hope lots of people can participate in those. All right, well, let me get started really here. Okay, let's go here. And start. All right, so let me start off. This is our website. And you can find most of the stuff I'll be talking about here today somewhere on this website. There's probably about 1,000 pages of material on this website. Let me just point you to a few pieces of this, which maybe will be useful. First of all, there's an announcement here. This is kind of a basic outline. It was supposed to be a short announcement. It turns out it's about 60 or 70 pages, but it's kind of an outline of what we're doing here. Oops, I'm being told I'm not sharing my screen, so let's check that. That is bad. Hold on. Boom, there we go. Okay. Oh, let's start that again. So I was saying, this is this is our main website that just went live. There's about 1,000 pages of material here, and let me go through a few pieces of this. Here's some. Let me see here. Okay. So there's some our main announcement. There's kind of another piece that I've written, which is kind of about the backstory of this project, kind of how we got here. Then there is kind of technical introduction that I've written. It's kind of describes in more detail kind of how the models that we're discussing work. Then there are an area for technical documents and related material that includes a couple of papers by Jonathan that for people who are kind of equations first readers, particularly professional physicists, I would encourage you to check out some of Jonathan's work here. Then there is an area here of software tools. One of the things we're doing is to make all the tools for doing the things that we've been doing completely available. They're available today, and you should be able to run them in Wolfram Cloud or anywhere where you're running Wolfram language, and that's a way that we hope people can start to participate in this. I'll be talking more about some of these other things later. This is a registry of notable universe models. We'll be talking about that a bit more later. There's also, I'd like to point you to the Q&A. We've answered some of what we think of as the most obvious questions here. As questions come in, we'll try and answer more of them, but I encourage you to check that out also. Okay, well, let's get down to business. How do we think physics basically works? Well, here's a kind of a pictorial outline of things, and this looks kind of complicated. I guess that might be because our universe is ultimately kind of complicated, but this is a lot simpler than that. This is kind of showing way down below underneath our universe. So I'm going to be talking about different parts of this. I'm going to be talking about how we start from this very simple kind of rule, how we build up a structure that represents space in our universe, how we understand how time works, how we derive from the properties of space and time relativity, special relativity, general relativity, the theory of gravity. Then I'm going to be talking about how the different paths that you can follow in applying this rule correspond to the different paths that can occur in quantum mechanics and the way in which one gets this sort of entanglement of states in quantum mechanics and how that emerges in these models. And in a sense, one of the most spectacular things that happens is that it turns out that relativity and quantum mechanics are in some sense the same idea in these models. There's a sort of complete unification of the notions of relativity and quantum mechanics, which is one of the most beautiful things, I think, that comes out of this. And sort of in the middle of a bunch of those things are things about black holes and the quantum mechanics of black holes. Let's see, people are asking for me to zoom in a bit here. I think, unfortunately, if I zoom, I will, well, okay, here we go. I encourage you to just look at this for yourself on the web. This is under the visual summary on the website. Okay, well, let's start in on how this stuff works. So the thing that we're interested in is to figure out if there is a rule underneath the universe, what might that rule be like? And if the rule is going to be at all simple, we pretty much know that nothing that we're familiar with in the universe is going to be immediately evident in that rule. We're not going to be able to see that the rule has a 3 for the number of dimensions of space. We're not going to be able to see that the rule has some case for some particular detail of the properties of the electron and so on. That rule has to be something that sort of packages everything about the universe into some tiny bundle from which all the things that we observe must emerge. So what I realized long ago is that we need that rule to be as kind of minimal and structureless as possible. And we need to have something that sort of allows the possibility of everything that we see in the universe emerging. Now, one of the things that is sort of a basic feature of this rule is we don't get to have any notion of space intrinsically in this rule. And so we have to kind of make space out of something. And in the end, one of the things that's sort of a first surprise is the idea that happens in these models that space is something discrete. Space is made out of a bunch of discrete points that are kind of going to be knitted together. And traditionally, for the last couple of thousand years, actually, people have kind of assumed that space is somehow a continuous thing, that you can just say, I'm going to pick any position in space. It'll be specified by some precise triple of numbers, for example. And that's how we define that we can do that. We can pick any possible position in space. What happens in these models, among other things, is that that's no longer possible. And instead, we're making space out of these discrete elements. And one of the other things about these models, I said it's very minimal, very very little that gets put in from the beginning. In a sense, everything is just space. And all of the features that we are familiar with about matter and elementary particles and all these kinds of things ultimately will emerge as features of space. Okay, so let's talk about what the rules for kind of doing things in might look like. Okay, so what we're going to be talking about are rules which we can represent as rules for hypergraphs, or we'll talk about those in a minute, but we can think about them as rules for graphs or networks. And so for example, we might start off by saying, let's imagine that we have some structure like this, and we have these elements. We're just numbering them 1, 2, 3, 4. And then we have some rule that says how we're going to update this by just looking at the different patterns of elements here. What are we going to do to this structure? And it's sort of an embarrassing thing to admit, but the basic idea for how these rules work is something that is sort of also the foundation for kind of the symbolic programming that is the foundation for Wolfram language, and is actually the foundation for pretty much all of the practical things I've done in computation for the last 40 years. And the embarrassing thing is that I didn't realize that sort of the essence of that symbolic programming idea was exactly what's needed to understand how to build physics out of. And I was working on sort of a slightly different way of setting this up. But the essence of that idea turns out to be the essence of the idea that it looks like we need for physics. So this is just an example of a essentially a rule. This is just a sort of more algebraic representation of the thing I was showing earlier, this rule that tells us how to replace one sort of structure in our graph with another structure. Okay, so let's say we start off with some graph that looks like this. Then let's just try applying that rule a few times. This is what we get. So it's the beginning, then we apply the rule, we apply it again, and eventually we're getting something like this. So this is kind of the story that I first learned in the 1980s, that even when the rule is very simple, the behavior and the structure that you get can be complicated. So this is an example of what you get after just running maybe 10 steps or something with that particular underlying rule. So you can say, so what's in the end going to happen is we're going to run this rule maybe 10 to the 400 times, or a rule like this maybe 10 to the 400 times, and that's going to build our universe. Now, I will say at the outset, we don't yet know exactly what the right underlying rule is. It's going to turn out that an awful lot of what shows up in physics, and this is one of the big surprises, is quite generic and actually quite independent of the details of this underlying rule. So we can already derive lots and lots of physics without knowing this final ultimate underlying rule. One of the things we want to find is what that final ultimate underlying rule is. So if we ask ourselves, well, what kinds of things happen with different rules? Here are just a few examples of things that happen with some of the simplest possible rules. And what we're anticipating is that when we look at enough of these rules, eventually one of them will turn out to be the rule for our particular physical universe. I'm going to make a little footnote to that. I'll explain later why, in a sense, there can be many different rules that all represent our universe, but we'll get to that in more detail later. In a sense, this sort of process of looking at all these rules and seeing what happens, it's sort of a very zoological thing. It's very, it's as if you're looking at all these different possible creatures in the computational universe, and you're trying to find the one that actually corresponds to our physical universe. But so all kinds of different behaviors can occur, this is what we're interested in looking at. Okay, so first question is, how do you get something like space as we know it? So the basic idea is that when you're looking at the kind of large-scale limit of one of these structures, after it's grown for a very long time, you'll have something which, to a high degree of approximation, seems like the space that we're familiar with. So it's kind of an analogy that one's very familiar with, that we've known about for maybe 150 years, although it was guessed even much before that something like a fluid like water that seems to us continuous, it seems to sort of flow continuously. We actually know that ultimately it consists of a bunch of discrete molecules bouncing around. And I think the same thing is essentially what's happening in space, that space is just a bunch of discrete points, but on a large scale, it seems to us like something continuous that we can apply mathematics like calculus and so on to. Okay, so how can we see that more precisely? Let's take a look at a particular very simple rule. It's just one of these specific rules, and this is the first few steps of what it does. And if you keep going for a while longer, you'll discover that you can start seeing it here. It's kind of knitting this structure. Keep going for a while longer, you'll find that it knits a structure like this. Keeps going, keeps knitting this structure. Well, when we look at the structure, we can kind of make a reasonable guess that in the end, this is going to be kind of like ordinary space. It's going to be like a plane that's just a mesh that corresponds to sort of two-dimensional space. And that's, this particular case, it's very easy to see how the thing produces something that's kind of like space. So, but things aren't always that simple. Here's an example of another rule. This makes a structure like this. Understanding the limit of this is more complicated. here's another one. This makes a structure like this, which we can again kind of recognize as something that's a little bit like our sort of traditional mathematical object with a two-dimensional surface or something. Actually, if you project that into 3D and kind of fill it in, it'll make a structure that looks like this. Okay, so what we've got underneath is just this discrete collection of points, and all we know is which point is joined to which point. We don't know, there's nothing that intrinsically tells us that the thing should lay out as a structure like this. All we know is kind of the connectivity information for this network. I might mention one point is that the actual underlying thing that we have here is a thing called a hypergraph. It's a generalization of a graph where instead of just having points joined by one point joined to one other by a connection, you can have a hyper edge in which you have multiple points that are all joined together by a hyper edge. That's just sort of a detail of how we're building things, but it's why we'll refer to the structure that we think limits to physical space as being the spatial hypergraph. Okay, so let's say we want to analyze what's happening in a system like this. How would we do that? Well, one question would be, given that we have a structure that looks like this, we look at it with a very large number of points in it, what dimensional space might this correspond to? Well, actually, there's a pretty simple way to determine that, and here's how it works. And there's a little bit of mathy stuff, but it's not too bad. So if we think about a two-dimensional grid, and we just say, let's start at a point in the middle of this two-dimensional grid, and let's keep going to points that are one step away on the grid from the points we've already got to. Let's keep growing that structure and see what we get. Well, one of the things you'll see here is if we just count how many points we got to after we went, let's say, r steps, we'll discover that the number of points we got to is about r squared. So that squared in the r squared, that 2 in the r squared, that 2 is the thing that represents the fact that this is behaving like two-dimensional space. It's behaving like just a grid on a plane. If we do the same thing in a 3D, in a graph that's made to correspond to a 3D grid, we'll find out that we do that same computation, we'll find out that the number of points we get to is about r cubed. So in other words, that cubed is what tells us that we've got something that is behaving like three-dimensional space. Okay, well, we can do exactly the same thing in one of these structures here. We just start from one point and we keep going to points that are one more step at each one of these away from the points we got to already. And then we can ask the question, if we do this, how many points do we reach after we've gone r steps? Okay, and we can start plotting that, and it's a little bit complicated because there's sort of multiple things happening. We're kind of evolving the structure, so the structure is getting bigger, and we're also asking for these kind of balls of points that we're looking at. We're asking what happens as they get bigger. But anyway, when we do that, we'll find out these are just curves that represent the essentially the logarithmic difference of growth. Its growth rate. It represents it sort of fitting that exponent. And so what we see here is that exponent is roughly fit by about 2.7 or so. So what that means is that structure that we had, this thing here, in the limit, this thing is behaving roughly like 2.7 dimensional space. It's kind of like it's not quite three-dimensional space. It's more like the kind of thing you would find with fractals and so on, where it is behaving like a fractional dimensional space, but it's behaving like a space with a definite, albeit fractional number of dimensions. If we go back to something like this, and we do that same test, we'll find out that in that case, when we measure it, this thing indeed behaves like it's two-dimensional space. And if we do the same thing for something like a fractal, we can measure that, and we'll find out that it behaves like in that particular case of that particular fractal, it's about a 1.58 dimensional space. Okay, so this is kind of giving us an idea, how do we work out the dimension of space? Well, another question would be, okay, we've got space, but our universe isn't just space, it's got a lot of stuff in it. It's got a lot of particles like electrons and photons and all those kinds of things in it. And so one question would be, what are those things like particles? So the basic picture is this, that there's sort of a background of activity in space where this thing is sort of bubbling around and lots of connections are changing here. But there are certain pieces of this network that have a certain, at least local stability to them. And those things are the things that correspond to particles that we're familiar with. So as an analogy for that, we can say, imagine this network was just planar, was just everything could be laid out in the plane. But imagine that somewhere in that planar network, there was a little piece that wasn't quite planar. That might correspond to something like a particle in that network. It's a thing that's sort of locally stable in the network and can move across the network and sort of keep its identity. And that's how we think particles work. We haven't actually found particles in specific, in the more complicated rules here. And that's one of the things that we hope to start working on in the next few weeks. All right, so first thing about space is to know what dimension it is. And for our universe right now, we want that we know that number is roughly 3. As we'll talk about, maybe one of the things that comes out of this theory is that the dimension of space might not be exactly 3. There might be variations in the dimension of space that might be associated with phenomena in cosmology. It might be that in the early universe, the dimension of space wasn't exactly 3, but may have been much larger than 3. Talk about that a little bit more later. Okay, so one feature of space which was discovered, comes out of the general relativity invented by Einstein in 1915, is the idea that space is not just a flat three-dimensional thing, it's something that has curvature as well. And in fact, we can understand the phenomenon of curvature in these networks. Here are examples of networks that grew from simple rules. And we can kind of get some sense as these networks are laid out here that there's some kind of curvature to the space that corresponds to these networks. Well, that criterion that I told you for working out dimensions of space, you can use a similar criteria for working out curvature. And just to mention how that works, you know, when you might think the area of a circle is pi r squared, but if you draw that circle on a sphere, its area isn't exactly pi r squared. There's a correction that depends on the fact that it is being drawn on a curved object. And that we can kind of key into that correction. So we can work out actually that when we do this thing about saying sort of how big is the ball, how many points do we get to when we go a certain distance in our system, that will end up not being something which in this plot looks like it's just sort of flat two-dimensional space. Instead, this thing will have a variation, and that variation corresponds to curvature. And we'll see all sorts of features of that curvature. One thing I might mention, sort of from a mathematical point of view, is that what comes out in these models immediately is that what matters to the sort of growth rate of number of points is a thing called the Ricci scalar curvature, which turns out to be exactly something that shows up in general relativity. But one of the features of curvature is when a space is curved, it means that the shortest distance between points is no longer an ordinary straight line. So if you were just on this flat space, the shortest distance would just be these straight lines. On a sphere, these so-called geodesics, these shortest distances, they kind of bow out like this. This is a space of negative curvature where the geodesics get squashed together. Well, we can look at exactly these kinds of things in our systems, and we can, and this is and well, the thing. So by the way, in Einstein's idea of general relativity, gravity is associated with the fact that when things travel, like a laser beam, for example, would travel in what it thinks is a straight line. But because space is curved, that straight line to it is not really a straight line. And that non-straightness is what is associated with the effect of gravity. And we have exactly the same phenomenon. And in fact, we can go ahead and work out the effective equations for these for what happens with these geodesics and so on. And it turns out that the equations one gets for the limit of what happens with these geodesics in our space that's created just from these underlying rules being applied to create this larger and larger spatial hypergraph, it turns out that the equations that govern the behavior of these geodesics are exactly Einstein's equations. So to begin with, a little bit of more technicality. To begin with, what we're talking about so far is the vacuum Einstein equations, the equations that govern essentially the curvature and structure of space itself. Okay, so so that's a little bit on how space works. Another big thing about our universe is time. I was sort of describing this as these spatial hypergraphs, they just grow, but they grow in time. How does that time thing work? Well, one feature of the sort of traditional approach to physics is this idea of space-time, the idea that somehow space and time are in some sense the same kind of thing. And that's an idea that kind of gets a lot of special relativity is very much involved with space and time being sort of the same kind of thing. But in these models, space and time aren't intrinsically the same kind of thing. And space is this extent of the spatial hypergraph, and time is the kind of inexorable computational process by which that spatial hypergraph evolves. And it will turn out, as I'll explain, that even though space and time in these models are fundamentally very different kinds of things, it will nevertheless turn out that all the phenomena of space-time emerge and one gets all of the standard results of relativity and so on. But at an intrinsic level, space and time aren't the same kind of thing in these models. And if I were to pick sort of one potential wrong turn in the history of physics, it was probably about 100 years ago when people started saying space and time really are the same kind of thing and not considering the possibility that they should be thought of differently. It's something that's come out of sort of our computational paradigm, that time is this thing that corresponds to sort of the process of computation, and space is something different. Okay, let's talk about time. So when I showed this sequence of different steps in the evolution of this graph, I was a little bit cheating, because what I really should have shown is every individual little update that gets applied by that underlying rule. So this is a possible set of such updates, showing in purple the parts of that got applied. So what I was actually showing were these sort of complete steps after sort of every update that could have been applied to this graph had been applied. But this is kind of looking underneath, looking at every possible update that might have been applied. Okay, so here, sort of the progress of time is about the applying of these updates. But now there's a very important thing, which is this picture is not the only picture that I could make about how these updates are applied. When we're given the underlying rule, there can in general be many different places in this graph where the update could be applied. So how does that work? Well, actually, what we can think of is this whole graph of all the possible updates that could be applied. So here's the starting state. This is one update, goes to here. A different update goes to a thing which actually looks similar, but the arrows will be different here. We keep going, we'll get to these different structured states. And if we keep going again, we'll get to yet more states. Okay, so maybe it's sort of a spoiler here that this sort of branching is going to turn out to be what gives us quantum mechanics. But for current purposes, what I'm explaining is that the sort of progress of time is down the page here. And what we're seeing is that there'll be a progression from one spatial hypergraph to another, and that corresponds to the progression of time. If we continue this graph longer, well, this is a version of this graph where we didn't arrange it so that it sort of explicitly goes down the page. This is just showing the relationship between these different spatial hypergraphs. So, okay, well, let me, to sort of explain how this works. Okay, so it's going to be a little bit, we're going to get to what we call causal graphs, which are a very important concept. And they're a bit easier to explain, not in the context of spatial hypergraphs, but in the context of just rewriting strings of characters. So think of it being as like being in a sort of find replace text editor. You've got a big string of text and you're told anytime you see an A, you can replace it with BBB. Anytime you see BB, you can replace it with A. Okay, so the question is then what happens if you run your text editor sort of in all possible ways? So this is what we call a multi-way graph of what happens. So we might start with an A that can only give BBB, but then BBB could give one possible transformation as it gives AB, another transformation that gives BA, and it keeps going from there. Okay, and so we end up with this whole network of possibilities. Okay, so that's analogous to the network of possibilities I was showing you before for spatial hypergraphs, but it's a little bit easier to see in the case of strings. Okay, so we can look at that in a little bit more detail. This shows what we can think of as the updating events. So this starts with an A, and then this is the sort of updating event that says A goes to BBB, and there's more updating events. So this is showing kind of the network of states and events, showing sort of how things can progress through time, in effect. Okay, so now I'm going to make this even a little bit more complicated, because one of the big questions here is, what can happen before what? And we can think of these updating events as being like, well, you can think of them sort of computer science-ly like functions, and they have certain inputs. And a particular updating event can only occur if all its inputs are ready, in some sense. You have this kind of ordering of what can occur when, based on when its inputs are ready, so to speak. We can draw that here by adding these causal relationships. So they're saying this particular thing depends on this having happened because it needs that in order to get its input. And so down here, there might be something that needs this to have happened in order to get its input and so on. And so all these orange lines represent the causal relationships, the what thing needed to get its input ready from something that happened before, so to speak. Okay, so we can then, let's now get rid of the states and just talk about what we can call the causal graph. That is the graph that represents the causal relationships between events. This says an event here, this event here could only happen after this event here. This event here can only happen after this event here. This is a graph of causal relationships. Okay, and this is going to turn out to be sort of a critical thing in understanding a lot of what goes on. Let me show you, so if I kept going a little bit longer and I didn't lay it out, sort of starting from the first event, I might get, this might be the causal graph of relationships between different events, the threads of causality that join those events. Okay, now let me explain something, a very important idea here, which is the idea of what we call causal invariance. So one of the questions is, we've said there are all sorts of different updates we could do, and there are lots of different orderings in which we can apply those updates. But it turns out, for many kinds of underlying rules, it doesn't matter what order we use. So long as we respect this causal graph, we can do the updates in any order we want. Okay, let's show an example of causal invariance in action. Essentially, what causal invariance, this is for a particular rule that is a rule that takes our string of characters and just two at a time sorts them. So it says that BA should get turned into AB. That's all it's doing. And this is showing, starting from BBB, AAA, this is showing all the possible ways that BBB, AAA can get rewritten with that particular rule. And we see these various events that can occur and so on. Okay, so there are all kinds of different things that can happen. We can wind up with BAB, AAB, we can wind up with ABB, ABA, but in the end, we're always going to get the same answer. In the end, we're always going to get a sorted string. Doesn't matter what sequence of states we went through, we'll always get to the same answer in the end. And that's the essence of causal invariance. It's actually a property that has been studied in mathematical logic and other places. It's sort of re-emerged many times under many different names, sometimes called confluence. has a variety of different names, the Church-Rosser property, all sorts of other things. There's slight technical differences between all these different things, but they're basically the same idea. How would you know that this idea exists? If you've done algebra, you might know that when you are doing something like expanding out some polynomial, you can say, well, I'm going to expand this set of parenthesized terms first, and then I'm going to do this one, or I'm going to do it in the other order. But in the end, it doesn't matter what order you do it in. That's because that kind of algebra has this confluence or causal invariance property. And some of these rules that we're looking at also have that property. So this particular sorting rule has that property. Okay, so what? Well, the big so what is then what that's saying is there are these different possible sort of paths of history, but it doesn't really matter in some sense which path of history we choose. We're always going to sort of get the same behavior in the end. Okay, so for example, for this particular thing, we can look at what the causal graph that it makes is. Its causal graph is actually very simple. It just looks like this. Let's look at how this works in sort of actually operating on the original string. So here we have a fairly long string, and each of these yellow boxes represents an event. It represents a rewrite of BA gets turned into AB. So this is a particular choice for how we can do that sequence of rewrites. I can show you what the causal graph associated with that particular set of rewrites is. There it is. But there are lots of different causal graphs that I can use. And what we'll notice here is that even though the actual particular updates were done in different orders, if you look and you just look at the structure of this causal graph, it's always the same. So it doesn't matter what the underlying order of updates is, you'll always get the same causal graph. Okay, well, so here's the first big thing that comes from this. We get to derive special relativity. And that's special relativity is not usually something that one imagines deriving. It's something which, in a sense, is a consequence of sort of axiomatic features of the way physics is set up: constancy of the speed of light, independence of inertial frames, these kinds of things. But in these models, we get to actually derive special relativity. It might not be true in these models, but it is true. It is a consequence of causal invariance and of various kinds of limits and intrinsic randomness properties and things of these models that one gets special relativity. So let me show you roughly how that works. So let's look at a simple causal graph. Here's a simple causal graph that has a bunch of events joined in these simple ways. So let's imagine that the important thing to say is in special relativity, one of the sort of big innovations was being more realistic about what an actual observer of the universe can tell is going on. So if we sort of look from outside the universe, we might be able to see all sorts of things. But as an observer embedded in the universe, operating according to the same rules as the universe, there are limits on what we can tell. For example, in the sort of physical case, we can't, things can only travel at the speed of light. So we can't be aware of things yet that were sort of, that happened further away than we have been able to see them based on information from them coming at the speed of light. So there's a question of sort of how do we model that observer? How do we model an observer who is embedded inside the system? And I might say that for the systems that we're looking at here, one of the things you might ask is, if the observer operates according to the same rules as the system itself, what consequences does that have? Let me give you an example of a consequence that have, a rather bizarre consequence. Let's say that we were to set up the universe so only one place in the universe ever gets updated at a particular moment. So what's then happening, it's kind of like a Turing machine in computer science. You have this sort of head that's zipping around the universe, updating different parts of the universe. You might say, that can't possibly be the way the actual universe works. I can plainly see that's not what's happening. The problem is, if you start thinking about it, you realize that you can't see anything until, in a sense, you've been updated. And as this head zips around trying to update different things, it's kind of the causal network that it is producing is one that actually can look pretty much like this, where you can't tell that that thing over there has or hasn't been updated until you yourself have been updated. And so when you sort of put all of that together, you realize that you get this sort of one integrated causal graph in which, in a sense, things to you as an observer can sort of seem to happen at the same time, even though to something sort of outside the universe, you might imagine seeing this head just zipping around doing different things at different times. Okay, so how do we make sort of a model of what that observer is like? The thing an observer will do is to say, okay, I'm going to decide what counts as successive moments in time for me. And so this is mathematically foliation of this causal graph. And this is saying these are the successive moments of time that I, as an observer, am going to decide to identify as this is my definition of time, is going to be the sequence of slices like this. Okay, well, the important thing is, let's see, I think I have a better picture than that. Yeah, here we go. So, right, so let's imagine that our observer is not just stationary, but our observer is moving. Okay, so this is now our moving observer. To our moving observer, that moving observer will choose their kind of foliation of space-time in a different way. If we say, well, what will this be perceived like to an observer, we'll realize that the sort of perception to the observer is of something like this, where the observer will say, okay, I'm just having these sequence of simultaneous things of sort of surfaces of simultaneity, what are in physics called space-like hypersurfaces, the sequence of space-like hypersurfaces, and then this and that, when I make that transformation, my causal graph will seem to me like this. Okay, so what? Well, the so what is that transformation of the causal graph happens to be exactly the transformation that occurs in special relativity. And in fact, we can see kind of, so what's happening here is that even though we might start off from this just simple rule that's operating according to in this particular way, it produces this causal graph. Once we have this causal graph, when we are entities sort of existing in this universe as part of this causal graph, we will end up perceiving the operation of the universe to be exactly the way that special relativity says it has to be. So one of the phenomena in special relativity is time dilation. And time dilation is kind of, as we can kind of see time dilation here in my other picture probably. Oh no, that one. If you're moving in space, if you're kind of exploring space more rapidly, time will move more slowly for you. And let's take a look at how that works in these systems. So let's say we've got something like this. So time, the events are sort of occurring at a certain rate here. If we now pick a different reference frame, if we are effectively traveling at a certain speed in space, this is the sequence of underlying events that we'll perceive. And you'll notice that it takes longer to get to the final answer here than it did when we were just sort of stationary and choosing to choose our sequence of time, moments of time differently. And that phenomenon is, in fact, exactly time dilation in special relativity. And the reason, okay, so why does this all work? The reason this works is because of causal invariance. What causal invariance implies is that even when we are picking this different reference frame that corresponds to going at a different velocity, even when we pick a different reference frame, it will still be the case that the causal graph that we get out from the system will be the same, and that's a consequence of causal invariance. And so causal invariance implies special relativity. Now, the real situation is a little bit more complicated than I've showed you. The real situation, this is a slightly more realistic causal graph, still not really as wild as they come. But this is sort of the foliation of this more realistic causal graph. And it's the fact that this causal graph has this property of causal invariance that implies the validity of special relativity. So again, even though space is this whole thing that's built up from this extent of the spatial hypergraph, time is just this sort of computational progression of applying update rules. It's still the case that when we look at what we as observers inside that universe perceive, what we perceive as the causal graph, and when there is causal invariance, that has the consequence that what we see will satisfy the rules of special relativity. In a sense, the causal invariance is what leads to the independence of reference frames that special relativity talks about. All right, so that was the first. I mean, I think it's a big deal. I knew this in the 1990s, actually, that from models like this, it was possible to derive special relativity. Let me tell you something I didn't know at that time, which is what things like energy are. So and it's really surprising to me that it's possible to say this as simply as it'll be possible to say it. So I'll just say what the final statement is. Energy is the flux of causal edges through space-like hypersurfaces. And so what does that mean? It means when we look at this picture, I made these slices here. These are the so-called space-like hypersurfaces. These things here, these are the causal edges. And the statement is the energy, if we look at some region of the universe and we ask how much energy is there in this region of the universe, the answer will be the amount of energy that's there is basically the density of these causal edges that slice through these space-like hypersurfaces. And in fact, so that's in this model, that seems to be what energy corresponds to. So momentum, for example, corresponds to the flux of causal edges, not through space-like hypersurfaces, these horizontal surfaces, but through what are called time-like hypersurfaces, which are the sort of orthogonal surfaces here. So the momentum corresponds to the flux of these edges through time-like hypersurfaces. Well, now one of the things that comes out in relativity, that's sort of an assumption in relativity, is that space and time have the same relativistic transformation properties as energy momentum. In this model, that is derivable, and that comes about because of this fact that energy represents these slicing through space-like hypersurfaces, momentum slicing through time-like hypersurfaces. When you work it out, you'll discover that that it implies the same special relativistic transformation properties for energy momentum as for space and time. Okay, so another big thing in the world is mass, and you can understand mass, rest mass, in terms of this as well. Rest mass is a little bit more complicated to describe, but it is essentially it relates to kind of the part of energy that kind of does not correspond to communicating with different pieces of the spatial hypergraph. It's the part of the energy that sort of has to do with a single part of the spatial hypergraph going sort of being rewritten in place, so to speak. That corresponds to mass. So actually, I think I even mentioned in the announcement post, and I mentioned in more detail in the technical paper, and I think Jonathan mentions in even more detail in his technical paper, that means from those definitions of energy and mass and so on, we can simply derive, for example, E equals mc squared, which again is quite remarkable because that's not something that has been derivable in physics before. That's something that really comes from the sort of axiomatic assumptions of relativity. But in this case, it's actually derivable from sort of the underlying structure of these models. Okay, so that's okay. So I should mention another thing. The Einstein's equations for gravity, the way Einstein's equations work, they say, this is kind of a version, actually that has it's a version of Einstein's equations that talks about the curvature of space, that's what's on the left-hand side, equals this thing here, the energy momentum tensor, that has to do with energy and momentum in space. Well, since we think we know what energy and momentum is, and we think we know what curvature is, we should be able to derive this equation. And indeed we can. And indeed this equation follows as a result of causal invariance. This equation is an inevitable consequence of causal invariance plus a few other kind of mathematical features of these models. In fact, to say how it works roughly, the main other assumption is that sort of at a microscopic level, the sort of individual rewrites that are happening occur in a kind of random way. Now, they're not really random at all. They're completely determined. But when we look at one of these things, it looks to us random. It's the same thing that happens, I don't know, in the digits of pi, for example. The digits of pi have a completely determined sequence, yet when we look at those digits, they seem for all practical purposes random. And if we do statistics on those digits, they'll come up as being just like a random sequence to all of our statistical tests. Well, the same thing happens for the points in space. At a very small scale, the points in space are completely determined how they all work and how they're all connected, but they seem for all practical purposes random. And that effect of randomness allows us to use various kinds of statistical arguments that allow us to derive sort of the continuity of space and so on. And essentially we need that kind of intrinsic randomness generation. We need causal invariance, and we need one other crucial fact. And the other crucial fact is that the universe is finite dimensional. The universe is not zero dimensional and it's not infinite dimensional. And if we put those facts in, then we can derive Einstein's equations. And it's actually analogous. The derivation is actually surprisingly analogous to the derivation of the equations for fluid flow from knowing about microscopic dynamics of individual molecules. And for sort of the same reasons as it doesn't matter what the individual molecules look like, you still get the same fluid equations. It doesn't matter the precise details of the underlying rule here, you still get Einstein's equations. So kind of another big deal. I mean, I kind of knew this, well, I knew at least the left-hand side of this back in the 1990s, that was derivable from models like this. But since I didn't know how energy momentum worked, I couldn't really get the right-hand side properly. Okay, so that's that. So let me talk a little bit about the other things in the universe, so to speak, and then I'm going to talk about quantum mechanics after that. So let's talk a little bit more about the universe. So one question is, when we look at the, so when we look at the spatial hypergraph and its evolution, can do all kinds of things. Here's one of the bizarre things that can happen. A piece of the spatial hypergraph can break off. It's like, we've got the universe, it's all going along just fine, and then a piece just breaks off. Once it's broken off, it can never communicate again. It's stuck. It's a disconnected piece of space-time, okay? Well, what does that remind us of? That reminds us of black holes. And indeed, in these models, it's pretty natural to form black holes. This is a causal graph. And this causal graph says you start here and everybody's communicating, everybody's going back and forth. But then, well, then it splits. And this part of the causal graph splits off from this part of the causal graph. This is the inside of a black hole. This is sort of the outside of a black hole. So that becomes a natural thing that happens in these models, the formation of singularities, and a lot of the phenomena. Essentially, if you are familiar with general relativity, these causal graphs of ours are very much like the causal diagrams of general relativity, but they are now derivable from something much lower level. So if we look at, what might our universe be like, these are just sort of three examples of different kinds of rules. This is one that forms a lot of disconnected pieces that these pieces are not space-time disconnected, but they are causally disconnected. So they will act like black holes. This one is a weird universe where things don't communicate much with each other. This is more like sort of this is way too simple to be our actual universe, but this is more like ordinary space. So now one question would be, in the very early universe, what might it have looked like? And one of the things that comes out of these models is the idea that the very early universe could have been much higher dimensional than our current universe. And that turns out to solve a bunch of problems about inflation in cosmology and so on. The idea that you have a universe that starts very high dimensional so that everything can easily communicate and then only gradually becomes more like three-dimensional. Now, by the way, when I keep on talking about dimensions changing and so on, there isn't a lot of good math around how to do that. Typical studies of the way things work are based on spaces of fixed dimension and typically integer dimension. And so, for example, essentially all of calculus is built on the idea that one's looking at sort of continuous spaces of integer dimension. And so in order to really, one of the things that we need is to figure out essentially a generalization of calculus that works for these fractional dimensional spaces, and that also works for spaces which can change their dimension, and which can work for things, bizarre things, like it could be the case that it's possible to reformulate general relativity, not in terms of curvature of space, but in terms of dimension change in space. So those are some of the kinds of strange things that can happen. Let me mention one other thing while I'm talking about structure of space, and let's talk a little bit about particles again. So, I've studied cellular automata a lot. This is an example of a cellular automaton. A cellular automaton, unlike the models we're using for physics now, where there's just a bunch of points that are all connected in arbitrary ways, a cellular automaton has a very rigid grid. It's just a rigid grid of cells. Each cell is, for example, either black or white, and there's a rule that updates the color of each cell based on its neighbors. So it has a very rigid notion of space and time. It doesn't have dynamic emergent space and time. It's just you put it in from the beginning and then you see what happens. But it's easier to actually run simulations and so on. There's a particular cellular automaton, rule 110. And one of the features of this cellular automaton is you can see that it has these kind of like persistent localized structures that develop in the cellular automaton. And these behave very much like particles. They interact, they have various rules for colliding, et cetera, et cetera, et cetera. This is kind of this is a kind of an analog of the particles that we might see in these networks. And as I mentioned before, we don't yet know in detail how that works. I've been interested in these things for a long time, and I've asked, for example, some of the world's leading graph theorists about how we can understand things about how localized structures might work in graphs. And I think a good example of a quote was, "Come back in 100 years and we may know more about how that works." Well, my hope is that one of the things that we're able to do now is, because we can actually simulate these things, and we actually we can build up our intuition from actually doing things with computers, we might be able to accelerate that 100 years a great deal. So one thing I might mention about particles is one thing we would hope is that eventually we can derive from these underlying rules what particles should exist in the universe, and the fact that there are electrons and muons and tau leptons and gluons and photons and all those kinds of things. Let's talk a little bit about that, though. One of the issues is, just because you know the underlying rule doesn't mean that you immediately know its consequences. There's a phenomenon I call computational irreducibility that I started studying a lot in the 1980s, that basically says that the process of knowing what will happen, even in a system like this, can be something that requires an irreducible amount of computation. You might say, gosh, I don't need to, the rule is so simple, I can just jump ahead and say, this is what's going to happen a million steps in the future. Well, it turns out you can prove that you can't do that. Essentially, the reason is that whatever it is that you're going to use to jump ahead is itself like a computer, and this thing behaves like a computer, and those two things are essentially computers of equal power. There's a thing I call the principle of computational equivalence that says that, and that we have increasing evidence for, and that means that we just don't get to jump ahead. It's an irreducible process to know what will happen. And that's one of the things if we have this underlying rule for the universe, to know its consequences requires sort of an irreducible amount of computation. And among other things, to, for example, know its consequences for the, whatever it is, the 14 billion years that our universe has existed, we would have to essentially run the computation that corresponds to all those steps of evolution of our universe, which we don't get to do in the universe, and we don't get to really accelerate it much because of computational irreducibility. Now, the good news about computational irreducibility is that whenever there's computational irreducibility, there are always pockets of reducibility. There are always pockets of places where you can jump ahead. And those are the pockets that we have to kind of live in when we try and actually understand how the physics of our universe emerges from these underlying rules. Actually, I should say one of the sort of spectacular things that I really did not expect at all is that in these models that involve these hypergraphs and so on, it turns out that there's kind of a layer of reducibility that sits on top of this sort of underlying computational irreducibility. And that layer of reducibility is precisely what allows us to derive things like general relativity and will allow us to derive quantum mechanics. It's the fact that in these models, for reasons I did not expect, although it's sort of obvious after the fact, there are things about them that are both generic and don't depend on the precise details of the underlying rules and are not kind of ensnared by this kind of irreducible difficulty of computational irreducibility. So that's an important piece of why it's been possible to do this project so far. And we don't know exactly how far this computational reducibility is going to go. And we don't know, for example, whether it will allow us to derive things like features with local gauge invariance. I'm kind of expecting that it will. And we don't know whether it will go as far as telling us things like particle masses. My guess is it won't, and that those will be specific to particular rules. But anyway, so we can start to try and work these things out. I might just mention one thing. We know certain particles, they've been discovered by particle accelerators and all these kinds of things. We've got sort of a mystery in the universe that it seems like a large fraction of the matter in the universe is dark matter that we don't know what it is yet. So sort of the hunt has been on for what that might be. In our models, there are a bunch of, there's a sort of a question of what the spectrum of particles might be like. So one feature I'll talk about a little bit more later is it turns out that an electron, which is kind of the lightest non-zero mass particle, well, except for kind of the neutrinos, which have a weird way of having mass, that we know about. But in our models, for reasons I'll try to explain, there's reason to think that there might be particles incredibly much lighter than the electron, that are like 10 to the 20th times lighter than the electron, but not of zero mass. Non-zero mass, but very light compared to the electron. And that's sort of interesting because that's a potential candidate for things like dark matter. I've called these things oligons. The reason I call them that is because it comes from the Greek word oligos. It means few, and I call them that because they're things that involve, they're particles that involve few hyperedges in the spatial hypergraph. And so that's one of the things that's sort of a prediction of this model is the expectation. We don't know exactly where those particles will be, but that there will be particles very light compared to the electron that will exist. Okay. So somebody's asking what the sort of caption of this image. This is the Rule 110 cellular automaton. Okay, let's go on and talk about quantum mechanics. So let me see, what do I have here? Oh, okay. All right. So one thing, so quantum mechanics is this sort of strange feature of physics that was discovered originally around 1900, was the first inkling of it, and then it really sort of came of age in the 1920s. And my friend Dick Feynman always used to say, nobody really understands quantum mechanics. And I know I certainly didn't understand quantum mechanics before really recently. And there's still more to figure out about it. But one of the features of these models is quantum mechanics is not an add-on. It's not something where you say, oh, there's physics, we understand classical physics, we understand that there are certain laws of motion and things like that. Oh, now we have to add on quantum mechanics. That's another physics course which has to get added on, so to speak. That's not the way this works. It is absolutely inevitable in these models that one has to have quantum mechanics. And so the reason that comes about is the thing I was talking about earlier, that there are these rules, and there isn't just one way the rule can be applied. There are many ways the rule can be applied. And what we think about is apply the rules in all possible ways. And in a sense, all these different possible ways. So what a key feature of quantum mechanics is that it isn't the case that one always says a definite thing happens. In sort of classical physics, one says, the ball moves in this trajectory and it's definite. in quantum mechanics, one says the photon can go this way or it can go that way, and there can be interference between these different ways that it goes. And it's all something where one traditionally is just saying there's a certain probability of measuring it to be this or that. So there are these many paths of history that get followed, and we get to sample sort of the aggregate result of those different paths of history. And that's exactly what's kind of happening here. Now, so sort of this would be kind of the classical version is you just have those sequence of strings. I'm looking at strings rather than hypergraphs here because it's a bit easier to do that. Okay, so how does quantum mechanics then work? Well, these different possible things correspond to these correspond to the states that one talks about in quantum mechanics. Eigenstates, pure states, whatever, that one talks about in quantum mechanics. Okay, so here's sort of a big story of quantum mechanics. Turns out, in quantum mechanics, one should think about, one thinks about this is the sort of multi-way system of all the possible things that can happen in quantum mechanics. Now imagine that we're an observer, also embedded in this multi-way system, observing it. And we're trying to make sense of what's going on in all these different paths that are going on and the different paths going on inside us and so on. We're trying to make sense of all of this. What we'll end up doing is doing something very much like what we did in space-time. We'll make these kind of foliations. We'll say, we are going to view the world according to this particular reference frame. We're calling these things now quantum observation frames. There's kind of a new idea about how to think about quantum mechanics. This idea of thinking about it in terms of sort of reference frames, a bit like relativity. One of the things that happens in quantum mechanics is this idea that you make a measurement in quantum mechanics. There are all these different possible things that are happening, but at some point you say, I'm going to figure out, did the electron go that way or this way? You make a measurement, and then after you've made the measurement, it's definite. It's never going to change. That will be the result of that measurement. Now, one of the things that's been very mysterious in quantum mechanics is the fact that given that there are all these different paths of what can happen, how can it be the case that different observers, different measurements sort of are consistent? How can there be sort of an objective reality in quantum mechanics, even as what's coming out is just saying there are all these different paths and all these probabilities for paths and so on? And so this model of ours kind of explains that. And it turns out that the origin of kind of the objectivity in quantum mechanics, the fact that there's a definite reality in quantum mechanics, is precisely the same phenomenon of causal invariance. Even though there are different ways that one can make measurements, even though there are different kind of quantum observation frames that one can use, one still ends up with a consistent sort of view of reality. And that's a consequence, just like in relativity, the fact that we got sort of the same laws of physics independent of whether we were moving at different speeds, and that corresponded to different reference frames in relativity. So here, these different quantum observation frames correspond to different sort of slices of viewing reality, but nevertheless, because of causal invariance, they all ultimately correspond to the same reality. So what I'm showing here is kind of a cartoon version of a quantum measurement. What happens here is one's saying, okay, the quantum system is evolving, and then what happens here is the observer is deciding to make a foliation in which they're essentially freezing time. They're saying, I think this is the way things came out, and I'm sticking to that. And so I'm basically making these successive time steps all be scrunched together here. Now, again, a little bit complicated what's going on here. I will make an analogy. This is kind of what happens. So this is analogous to what happens in a coordinate singularity in general relativity, in space-time. It's actually analogous to what happens at the event horizon of a black hole. Effectively, what's happening is that you're freezing time. Now, in this case, you're just freezing time by a convention. The observer is choosing this way of setting up time. They're choosing to decide that time isn't going to change for them after they get to this state. And it turns out when they do that, things, in order to maintain consistency, they're sort of the region that that is then frozen for them will get larger and larger. And that corresponds to quantum decoherence and to sort of the entanglement of states in quantum mechanics. Okay, so this is a super simple case. This is a slightly more complicated case. The real case is vastly, vastly more complicated than this. But this gives some idea of how you can have kind of time-freezing foliations in this. Well, it turns out when people do quantum computing, they really want to freeze the state of a particular qubit. They want it to stay as a pure state. They say, this is the state, I want it to stay this way. And essentially what they are doing is to form a black hole in this multi-way space. So the thing to understand, and sort of a very beautiful analogy, I think, is that we talked about space-time, we talked about how there's a causal graph in space-time. We now are talking about the multi-way graph, and and we're talking about foliations of the multi-way graph, and those foliations are, as I was mentioning, directly analogous to the foliations that we do in space-time. And so one question that you can ask is, okay, when we looked back at something like this was a foliation of a causal graph. The slices here, when we look at these slices and we say, what are the states associated with these slices? These slices correspond to instantaneous spatial states. So they correspond to spatial hypergraphs at a particular moment in time. That's what the foliation of the causal graph in space-time corresponds to, is spatial hypergraph. Okay, what is the foliation of a multi-way system? What does that correspond to? Okay, well, we can think of that, it turns out, as a thing we're calling branchial space. I'm sorry, my British accent probably ruins that word, but branchial. Unfortunately, Jonathan also has a British accent, and we're the ones who've been talking about this a lot, and so we don't really know if this works in American, but that's the word we're using. Okay, so the slices here correspond to what we call branchial space. If we kind of take that slice and look to the side, we'll discover that these successive steps correspond to the way that multi-way graph worked. They define connections between different states in branchial space. And those connections are a map essentially of quantum entanglements. This is essentially a map of entanglements in the space of quantum states. And so that's so this is then, we get to kind of analyze sort of the entanglements of quantum states. So again, there's space-time with this notion of extent in space. In the multi-way graph, the different nodes in the multi-way graph correspond to different quantum states, and there is a notion of a space of different quantum states, and there is this way that we can kind of knit together these different states by using not sort of positions in space, but instead entanglements in branchial space. And so what we've got is this notion of branchial space corresponding to the analog of physical space, but in the space of quantum states. Okay, so so now we can start asking questions. So we've got a whole setup that's a bit like general relativity. We've got so a bit like relativity. We've got these foliations, and I would say that when we foliate the space, the thing what's going down the page here is still time, just like it was for space-time. But what's going across the page is not physical space, it's branchial space, the space of quantum states. And so then we can ask ourselves, well, is there an analog of general relativity in branchial space? And it turns out that there is. And essentially what's happening is, when we look at geodesics, the shortest paths in branchial space, those we can ask a question like, if we want to get from this quantum state to this other quantum state, what's the geodesic that goes from one quantum state to another quantum state? And we can ask about how those geodesics are affected by the presence of other quantum states. And so effectively what ends up happening is that the geodesics in branchial space when you want to get from one place in branchial space, one quantum state, which is a sort of position in branchial space, to another one, you're going along these geodesics, and the geodesics are deformed by the presence of other quantum states. And that deformation, the presence of other quantum states. Okay, I have to mention one other thing. I mentioned that in space-time, energy corresponds to the flux of causal edges through space-like hypersurfaces. Well, we can make, and it's a slightly more complicated thing, just like we can make a causal graph in space-time, we can also make a causal graph in multi-way, in branchial, well, in the multi-way graph. And this is a thing called the multi-way causal graph. And causal invariance implies that the multi-way causal graph is essentially can be decomposed into a collection of identical causal graphs corresponding to each different path in the multi-way system. But basically, this multi-way causal graph is a representation of causal relationships, not only across through space, but also through branchial space. It's a representation of the causal relationships that between events that occur both at different places in space and at different places in the space of quantum states. Okay, and now it turns out that we can use the exact same definition of energy for the multi-way causal graph as we could for the ordinary causal graph. It's still a flux of causal edges. Now, in the details of the way that physics works, it's always been a bit mysterious how the energy of classical mechanics, in particular statistical mechanics, relates to the energy that appears in quantum mechanics. In this setup, the way it works is they're both fluxes of causal edges. They're both fluxes of causal edges that, in a sense, decompose the same way, but one of them can be thought of as part of as flux of edges in the multi-way causal graph, the other in the ordinary causal graph. Okay, slightly complicated, but that means that when we are asking about geodesics in branchial space, just like in physical space, the geodesics, the shortest paths, are affected by the presence of energy, the same thing happens in branchial space. So in other words, the geodesic that determines the sort of the path that lets you get from one quantum state to another is affected by the presence of essentially energy in the system represented by a feature of the multi-way causal graph. Okay, so what? Well, the big so what is that the analog of Einstein's equations, effectively, which tells you about the deformation of this geodesics, tells you that the presence of energy makes the geodesics turn. And okay, in slightly fancier physics, when you're talking about energy and momentum, there is a relativistically invariant quantity called the Lagrangian, which is sort of a combination of those things. And it turns out what actually matters here is the Lagrangian density. And that's what actually turns the geodesics in branchial space. Okay, well, the turning of geodesics in branchial space gives you the equations of motion of quantum mechanics. And so that, and the most direct way to think about that, my friend Dick Feynman, one of his great achievements was this thing called the path integral in quantum mechanics, which is the mathematical formalism that's sort of the underpinning of most modern ways to approach quantum mechanics. The path integral says you are looking at between one quantum state and another, the world can take many paths, but each path is weighted by a particular quantity, e to the is over h bar. And in this setup, we get exactly the path integral. In other words, when you look at these geodesics and the deformation of these geodesics, the way these geodesics are deformed is precisely the way they turn exactly corresponds to this e to the is thing. We're thinking about them as turning in branchial space. You can equivalently think about them in terms of complex numbers, but we're effectively thinking about them as vectors in branchial space. Branchial spaces are wide, so that's a pretty big deal, that I think, that it's possible to derive the path integral from this underlying structure of the multi-way graph and the multi-way causal graph and so on. It's also just super cool that the fundamental fact of quantum mechanics is the same as the fundamental fact of space-time, and that essentially the analog of the Einstein equations is the path integral. So we might ask, what is branchial space actually like? Branchial space is very complicated. Whereas physical space is nice and tame and seems to be roughly three-dimensional, branchial space is much more complicated and sort of probably exponential dimensional. It's kind of like some kind of projective Hilbert space or something. It's a complicated thing and we need to understand more about it. But we can already say things like these aggregate facts about geodesics and about the path integral without knowing more details about branchial space. But to really understand branchial space, we have to go and do more there. I should mention that the analogy between quantum mechanics and general relativity has another interesting piece. So, for instance, you might know the uncertainty principle in quantum mechanics. That if you make a for example, if you make a position measurement and then you make a momentum measurement, that the one measurement affects the other, or effectively that if you and that corresponds to the formalism of quantum mechanics, the non-commuting of the operators that represent the operation of doing a position measurement and doing a momentum measurement. So essentially, what one's saying is you do position, then you do momentum, and that isn't the same as doing momentum and then position. Okay, so turns out mathematically that is a statement that these operators do not commute. Okay, well, in general relativity, we have an analogous thing. We have so-called covariant derivatives. We have taking paths in space. So you can say, let's go horizontally, let's go vertically, let's go horizontally, let's go vertically. And when you're in a curved space, you don't get back to where you started from again. And that's a consequence of curvature. It's represented by the Riemann tensor in standard differential geometry and in studies of space-time. Well, it turns out that exact same phenomenon happens in branchial space. You have the same, you don't get back to where you started from in branchial space when you apply these two operators in two different orders, and that's exactly the uncertainty principle. Then there are all kinds of other things that you can derive in quantum mechanics, and Jonathan has written a nice paper that goes through some of the mathematical details of that. But anyway, that's the, okay. So let me now mention a couple of things here. And I'm getting closer to the end here. I'm going to talk a little bit about some of the sort of what this all means and so on. But let's talk about this sort of analogy between space-time and branchial space, the space of quantum states. This is a very, very simplified representation of a multi-way causal graph in which we're essentially seeing kind of edges that correspond to edges that correspond to, this is sort of the time direction, and we're seeing there's extent in space and there's extent in branchial space, okay? So we're now seeing sort of together, sort of physical space and branchial space. Most of the time, physical space and branchial space don't really get together much. Near black holes, they can get together and all sorts of fun things happen. But let me mention another feature of this. So in space-time, one thing that happens is there's a maximum speed at which information can propagate, and that's the speed of light. And we can see that in these models because in a causal graph, the maximum rate of information propagation here, let me pull up a causal graph here, the information propagates by going from one event to another. And we can make up light cones effectively by saying which events are in the future light cone, which events can be got to from this event here. And that you can only get to a certain cone of events in the future of that event. And the width of that cone essentially corresponds to the speed of light. And in a sense, the conversion from an elementary time going down here to an elementary distance in space going across, that conversion factor is precisely the speed of light. Okay, so in branchial space, the same kind of thing happens. In the multi-way causal graph, you can make also cones that aren't light cones. They're now what we call entanglement cones. They're cones that represent the maximum speed at which you can entangle new quantum states. So they represent sort of a limit to the rate of kind of measuring more quantum degrees of freedom. Just as in the case of space, they represent the speed of light represents the maximum rate of kind of sampling new parts of space. So the maximum entanglement speed represents the maximum rate of sampling new parts of quantum space, new quantum states. Okay, so that maximum entanglement speed has all kinds of consequences. Let me mention one thing that relates to black holes. So in a black hole, there's an event horizon, and the event horizon is associated with the fact that, well, you can think of it as a black hole is something where the escape velocity of the black hole is more than the speed of light. Nothing can get out of the event horizon around the black hole. That comes up that in our models, that event horizon is associated with a separation, a disconnection in the causal graph that corresponds to effects that can't propagate from one side of the event horizon to the other. So in addition to a physical event horizon associated with the space-time causal graph, in our models, there's also an entanglement event horizon that's associated. One can think of it as also exceeding the maximum entanglement speed, that effects would have to exceed the maximum entanglement speed. And so all sorts of bizarre things happen. So there's an entanglement horizon that actually sits outside of the causal event horizon. And the entanglement horizon is not localized in physical space, it's localized in branchial space, but it's something that's outside the space-time event horizon. And so that, if you follow the theory of black holes, there's been sort of an information paradox about black holes that has to do with where do the quantum degrees of freedom that sort of reside between a black hole that starts and a black hole that eventually evaporates in Hawking radiation. And I think we now kind of understand a way in which that works, which actually dovetails very nicely with a bunch of recent thinking about that's happened in particularly in the ADS CFT correspondence and in the ER equals EPR work that's been done recently in theory of black holes and so on. But in any case, in our picture, what happens is there's this entanglement horizon that sort of sits outside of the causal event horizon, and there can be sort of quantum degrees of freedom that exist there and are preserved even when the black hole forms. Okay, let me mention one bizarre thing that happens. So in a black hole, I think in Russian, black holes are called frozen stars. And the reason for that is that if you look at a black hole from a great distance, it will never ultimately seem to form. So, and what will happen is, for example, if you're looking at a spacecraft that's falling into the black hole, falling through the event horizon, to you as an outside observer, it will seem to be freezing time right at that event horizon. It will never seem to go over the event horizon to a distant observer. And actually that freezing of time at the event horizon is exactly the same kind of thing as is happening here. When you try to make a qubit in a quantum computer, what you're effectively doing is to make a black hole in branchial space to try and freeze time around your qubit to prevent it from being affected by the rest of the universe. Same thing is, but now in the analysis of black holes, so in physical space, you're effectively freezing time as you go over the causal event horizon. What happens as you go over the entanglement event horizon? Well, if you're an observer there and something rather bizarre happens, effectively you are, I should mention another thing. When you go through the event horizon, when you go into a black hole, you get what's often technically called spaghettified. You get elongated, very sort of by the tidal forces of gravitation. You get kind of extended in space. Well, the same thing happens at the entanglement horizon. You get extended in branchial space. And one of the consequences of all of this is you basically can't do a quantum measurement there. It becomes infinitely difficult to do a definitive quantum measurement. So a way to think about this is at the entanglement horizon, an observer can no longer form a classical thought. They can no longer come up with a definite conclusion about what happened. They will always be stuck sort of having this quantum indeterminacy. And that means, for example, if they ask, when they have a couple of particles, like a pair of particles, and you say, did the particle fall into the black hole or not? The observer stuck at the entanglement horizon will say, I don't know. I can't form the definite classical thought of whether the particle fell into the black hole or didn't. So that's just one of the weird things that happens at the entanglement horizon. That's one of the places. So let me show you something. So one question is, I've talked about this structure of space and how it might be discrete and so on. So one question you might ask is, how big are these little connections in space? And I forgot to make a slide here, but so I have to show you. Actually, I might just mention in my more technical paper, there's kind of a table of what the different kinds of things that we know about in physics correspond to. So things like local gauge invariance, the expansion of the universe, conservation of energy, microscopic reversibility, all these kinds of things, virtual particles, all these kinds of things that one discusses in physics. We're trying to understand the analog of those in our models. By the way, I might mention one big analog is in terms of cosmology. One of the mysteries of cosmology has been that when you try and mix quantum field theory with general relativity, there's sort of an incompatibility in cosmology, because quantum field theory says there's sort of an uncertainty principle about particles that says that in a quantum field, you don't know how many particles there really are there, and there's sort of this infinite soup of virtual particles that are getting produced. And those virtual particles will have an energy density that's absolutely huge. And that energy density would roll if you then applied that energy density in Einstein's equations, it would roll the universe up into a tiny ball. Well, in our models, that doesn't happen. And the reason that doesn't happen is because those virtual particles, all of that sort of bubbling around in the quantum field is precisely the thing that makes space in our models, because space is being made by the same kind of stuff that particles are made of. And in fact, so in a sense, space is making the particles. The particles are the space. And so you don't get to, that means it's not like the particles are added to the space and then curl it up. The particles are making the space. And so you don't have that same kind of issue with 0-point energy and so on. Anyway, let me go down and just show you something here. This is about, well, how big are these things? What is the elementary length? Okay. So one thing that people have often talked about is a thing called the Planck length, which is something you get from dimensional analysis in traditional physics. And the Planck length is very, there's a bug there. The Planck length is very, is something very involved in what we're talking about, but it isn't exactly what we're talking about. So we don't have a tremendously good way of estimating the elementary length, but we have a possible way of estimating the elementary length. And let me tell you how it comes out. So in the best estimate we have of the elementary length is that it's 10 to the minus 93 meters. Now that's really small. The Planck length is 10 to the minus 34 meters. And so this is really tiny compared to the Planck length. Actually 10 to the minus 35 meters times this quantity. So it's really tiny compared to the Planck length. And roughly the reason that's happening is it's the trade-off between the multi-way causal graph and the ordinary causal graph. And that the fact that what sort of matters is the multi-way causal graph is what's making things be much, much smaller than the Planck length. So that means the elementary time is at 10 to the minus 101 seconds in this estimate. And more importantly, the elementary energy is 10 to the minus 30 electron volts. In the case of the Planck energy, the elementary energy in the Planck sort of way of estimating things is actually 10 to the 19 GeV, which corresponds to sort of the energy of a lightning bolt. Doesn't seem like something very small in the universe. When you set this up in this model, the elementary energy is 10 to the minus 30 electron volts. So that means how many elementary lengths are there across the universe? About 10 to the 120. How many elements are there in the spatial hypergraph? About 10 to the 350. So these are big numbers. How many updates has the universe done so far? 10 to the 119. How many individual updating events? If you take account of all the different quantum degrees of freedom, about 10 to the 500. So these are big numbers. And when one's worrying about the limit of something, is one going to get exactly this? Is one going to get exactly continuous space? Well, by the time it's 10 to the 500 events, 10 to the 500 is a very, very big number. And that means that to a very, very, very good approximation, you get continuous space. I might say, by the way, that in the way these models are set up, it is possible that the numbers are even much, much bigger than that. It's possible that there's sort of a continuous doubling of a continuous sort of increase in the number of elements in space that even goes beyond this. But with these estimates, we can get things like the radius of an electron. So according to current physics, the electron is of zero radius. The intrinsic radius of an electron is zero. Quantum effects produce an effective radius, but the intrinsic radius of an electron is zero. Experimentally, we know that the radius of an electron must be smaller than 10 to the minus 22 meters. In this theory, in this particular estimate, we're saying that it's 10 to the minus 81 meters across, very small. That means, though, 10 to the minus 81 meters is actually quite big compared to the true elementary length of 10 to the minus 93 meters. And that means an electron is a big fluffy thing with like 10 to the 35 elements in it. And that's why when I talked about particles much lighter than the electron, that's why we suspect that those exist, because there will be stable structures in the network that are much smaller than something like this. Okay, so one of the consequences of all this is that we can estimate the maximum entanglement speed. And the maximum entanglement speed corresponds to about, we're calling it zeta, that's our analog of c, the speed of light, is zeta, the maximum speed in branchial space. And we can estimate that, and it's a bit big in this estimate, it's about 10 to the 5 solar masses per second. I might say that in branchial space, in a first approximation, whereas distances in physical space relative to times are measured by the speed of light, distances in branchial space are roughly measured by Planck's constant h bar. But when you deal with all this multi-way stuff and so on, you find out that what really matters is this maximum entanglement rate, zeta. And as I say, the maximum entanglement rate is in this estimate pretty big, about 10 to the 5 solar masses per second. So we, at our scale, don't usually encounter things that are like 10 to the 5 solar masses per second. But one can imagine that if, for example, there was a merger of black holes at the center of galaxies, that would correspond to those kinds of masses doing things in matters of a second. And then one would expect that this maximum entanglement speed would have a direct effect on what happens in that situation, and will produce different physical effects. And I might mention that there are other physical consequences of what we're talking about. So, for example, one that we were looking at just recently is what we can call frame dragging in photons that are in orbit around black holes. And that we would expect that as a result of the entanglement horizon, that correlations between such photons will be different from what you would expect otherwise. There are other kinds of predictions one can make. So another one that's really bizarre is one of the things we know about the universe is that on a very large scale, it has the cosmic microwave background gives us a sort of a map of what the very early universe, well, at least 100,000 years after the beginning of the universe, looked like in terms of where there was mass and where there wasn't mass. And presumably that mass eventually seeded the galaxies that we have in our current universe. The question is, what made those initial density perturbations? Well, 100,000 years after the beginning of the universe is an awful lot of updates in our spatial hypergraph. So we don't really know that we can deduce anything based on sort of early updates in the spatial hypergraph. But it's at least fun to think about the possibility that, for example, sort of breaking of symmetry associated with the very first few updates in the spatial hypergraph might actually have an effect on what we see in the cosmic microwave background. And I think it's more science fiction than fact, I think, because I don't think it's actually going to work this way. But we might imagine that density perturbation is essentially a shadow of the very first few updates in the spatial hypergraph at the very beginning of the universe. And so, in effect, that the rule for the universe is kind of painted extremely large on the whole universe. I don't think it's really going to work that way, but something like that might be true. So we're back. Let me go back here. Where is it? We don't have a visual summary in the navigation. Okay, so I've given you a little bit of a tour of sort of how things work in this model of physics, from the underlying rule to all these different possible updates, the updates making the spatial hypergraph whose limit corresponds to space, the way that the different updates have certain causal relationships, and the way those causal relationships define space-time, and the way the different kind of foliations of space-time correspond to the reference frames of special relativity and so on. And then the way that this sort of multi-way graph of possible rewriting orders defines the possible, the different possibilities in quantum mechanics, and then how this branchial graph of entanglements between quantum states arises, and how that lets one do the analog of relativity in sort of quantum, in the space of quantum states. So I wanted to just mention, so what else can we say? I think this is, I'm really surprised at how far we've been able to get. As I said, I thought, among other things, ultimately the underlying rule has lots of computational irreducibility associated with it. But there's this layer of reducibility that we've discovered that essentially gives us current physics. And one thing that should make that not so surprising is that we, as observers of the universe, succeed in making a coherent picture of what's happening in the universe. If we were immediately thrust into computational irreducibility, that would be very hard to do. We wouldn't be able to really say much at all about what was going on in the universe. So in retrospect, it's not surprising that there's a layer of computational reducibility, which is essentially what we're keying into when we are sort of perceiving the universe and imagining and being able to make sense of what's going on in it. Okay, so I'm going to mention one more thing that is a little bit of a philosophically complicated thing, and which we've worked out less well than we've worked out the rest of what I've been talking about. And it's the following question. So let's imagine that we finally say, great, we've managed to find the rule for the universe. Okay? What, the question is, in a sense, why is it that rule and why not another? Right? What did we, isn't it weird that we got this rule and not another one? For example, if it's a simple rule, we're in a very strange scientific position, because if we look at the infinity of all possible rules, most of them won't be simple. So to say our universe got a simple rule is to say we're very special in our universe. Ever since Copernicus, basically, there's been kind of a view in science that we're not special. Our Earth isn't at the center of the universe, and so on. So how come our universe got to be one of the simple universes? How come it's that one and not another one? And I've been wondering about that for a long time. And the really strange thing is that I think we actually have a resolution of that question. And it's something that is, here's how it works. So I've talked about how each, at every step you can apply different, you can apply a particular rule to all these different, to make all these different possible updates. Same rule, but there are different ways that rule can be applied in the spatial hypergraph. Okay, so let's go really wild, and let's say we don't just have one rule, we have all possible rules. And we say, not only do we get to apply a particular rule in all possible ways, we also get to apply all possible rules. That gives us a sort of ultra multi-way system, a multi-way system where the branching is not just for different ways to apply a particular rule, but different rules we might apply, okay? So we've got this giant ultra multi-way system. So it turns out that it's basically inevitable that in that giant ultra multi-way system that we have causal invariance. And that means that there is a certain, that when we look at the consequences, when we look at certain kinds of consequences of this sort of rule of the set of all possible rules, that will actually end up finding out that we get definite answers for things that are guaranteed by causal invariance. And then what happens is that we can define foliations of this rule space, basically. And in fact, I should say causal invariance in rule space implies a certain rule space relativity. And we can define different foliations of rule space of this ruleal multi-way system. And what do those correspond to? We said that, for example, different foliations in space-time correspond in the space-time causal graph correspond to different states of motion, different foliations in the multi-way graph, in the ordinary multi-way graph, correspond to different choices of quantum measurement sequences. Well, the foliations in rulal space correspond to essentially different forms of description of the universe. It's getting quite abstract. Let me try and make a comment about this. So, when we say we are trying to find the theory for the universe, what do we actually mean? What we mean in the end is that we are trying to find a way to describe how a universe works in a manner that us humans can understand. If we just say, what does the universe do? Well, we can look at the universe and see what the universe does. But to say we want a theory for fundamental physics is to say we want something that we as humans can hold in our hands and sort of understand and find out that it does what the universe does. Now, it turns out that I don't think we humans get to do that. I think it's too far away from what our brains are set up to do. But we have a good intermediary, and the good intermediary is computers and computation. And I think what we're seeing when we are imagining a fundamental theory for physics is we're seeing this kind of three-way situation, where on the one hand, we've got humans trying to understand things. On another hand, we've got the universe just doing the physics that it does. And on the third hand, I suppose we're dealing with aliens here. We have kind of this computational, this medium of computation that's a way to sort of, that's a place where this process can occur. And so I've spent a lot of my life as a language designer, designing computational languages. To me, this is sort of a language design problem. Can we design a language that can bridge between these three things, humans, computation, and the universe? Can we design a language that will allow us to describe, to make a description across those three different things? And essentially what's happening when we look at foliations of rulal space is we're looking at different possible languages. Each foliation corresponds to a different description language for the universe. And what this is effectively saying then is that in this kind of ultra multi-way system, we're saying that these different foliations correspond to different ways of describing the universe. Any particular foliation has a particular rule associated with it that will be the rule that we use that works with that description language. But another foliation will need a different rule with a different description language. That will be the one that it picks as its way to describe the universe. So one of the consequences this has is that, so we humans have a particular way we choose to describe things. We have a particular set of senses, we've developed a certain mathematics, et cetera, et cetera, et cetera. So we're kind of stuck in one particular foliation. It's not the only foliation. And we can imagine, I've often, I've talked about extraterrestrials and things like that, and I've often said, but at least they'll have the same physics that we do. But then I realized it isn't true, because they can effectively be operating in a different foliation. It's the same underlying sort of universe, but it's a different foliation, a different description language. And that different description language can be not just a little bit different, it can be utterly, bizarrely, incoherently different. So that the things that we identify as features of the physical world are just sort of thrown into dust in some other foliation, which will have a completely different kind of way of looking at the universe. So in the end, I think that the answer to why this rule and not another is, well, actually, it's all just on us. It's because we exist in this particular foliation. We explore this particular foliation of this kind of ultra multi-way system. And that's sort of the experience that we have of the universe. And that's when we say we're going to find the fundamental theory of physics, it's the one that succeeds in making this three-way connection between us as humans, computation, and the actual universe. And that's kind of the goal here. So the thing we're trying to do then is so I've sort of given you a sketch of what we know now. The problem is, can we finish this? And can we here? Let me go back to if I can figure this out. There we go. Okay. So that's the story, and that's kind of as far as we've got. A lot more technical detail. We're very happy to talk about. It's all accessible on the website. We've also made, as I mentioned, all the tools that we've been using for this investigation available. So if you go into, for example, my technical introduction, and you click on any picture there, you'll get the Wolfram language code. You can just run it in a notebook, and you should get the same picture that I got. Might take some pictures take a bunch of computer time, others do not. But we're hoping that this is sort of a foundation on which we can go and try and actually find the rule for the universe, so to speak. And we can try to understand how all of this connects to the things that are already understood in physics. I mean, I might say that, pick some idea like string theory or like twistor theory or like causal dynamical triangulations or like topos theory or a bunch of other names of mathematical theories which have been developed in physics. I thought, gosh, these are not going to be relevant to the way that we're thinking about doing physics. But I was wrong. It seems that lots and lots of these theories are all talking about kind of limits and mathematical analogs of what we're doing. And I think that what we learn from those theories is going to be sort of super relevant to what's being done here. And I think that's one of the sort of early efforts, is to try and make all these connections between what we've figured out and what people have figured out with a variety of mathematical formalisms in these different kinds of theories. I might also say that from the point of view of mathematics, this is a very rich hunting ground, because we've basically, as is unfortunately very typical of physicists, we've kind of hacked our way through a lot of fine details of the mathematics to figure out how we can get to answers. And when you're dealing with limits where the parameter is 10 to the 500, there's a lot of hacking that's okay, because that's a very big number. But there's a lot of issues about what really is the multi-way causal graph. Is it really an analog of twistor space? Is it, what is the continuum limit of each of these things? What kind of mathematical structure is it? There are a lot of very interesting questions there. But anyway, so this is kind of introduction to what we're trying to do, and we're planning to live stream a bunch of the working sessions that we have about this. I would say that in the doing of this project, which we really started in earnest in about October, November of last year, it's been a remarkably quick project. In the doing of this project, we started at some point when it looked like it was actually going to work. We said, gosh, we're having really interesting conversations, let's record them. So we actually have 430 hours of working sessions that we've recorded, and we'll be putting those online soon. There's also about, how many was it? It's about 1,200 working notebooks that are sort of the scratch paper, so to speak, of this project, actually stretching back to 1994 when I really started working on this. And we just put all of those online today. And they should all be. The amazing thing is Wolfram language has been nice and compatible, so you can actually run the code even from 1994. So I guess that's pretty much all I had to say for now. And I'm happy to try and answer questions. I think today we'll probably take mostly more general kinds of questions, and people who are going to ask really technical questions, probably tomorrow is going to be a better time. And I think Jonathan Gorard is going to help tomorrow and maybe also today if people ask questions that I don't know the answer to. So let's see. So I can turn over to questions here if people have them. So there's a question here that came a little while ago. What is the significance of Planck units in this model? I think I kind of answered that. The Planck units set the overall scale, but there's an additional quantity that we're calling capital Psi. It's my favorite obscure Greek letter that essentially represents the parallelism of multi-way space. And that gives results that are numerically very different. Numerically very different from Planck units. Okay, there's a question here. Do you think this methodology can help us study the emergence of life? You know, we're very far below things like living systems when we're studying the things that are length scales of order 10 to the minus 90 meters and so on. We're really deep down in the sort of the micro machine code of physics. So there's a pretty long way from that to living systems. Having said that, the mathematical structures that have emerged in this model of physics turn out to be, as is often the case, if you have a sufficiently simple model, it's going to be applicable to lots of things. And I actually think it is going to be applicable to a bunch of questions having nothing to do with its application in physics. Just the mathematical structures that we've built, I think, are going to wind up being applicable in a lot of other places. And I think one of the places is actually possibly to a theory of evolution. I think that Rullial space relativity thing that I was talking about might actually have quite a lot to do with that. When you look at these different possible rules, that's a bit like looking at the different possible genomes that can exist. And so there may be a essentially mathematical, not structural, but just mathematical analogy between what we're seeing in physics and what we're seeing as a sort of a global theory of evolution. That's one thing. I mean, even more bizarrely, we were looking as part of kind of helping with pandemic issues, we were looking at digital contact tracing, and we realized that the reconstruction of essentially, if you know just the whose phone interacted with whose phone, that kind of gives you elements in a causal graph. And the reconstruction of space-time, which is kind of who was where when, from the causal graph of whose phone interacted with whose phone, is bizarrely similar, again, to the mathematics of what happens in this theory of physics. So I think that we're going to see a bunch of applications of the structural theory here, in addition to applications to actual fundamental physics itself. And I might mention also that what we're doing here is essentially a big story of parallel computing. I mean, essentially what's happening is that in the operation of the universe, so to speak, we're saying there's a vastly parallel computation going on. In fact, one of the things that probably held me up from doing this project for a while was I just couldn't believe that the universe was such a profligate waster of computation as it seems it actually is, with all of these different paths being followed and so on. But that following of all those different paths is really a story that's like parallel computation. And in fact, this notion of causal invariance, these ideas of foliation and so on, these I think are potentially very applicable to approaches to parallel computation. And I think there will be a very interesting interplay between what one learns. I mean, the causal graph is a partially ordered set, and what one is essentially doing, it's like the universe is doing a breadth-first search and respecting this partial ordering of the partially ordered set. And you can think of it in a very computational way like that. I mean, in a rather bizarre sense, the universe is like evaluating an expression. And the whole operation, the whole history of the universe is the evaluation of an expression. If you think about it in terms of lambda expressions, there are the free variables of lambdas. And essentially everything in our universe is a bunch of escaped free variables from lambdas in this picture. Okay, let's keep going here. How long does this project spend? I'm not sure quite what that word means there. Will the work be published after peer reviewing? Well, yeah, I mean, we're just putting this out today, and it'll my giant 450-page document will I hope lots of people read it. I hope lots of peer reviewers read it, and then it will appear. Jonathan's papers, as I say, are much more suitable for equation-first readers, and they will go through that same process. But this is it's a fairly complicated conceptual structure that we've built here, and it might take a little while to get well absorbed. Okay, what is a node and what is a line here? So what we're thinking about is, tend to call them elements and relations. The nodes are just abstract elements. The only thing we know about them is that they exist and that they are distinct from each other. Those are the only things we know about them. We can call them 1, 2, 3. We can call them X, Y, Z. We can plot them as points in a picture, do all kinds of things. But all we really know about them is that they are distinct things that exist, okay? The lines are relations. They're saying these elements are somehow related. And a hyperedge, like a ternary hyperedge, would be a relation between 3 of those elements. And the way this model is set up in detail, the order of those elements matters in the relations. Probably doesn't need to work that way, but that's the way we're doing it. It's very general. So that's what it is. It's just elements and relations. Now we can represent the elements and relations. If the relations are just binary relations, that's what happens in a graph, where there are nodes in a graph, and the nodes in the graph are connected by edges, and there are a node at each end of the edge. That's like a binary relation. That's how we build up the graph. But as far as we're concerned, they're just elements and relations. They don't have that. That's what everything is made of, but it isn't really a thing that we can talk about beyond just saying it's these elements and relations. You have a path forward for replicating the laws of thermodynamics. Yeah, actually, I think I figured out the laws of thermodynamics in the 1990s. Here's how it works. So the main thing that's mysterious, so the second law of thermodynamics is the big one to worry about. It's the law of entropy increase. It's the law that says typically what starts as very orderly, like motion of molecules, eventually turns into very disorderly motion of molecules that we call heat. You start off from some very structured, ordered thing, molecules bounce around, the molecules eventually arrange themselves in a sort of way that seems completely random. So people had for a long time, so back in the 1870s, I think, Boltzmann proved this thing called the H theorem that says you can, based on looking at microscopic collisions of molecules, you can show that entropy increases. The problem with that was it also showed that entropy decreases, because the way that we believe microscopic laws work is, for all practical purposes, for what matters for these, the laws are reversible, in the sense that any collision that can happen forwards in time can also happen backwards in time. Small footnote to that, but it's not relevant for the derivation of thermodynamics. Okay, so there's microscopic reversibility, but macroscopically, once stuff is turned into heat, it never goes back from heat spontaneously. Once you've got that kind of randomness, you never spontaneously get order again. How can that work? Well, actually, it's and it was really quite unclear how that worked. I think in the end, let me see if I can pull up something to show here. Hold on one second. If I can work this properly. What to do here? That's odd. I am not seeing what I would expect to see in my thing here. Well, maybe maybe I go there. Okay. All right. Show you something about this. This is my big book. There's a section on irreversibility and the second law of thermodynamics. And the main thing to understand is that you can have even a reversible system, and what happens is, at some point it may have a simple B, maybe in a simple state. But just as a result of kind of the computational irreducibility of the evolution, the thing will effectively encrypt that initial state into something that looks, for all practical purposes, random. So the origin of the second law is essentially that as observers with bounded computational capability, we see things going from lower entropy, more ordered states, to higher entropy, disordered states. So essentially the second law of thermodynamics is a consequence of the computational boundedness of observers in the physical world. And that's how it works, I think. And for purposes in that way of setting things up, that's important in this theory of physics because it's what allows us to take these continuum limits to get ordinary space-time and things like that. But a quite separate thing is that I think that the origin of the second law is essentially computational irreducibility that is leading to essentially the encryption of initial conditions for purposes of computationally bounded observers. Let's see here. Okay, question about, can you talk more about the relationship between physical particles, virtual particles, and space itself? So I think what we're really, when we're talking about particles, let me show you another example, which I can also find in the NKS book, I think. Let's see where they are. Here's a good example. Yeah. So this is that Rule 110 cellular automaton that I was showing you. And this is just an analogy. In the case of spatial hypergraphs, it's more complicated, but here we get to sort of just lay the particles out. We already know how to lay the particles out in space-time. So here are some particles that are propagating around. And this is, these are particle collisions here. These are two particles colliding, making another particle. So a typical, we can sort of catalog the particles. Here's a bunch of particles that we can catalog. And when those particles propagate for an infinite time, that's like a real particle, like an electron in the language of particle physics, and on the mass shell, the on-shell particle that has a in physics, p squared equals m squared, the form momentum squared equal the mass squared, something where the particle can propagate without making use of kind of quantum mechanics to exist. Now, in quantum field theory, there's this notion of virtual particles, particles that exist only for a short time, that sort of the uncertainty principle for particles makes that possible. And virtual particles rely on quantum mechanics to exist. And virtual particles are, in this, we don't know all the details of how that works in our models. But roughly, what's going to be happening is that those are particles that don't propagate forever in the spatial hypergraph. And not only that, they also are particles that have sort of an entanglement in the branchial direction. And so they're virtual particles that exist as things that are not sort of completely defined in, they don't have an absolutely definite structure. They have a structure that sort of extends in branchial space and can last only a certain amount of time in physical space and in space-time. And that's sort of the rough picture of how virtual particles work. But we have more to figure out there. In fact, one of the first live streams we'll probably do is probably talking about quantum spin and talking about, that's sort of one of the pieces of what we need to understand how particles work. We'll talk about a thing called the spin statistics theorem. We don't yet know how to derive it. That's why we're going to try and figure it out. And that will be related to a bunch of these questions about how particles work. And so the question of the relation to space is these are just like, you can see this sort of background of pattern here. That's sort of the space in this very simple cellular automaton. And the particles are just following exactly the same rules as the background space, but they have this localized form. And it's the same kind of thing we think in the spatial hypergraph, but the background space is something more random. Essentially what these particles will be is a sort of topologically stable structure in this background space. So just like the little vortices in water that you can see that have a certain stability to them, not affected by even, for example, some turbulence in the water. So similarly here, there will be some kind of topological structure, although it isn't actually topology in the ordinary sense of topology, because we don't have certain data. We only have this connectivity data. We don't have more data about faces and things that you need to form ordinary topology. But it's something analogous to topology. Okay. Oh, I might mention another thing, which is you might ask the question, all these particles running around in space, how important is that to space? Well, I think that all of the real particles, that is, the virtual particles are a different story, but all the real particles in the universe might represent 1 part in 10 to the 120 of what's actually happening in the spatial hypergraph. So in other words, everything we know about particles, the vast majority, it's a tiny little piece of fluff on top of all of this activity, which is basically maintaining the structure of space. So, 10 to the 120, things maintaining the structure of space relative to one thing doing something with a particle. So that kind of gives you a sense. Most of the activity of the universe in this kind of setup and with this estimate of parameters is involved in the maintenance of space. And the existence of particles is just a small little twiddle on top of that. Okay, let's see. Okay, if we find the model for the universe and run the code, would it be computationally equivalent or actually equivalent to something like the Big Bang? Yes, absolutely. If we get sort of a final rule and we know its final initial conditions, by the way, you don't really have to distinguish between rules and initial conditions. You can always build the initial conditions as part of the rule. If we have that and we just run it and we run this giant multi-way graph, according to this theory, we will get everything in our universe. And that's what we get to have. And sort of the expansion of the universe is then associated with the expansion of this spatial hypergraph and so on. Okay, question from Justin here. What predictions have you made that you think would be easiest to verify empirically? So the first thing is, in a sense, theoretical verification. What do I mean by that? Well, there are emerging studies of things like black holes and so on that have made various inferences that are non-trivial inferences from existing physical theories. The fact that we can directly get to those inferences from this theory is significant. Now, anything to do with black holes is going to be somewhat theoretical. We know from gravitational wave detection that we know some features of black holes, but by the time we're talking about sort of quantum effects around black holes, that's theoretical, but already there are theoretical predictions that can be verified in the context of the theories that have been being developed in the last few decades around those kinds of things. So that's first type of thing. The second type of thing is being able to is kind of things like these oligons, these very light particles. We don't know exactly what their mass will be, but the strong suggestion from these models is very light particles are very likely to exist. Similarly, some of these things about the early universe, similarly, this maximum entanglement speed, we just don't know the numerical value. Is it exactly 10 to the 5 solar masses per second, or is it 10 to the 4 solar masses per second, or 10 to the 6 solar masses per second? We don't know exactly. And to really know that for sure, we kind of have to find the actual rule, but we can already, there's a suggestion of things to look for, even though we can't nail down the actual parameter. As I mentioned, things like these correlations in photons orbiting black holes, things like that. My guess is there are also things to be looked at in quantum computing. This theory has definite implications for quantum computing. It has more theoretical implications than about what's in principle possible in quantum computing. Causal invariance implies certain limits on what's possible in quantum computing. And this maximum entanglement speed does also. But those things may be far away from what's experimentally accessible, or it may be possible to very cleverly arrange things in quantum computing so that you can actually see some of these effects like maximum entanglement speed. I'm not sure yet. I think that's going to be a bunch of hard work figuring out the details of what those predictions might look like. And once, if we can find a definite rule, then it's really going to be much easier to get very definite predictions because we're going to know the exact scales for things and so on. I would say in terms of finding the rule, there are probably 5 attributes that we think the final rule has to have, among them, giving eventually 3-dimensional space, having certain properties about causal invariance and so on. We have rules, individual rules that have each of those probably 5 attributes, but we don't have a single rule that has all of those attributes. And it's a question of finding that. I mean, actually, I think I mentioned before that we have this registry. Let me show you this. We have this, this registry. Am I sharing my screen? Yes, I am. We have this registry of notable universes, and you'll see here, this was some computed properties of this particular universe. the embarrassing thing is it could be that in our registry you already have our physical universe with our description language, but we don't know that yet. But this is something we have to go explore. Okay, it's a question about the renormalization group in this framework. I think the renormalization group is alive and well in this framework. I think, how about we do that? If we want to talk more about the renormalization group, let's talk about it tomorrow in our Physicists and Mathematicians Q&A, because I think that's going to get fairly technical fairly quickly. Thoughts about Leonard Susskind's ideas around entanglement complexity. Let's see, is Jonathan online here? Maybe Jonathan would like to take that.
Yeah, I'm here. If you
go ahead.
Right.
Do you want to? You read these papers much more than I do.
Right. So it turns out that actually the geometry that's induced on branchial space, as Stephen was talking about it, seems to be remarkably similar to a lot of the geometrical ideas that Susskind has been talking about in the context of things like the ER equals EPR conjecture and stuff like that. And so one possibility is that, so effectively what happens is that different points in branchial space, their natural distance metric is expressible in terms of something like an entanglement entropy. And then things like the ER equals EPR conjecture, which is what Susskind is interested in, can then be formulated about in terms of correspondences between the multi-way evolution graph and the multi-way causal graph. But as Stephen said earlier, we should probably address this in more detail in the technical.
We'll talk about it in full technical detail tomorrow.
Right. But the short answer is yes, it's definitely related.
Okay, next question is about string theory. And the question is this related to string theory? We don't know for sure yet. I was writing my sort of technical introduction to this stuff, and I wanted to talk about the analogy with string substitution systems. And I was thinking about the title of that section being, the case of strings. And I thought, oh my gosh, this is going to confuse every physicist because they'll think I'm talking about string theory. And then I started thinking, well, actually, is there an analogy between these string substitution systems and string theory? And it kind of starts as a pun that if you make these strings longer and longer and longer, and you're kind of looking at the continuum limit of an infinite number of symbols in the strings, what is that theory? And the absolutely bizarre thing is that pun may turn into physics. It may turn out that the continuum limit of string substitution systems is string theory, or more accurately, string field theory. We don't know that for sure yet, but that's an interesting possibility, and it's something that, I hope some string theorists will get into looking at that. And looking at how the analogy between what's happening in this theory and in string theory. My guess is that string theory will end up being sort of a simplified limit of some part of this theory. That would be my guess. Don't know that for sure yet. And possibly even this limit of these string substitution systems, which actually aren't the same as spatial hypergraphs. Spatial hypergraphs are, in a sense, much cleaner and have much less intrinsic structure than strings do. They don't yet have a notion of ordering and things like that in them. But that's at least my guess right now for how that might correspond. Can this model explain weak nuclear forces? So the answer is it's certainly better. The thing that we know that the weak nuclear force is associated with the SU2 cross U1 local gauge invariance that exists in the physical world. And there's a question here so local gauge invariance is kind of like, we can think of sort of rotation invariance as things are the same when you kind of rotate the laws of physics are the same independent of which way you're rotated, so to speak. And there's a more local version of that sort of you can rotate locally and have it be the case that you can match things up in such a way that you still get the same laws of physics. There's an analogy of that in rotating in kind of an internal space that corresponds to the space of so-called gauge groups. And actually, in our models, there is, I think, we very strongly suspect that local gauge invariance can arise rather easily in our models. And essentially the way it arises is that when you're doing updates, when you're applying these updates in different, you can apply these updates in different ways at a particular place in the spatial hypergraph. And there are multiple ways of applying these updates that essentially correspond to sort of a rotation in the spatial hypergraph. And that rotation in the spatial hypergraph is like the operations in the gauge group. And when you kind of look at successions of those things, we think that the limit of the kind of equivalences between different updates, that the limit of that set of equivalences will correspond to the Lie group, continuous group that corresponds to a local gauge group. So just as the limiting of the spatial hypergraph itself is to a manifold, something like ordinary space, the guess is that the limiting of local rewrite rules around a particular point in the spatial hypergraph will end up corresponding, that the limit of those things will end up corresponding to a Lie group that will correspond to local gauge invariance in the system, and that will be what leads to the known local gauge invariance. And it's part of SU2 cross U1 is what gives you the W boson and Z boson and the weak nuclear forces. And I have to tell you, when I was a kid, the weak nuclear force was my favorite thing. And I even, when I was about 13 years old, I even wrote this book-length description of weak interactions that was all about that. So that was before gauge groups were really much of a thing. But I'm a super big enthusiast of the weak interaction in physics, and but actually we can already leverage what's been done in the standard model of particle physics to know that if we can get the standard model, we've got weak interactions. Let's see, do all generative rules produce curvature-like objects in an emergent way? So the issue is, what is curvature and what is dimension? That's really a big part of the story. So we talked about measuring dimension by looking at the growth rate of these balls in the spatial hypergraph. Curvature is, and so dimension is kind of the leading term, is the exponent of the leading term in that growth rate. Curvature is a correction to that. So for example, it's r to the d times 1 minus r squared times the Ricci scalar curvature over 6 plus d plus 6 times d plus 2 and so on. But in other words, the existence of curvature changes the rate of growth of the number of elements in these so-called geodesic balls. And so it's a complicated interplay between curvature and dimension. Once you say there's going to be finite dimension, then all the corrections to that, once you fix the dimension, the corrections correspond to curvature. Exactly what the interplay between curvature and dimension may be, there may be some slight surprises there in terms of sort of things that are mixtures of dimension and curvature, which we don't understand yet, because all the calculus we've ever built is in integer dimensional space. We don't really know what the analog of curvature is in fractional dimensional space. And that's what we have to be able to understand and to understand that interplay. Let's see, is there an equivalent graph with unordered edges to a given graph with ordered edges? Yes, there is. I talk about that in one section of my technical introduction. Actually, the stuff I was studying in the 1990s involved unordered graphs rather than these ordered hypergraph constructs. And the frustrating thing is that at the end of the day, after we do all of this work with all this very elegant system with elements and relations and so on, essentially you can get the exact same results with trivalent graphs. The only thing that's different is the enumeration of rules is different. So if you say, I want to find a simple rule that does this or that, the order in which you may enumerate those rules may be completely different for trivalent graphs as it is for these ordered hypergraphs. So there is a difference there, and I think the ordered hypergraphs are sort of a cleaner way to enumerate what's going on, but it's sort of a consequence of having models which have sort of computation universality that they all eventually end up being, in some sense, equivalent to each other. And the frustrating thing is, I was super close to figuring this out in the 1990s, but I should have pushed a bit harder to get there, but I didn't, and so this sort of languished for many years. Okay, let's see. Okay, so there's a question from Steve here on the live stream about a destructor that, so I've been talking a little bit, most of the time I've been talking about a single rule being applied at a time, or a single rule being applicable, where that rule increases the size of the hypergraph. You can absolutely also have rules that decrease the size of the hypergraph. And yes, you can have a dynamic equilibrium between rules that are increasing size of hypergraph and decreasing the size of the hypergraph. I don't know whether that's going to end up being important. I'll tell you a kind of an allegory or something. When Einstein invented the Einstein equations for general relativity in 1915, one of the things that the most simple-minded equations he wrote down predicted is that the universe expands. And he said, but of course the universe isn't expanding. We can see that, we know that. So I'm going to add this thing called the cosmological term to fix that problem that the universe would be expanding according to his equations. And he later said the cosmological term was the biggest mistake of his life, so to speak, that because it turned out another 15 years later, it turned out, well, actually the universe is expanding. Now there's a lot of discussion about how big the cosmological term really is, and we now think there might be a cosmological term, long, complicated story related to virtual particles and zero-point energy and so on. But so in general relativity, Einstein made this mistake of saying, well, the natural thing is that space expands, the universe expands, but I'm going to put this hack in there to prevent it expanding. So I'm trying to avoid making the exact same mistake. It is certainly possible to have in these rules dynamic equilibrium where you have sort of a limited rate of expansion because there's also contraction, or you can have rules that just unboundedly expand. I don't know what's actually right, and we need to look at that. But I think to say, well, we obviously need rules that decrease the size is kind of making exactly Einstein's mistake, and I don't want to do that. So could this answer the mystery of dark energy and dark matter? So I mentioned dark matter. My best guess is that these things I'm calling oligons, these very light particles, much lighter than the electron, could be related to dark matter. The main issue with oligons is the question of how hot are they? How fast are they going? Are they going slow enough that they'll be caught in the gravity wells of galaxies and things, or not? That's a question of essentially, if oligons were produced in the very early universe, how do they get to the point where they interact only so weakly that they only feel the force of gravity, they don't feel any other forces, and as a result, as the universe expands, they effectively cool down. Now, particularly if they were produced at a time before the dimensionality of space ended up being 3 and before we had kind of the inflationary period in the evolution of the universe, I think there is good reason to think that they will be very, very cold, that they'll be very low energy, and that therefore they will be caught in the gravity wells of galaxies, which means that they are reasonable candidates for dark matter. Now, their interaction with anything other than gravity would be extremely weak. And so that's a challenge in terms of detecting them. And that's one of the questions is whether one can make specific models and try and do experiments around that. Dark energy is a little bit of a different story. That has to do with acceleration in the expansion of the universe. And that I think is more to do with if it exists and if acceleration really pans out in that way, is more a story of the exact structure of this of the way the spatial hypergraph works. And effectively in the derivation, like Jonathan has a nice derivation of Einstein's equations in which essentially the cosmological constant, which is what leads to dark energy and so on, arises as a constant of integration in certain equations. And so we can't determine from our most immediate derivation what that constant of integration is. When we have more knowledge about what the underlying rule is, we should be able to determine that. And that will tell us whether this sort of spatial hypergraph, whether the structure of the spatial hypergraph can add a dark energy term to the Einstein equations. So next question is, what does this tell us about the nature of time, and is there physics to it? Well, in these models, time is essentially associated with this sort of inexorable doing of computation. So the universe progresses through all of these different rules being applied, and it is the aggregate of the progression of the application of those rules that is the passage of time. And one thing to mention is that in ordinary physics, there are several different kinds of time. There's cosmological time, the time that defines the expansion of the universe. There's kind of thermodynamic time, the time that defines the increase of entropy and the formation of heat and so on. There's perhaps psychological time for us humans perceiving what's happening in the universe. In this model, one of the nice things is that all those kinds of time are aligned, and they have to be aligned because they're all associated with this underlying computational process. Now, what happens is we know a lot about how time works in space-time and relativity and so on. What happens, as I was talking about before, is that in these models, all of that sort of structure emerges as a consequence of the sort of large-scale operation of the model. What you put into the model is time as computation. What comes out of the model is time in space-time, time as it operates in quantum mechanics, time in the ways that we're familiar with it in physics. But what time is in these models is computational. The passage of time is the operation of irreducible computation. And it's kind of a satisfying answer because it means that as time happens, something irreducible is going on. It's not like we can look at our universe and just say, oh, you don't need to run the universe. You don't need to exist for all these billions of years. We can just jump to the end and the answer is 42 or something. What this is saying is, in this model, we're explaining, no, actually, you can't do that. There's irreducible computation involved in the progression of the universe. That's what time is this irreducible progression of computation. And in a sense, that irreducible progression of computation really means something. It can't be done any way than to just actually run the universe and see what it does. We can't kind of jump ahead and immediately say, this is what the outcome is going to be. How confident are we that we'll find the rule? It's a good question. You know, last fall when we restarted doing this project, I didn't think we would get anything like as far as we've got. I thought that we would be slammed into computational irreducibility almost immediately, that we will be looking at, maybe we can get the first 10 to the minus 100 seconds in the evolution of the universe, but we'll not know whether it really connects to the universe as it exists today. It's worked a lot better than I expected because there's this layer of computational reusability that we've discovered in these models. Now, searching for the rule that corresponds to our description language and so on, I don't know how hard that's going to be. I really don't know. And I don't know whether, I don't know whether we're going to find it this month, this year, this century. It is not easy to predict that because we just don't know whether, essentially what the question is, how good a description language is what I've been telling you today? How close is this to aligning between us humans, the physical universe, and computation as we know it? How successful have we been at aligning those things? If we're successful enough, the rule is going to turn out to be something very simple expressed in that language. And we just don't know how successful we are at doing that. And so we just can't tell how hard it's going to be to find the rule. I mean, we're going to be doing all kinds of searches for it. Hopefully other people will as well. It's not trivial to set up criteria. One of the things that happens in searching the sort of computational universe of possible rules, my little mantra is the computational animals are always smarter than you are. Anytime you set a trap for them, anytime you say, I'm going to use this criterion to decide which ones are interesting, you'll find ones that somehow manage to squiggle around that trap. They do things that you absolutely didn't expect. And so it's a little bit difficult doing these systematic searches, but we'll do a bunch of these, and hopefully other people will help in doing that, and that will help in homing things down, and then we'll have to do a bunch of thinking about it. Let's see, can we talk about emergent effective differential geometry from fundamental computational rules? Absolutely. The differential geometry that emerges from that's exactly what we're doing. We're saying when there is a finite dimensional space that emerges, it has certain properties that have certain differential geometric features that happen to correspond to Einstein's equations. When you happen to end up with something whose limit is interdimensional space. You can go to town with traditional differential geometry. You can define Riemann tensors. You can talk about Christoffel symbols. You can look at equations of geodesic deviation. All these things. They all just work. They are more elaborate and less well defined in fractional dimensional spaces. That's kind of a math thing that still needs to be figured out. Let's see, a standard sci-fi question. Can you go faster than light? Is time travel possible? Okay. The can you go faster than light? Complicated, because in branchial space, you're reaching, that's a slightly complicated thing. You can have entanglement like you do in quantum mechanics, but the light cone is, and depending on how wild the structure of space-time is, you can have wild wormholes and things like this, but they'll work in pretty much the same way as they do in general relativity, I think. That's the story on faster than light travel, is it's kind of going to be the same as general relativity. A story on time travel, closed time-like curves, is you can have rules that give closed time-like curves in the multi-way graph, for example, but those rules do not admit the possibility of foliations that are kind of consistent time foliations. So again, closed time-like curves end up being like a consistency condition between different parts of the system, and they have sort of trouble in terms of, well, they have trouble for causal invariance. They have, essentially causal invariance says you can't have closed time-like curves. So you don't get, but time travel is a messy concept anyway. The basic answer is you can't have it in these kinds of models. Antimatter problem. So one question about the universe is there's matter and there's antimatter. By the way, we don't yet know in our model how antimatter works. To every particle, you can apply to every particle this operation of charge conjugation that goes from a particle like an electron to its antiparticle, a positron. And there's a question of how that will work in these models. We don't know that for sure. The first thing we expect we would get is a thing called the CPT theorem, which says that if you do charge conjugation, parity, that's space inversion, and time reversal, that the result of all those three things is guaranteed to, in traditional physics, Lorentz invariance, relativistic invariance, guarantees that CPT invariance is an invariance of any theory. We haven't shown that yet in our theory, but I don't expect it to be that difficult to show that. And that will at least give us some hint about how antiparticles work and how one gets, actually, as I think about it, I have an idea for how that might work, which I hadn't thought about yet. See, we've been, in the last few weeks, as we've been sort of preparing this for, to be able to present things on the website and so on, we've had kind of a no science policy, because we know that if we start doing more science, it will be a never-ending process to get to the end. It actually reminds me of Zeno's paradox, and I have to mention something I forgot to mention when I was talking about it. I mentioned time dilation in relativity, relativistic time dilation. It turns out there's a similar phenomenon in quantum mechanics. It's called the quantum Zeno effect, that basically says if you measure too often, you won't see things changing. So essentially, time is dilated if you make too many measurements. And in our theory, that's very beautifully comes out. It basically says as you move in branchial space, that motion in branchial space gives you a time dilation, and that is the quantum Zeno effect. But anyway, we were worried about a Zeno effect for this project, where if we do too much science, if we just keep doing the science, we'll never end the project, so to speak. So anyway, one of the things we should talk about is charge conjugation, and I just had an idea for how that might work. So, and I think but about antimatter in general, one of the mysteries of the universe is that there doesn't seem to be much antimatter in the current universe. It seems like and we might have thought that in the early universe it will be symmetrical between matter and antimatter. Actually, I worked on that problem back in 1980, trying to figure out why there's more matter than antimatter in the universe. And with came up with a definite theory about that, which we don't yet know whether it's right or wrong, because it involves some particles much heavier than things we've been able to see so far. The core phenomenon that leads to the possibility of matter compared to antimatter is violation of CP invariance. So the universe seems to be invariant with respect to rotations, for example. But if you do a space inversion, if you just negate all the coordinates, so-called parity transformation, the universe is not invariant under that. The weak interactions, for example, well, actually the most obvious thing is neutrinos are, every neutrino is almost exactly left-handed in the sense that its direction of motion and its spin is always arranged in a kind of left-handed way with respect to its direction of motion. And that means that space inversion, the universe is not symmetric under space inversion. The universe is also, so I mentioned the universe is invariant under the combination of charge conjugation, parity, that's space inversion, and time reversal. It seems to be invariant under that. But individually, it's not invariant under any of those. And it's also not invariant under CP, charge conjugation, and parity, or equivalently under time reversal. That inequivalence is, at least in the theory that I talked about around 1980, that is what leads to an excess of matter over antimatter when you combine it with the expansion of the universe. But we don't know how that's going to work in our models. And for example, there's a small amount of CP violation that is observed in particle physics. Being able to reproduce that in our models will be really cool. Don't yet know for sure how to do that. We may or may not have to actually start constructing things that represent particles like quarks and so on to be able to get that, or it may be something more generic. I kind of have a slight suspicion it might be more generic, which makes it possible to kind of figure it out without knowing the ultimate rule. Let's see. Is the model consistent with the Everettian multi-worlds theory? How about we send that one to Jonathan here? Jonathan, do you want to take that?
Yeah, sure. Okay. So the answer is it essentially is. So this whole notion of multi-way evolution, the way we've constructed it and its connection that we conjecture it has with quantum mechanics, is very reminiscent of the many worlds interpretation of quantum mechanics. So the simplest version of the Everettian interpretation, where you have non-interacting branches of quantum evolution, that effectively corresponds to the special case in which you have just a multi-way evolution graph where everything is branching and you get no convergence between states. In the more sophisticated kind of Deutschian version of the interpretation, where you get interaction between parallel branches of evolution history, that corresponds to our notion of kind of multi-way merging, and this notion that Stephen was talking about earlier of walling off states within sort of event horizons of quantum observation frames and things. There's more detail we can give, but we should probably save that for tomorrow.
Okay, question from David here. Are we saying that the universe is deterministic? The answer to that is simple. The answer is yes. However, it's a little bit more nuanced, because we're saying that there is this multi-way graph that has all of these different evolution histories, but we as observers of that graph are basically slicing across different ones of these histories. But the ultimate complete multi-way graph is absolutely deterministic. Our perception of it may not seem deterministic, but the actual progress of all those possible branches is completely deterministic. If you ask questions like, okay, what does that mean for free will? Well, that's all about computational irreducibility. Computational irreducibility is what gives us an impression of free will, because even though everything is determined, you can't know what's going to happen effectively more efficiently than just running it by running the computation. So you can't know, it's not like, the 1950s style robot science fiction thing where like the thing operates according to logical rules and therefore you can predict what it's going to do. It doesn't work that way. Because of computational irreducibility, one is sort of stuck having to just follow the progress of time to know what's going to happen. How do you measure if the rules one has are successful? That's a good question, and that depends on this whole computational irreducibility versus computational reducibility question. In other words, the The ultimate question is, do we reproduce the parameters we know in the universe? Do we reproduce that there are 3 dimensions of space? Do we reproduce that the muon electron mass ratio is 206? Do we reproduce that neutrinos are primarily left-handed? All those kinds of things. That's what will ultimately determine whether we found the rule. But we can already say, so here's one thing. If the rule is simple, then as soon as we get 3 dimensions of space and electrons and muons and tau leptons and things, I would be amazed if it wasn't actually the rule, because the distance between one simple rule and the neighboring simple rule will be huge with respect to its effect on the universe. So going from one rule to the sort of nearest neighbor rule, you'll go from 3-dimensional space to infinite exponential space to something wildly different. So as soon as you've got the basic parameters of the universe, you can be really, I think, very confident that everything else is going to fall into place. But so that's the best hope. And how difficult it will be and which parameters we will find first, I don't know. For example, I have a suspicion that the local gauge group is going to be a direct window into the underlying rule, that's going to constrain the underlying rule a lot in a way that I think that the dimension of space does not. I think the dimension of space is emergent over too large a scale in space and time to be as useful. I suspect the local gauge group will be a much better constraint, but we'll have to see. Do we see the possibility of new ways to manipulate space? Oh, that's a good question. I don't know. I mean, of course, all of these things are operating at length scales of like 10 to the minus 93 meters. That's incredibly far away from what we have right now. If you've got a pet black hole in your backyard, then there's a lot more you can do. But we don't have any pet black holes, probably for the better. The question of whether by doing some kind of quantum measurement process and by doing some iterated quantum measurement process, you could have some strange effect through this whole branchial space thing. It's conceivable. It's conceivable there might be some way to sort of teleport through space in some elaborate way by making use of some feature of branchial space. I don't know. Right now it seems far away, but I'm not sure. I mean, it's worth remembering that in particle physics, we still don't have a single sort of practical application of anything beyond the ordinary particles. There's no strange particles, for example, or charm particles, whatever. There's nothing yet that's been sort of reduced to practice. Even relativity, that's 100 years old, we're still only at the very beginning of having things where relativity really matters. In practical, in directly matters in sort of practical things we measure, use in engineering and so on. Okay, question about oligons and neutrinos. How much lighter than neutrinos will they be? Well, we don't know. We know the neutrino mass matrix. We don't know the individual rest mass of neutrinos, but we know that neutrinos mixing with other neutrinos have certain rates. I'm trying to remember the bounds on the neutrino masses right now. The point is that we've got kind of 30 orders of magnitude between the absolute minimum masses of particles, because there's another thing I should say, in standard physics right now, space and time are continuous, and energy is also continuous, and mass is also continuous. There's no quantization of mass and energy and space and time. There's quantization of angular momentum, there's quantization of all kinds of other things, but there isn't quantization of space-time, energy, momentum, and mass. In these models, those things are quantized, but the individual quantum units are really tiny. And the point is that I'm sort of guessing that you can have particles that are a small number of quantum units of mass, and those are really, really tiny. 20 or 30 orders of magnitude smaller than current bounds on neutrino masses. But that doesn't mean that there couldn't be a whole spectrum of particles that live in that space, so much lighter than neutrinos, so much lighter than all these other kinds of things. Neutrinos have very weak interactions. That's part of why they have low masses, but there may be other reasons. It's kind of complicated. It's not directly connected to that. But this possibility, which really had never occurred to me, at least, that there might be 20 orders of magnitude or 30 orders of magnitude of lighter particles, I've never really considered, and I think that's an interesting kind of thing, even when we don't know the full parameters, to start considering. Okay, good question. Next one. How is the graph stored? 10 to the 500 steps requires a fair amount of memory. Yeah, it requires all the memory in the universe. It is the universe. I mean, this is one of the kind of philosophical questions that comes up when you start saying the universe operates according to a rule. It's a kind of computational rule. People start saying, well, what's that rule running on? Where's the computer that's running this rule? Well, it doesn't work that way. The rule is just a description of how the universe works. It's like when we know that the motion of planets is governed by differential equations, we don't think that the planets have little mathematicas inside them solving those differential equations. We're merely saying the differential equations are a way of describing how the planets move. And it's the exact same thing here. We're saying these rules are a way of describing what the universe does. The universe is equivalent to performing these computations. It's not that the universe somehow is externally performing these computations. It's just the actual stuff the universe is the performance of these computations. And so that means the data structure of the universe is the universe. The computer of the universe is the universe itself. It's running itself, so to speak. And by the way, I mean, it's interesting to kind of see all these things about computation, all these ideas about computation, like trade-offs between space and time and computation. That's actually physics. The trade-off between space and time is related to relativity and light cones and things like this. The question of, I mean, by turning what one has done in a theory like this is one's conflated three things. One's conflated computation, physics, and mathematics. They're really ultimately all the same kind of thing. So, mathematics is something where you start off with sort of axioms and then you say, well, what are the deductions you can make from that? Physics has always been this empirical theory where you say, well, the world roughly works like this and this is an approximation. But this is saying that we can actually find the rule, the precise thing, like an axiom in mathematics, where just by working out the consequences of that rule, just like we work out the axioms in mathematics, we know precisely what the universe does. Of course, there's computational irreducibility, so it's irreducibly hard to actually do it. But from a conceptual point of view, this will reduce physics to mathematics. And similarly, in a sense, it's reducing physics to computation, and it's providing kind of and we can actually think about computation then. The universe is just an example of a parallel computation, and the laws of physics will also be laws that apply to these parallel computations. And so we can start talking about sort of relativistic things. And I haven't figured out yet, this is another good thing we should talk about, is the analog of time dilation for space-time trade-offs in parallel computing. But I think all of that formalism will be able to be interconverted there. Are there any implications of this in the near term for an average person? My theory is there are no average people, but anyway, here's the way I think about that. Is there going to be technology that operates on the basis of elementary lengths of 10 to the minus 93 meters? Not anytime soon. I think the main significance of this is probably a conceptual one. I mean, I would say that you can sort of draw a slight analogy to, like what Copernicus did in back in 1500 or so. People had always thought, the sun goes around the earth, all those kinds of things. There was this whole theory of, Ptolemy's theory of epicycles, all those kinds of things work just fine for predicting the motion of planets. Even today, when we, work out when an eclipse is going to happen, we're basically using the computational analog of tens of thousands of epicycles. But what Copernicus did was he showed that actually there was a mathematical theory that you could set up that didn't follow what we sort of perceive from our senses, that the Earth is stationary and the sun is moving around it, but that actually said, well, no, that's not really the case. This mathematical theory shows that you can have the sun at rest and the Earth moving around it. But the theory was kind of complicated and it had a lot of technical detail. And, you know, I don't know how many people cared about the theory, but the consequence of the theory was that the science and math can tell you things that weren't obvious from from your ordinary senses. And that started a huge progression of kind of scientific thinking that said, just work out the science. Don't, the fact that you can't figure it out by pure thought, by just pure reasoning, isn't really the important thing. Science can figure it out. Well, I think what we're seeing here is that we're sort of seeing a foundation for physics, for our understanding of the physical world, that's rooted in computation. And once we really believe in the fact that computation is what it's all about, once we really believe it's all computation kind of all the way down, that has consequences. And so, for example, one of its important consequences is the phenomenon of computational irreducibility. You simply can't get out of computational irreducibility. Once things are computational, you will have computational irreducibility. And computational irreducibility has everyday consequences. It's the thing that tells you you can't just figure out what's going to happen by just sort of pure thought. It's the thing that tells you you can't know whether a program is going to have a bug in it without running it. It's the thing that tells you when you have an algorithm for deciding what content should be in a news feed and some AI-based algorithm for that, you can't know what its consequences will be without effectively running it. It's the thing that kind of limits the effectiveness of science to make sort of global predictions. It's a way that science, it's sort of interesting that for example, in the Copernican case, that was kind of just trust the science, it's going to figure everything out. What we're saying is, when things are rooted in computation, there are inevitable limitations of science that come about just by the nature, just by the logical structure of the way that science is built from computation. And those center around computational irreducibility, and those imply certain limits on the way that we think about science. And so I think from a sort of everyday point of view, the thing I would say is it's sort of a different way of understanding the world. And, you know, from the time of Newton and Galileo and people like that, we got concepts like momentum and force and so on. And those concepts originally were concepts in physics, but we've been able to sort of apply them to our general thinking about a lot of kinds of things in the world. We talk about, you know, the momentum of some product, which isn't the physical motion of the product, presumably. It's something more conceptual. And we think about those things in a conceptual way. And I think knowing that things are rooted in computation gives us a way to think conceptually about the world with concepts like computational irreducibility, principle of computational equivalence, undecidability, those kinds of things that I think will have a general applicability to our way of thinking about the world, far beyond the specifics of the details of how the physical universe happens to work. Okay, next question was, is the universe a simulation? I think we can fairly say that question really doesn't make any sense. And let's see, Jonathan and I just worked on, this is one of these questions which always takes me a little while to unpeel philosophically. And Jonathan and I just worked on a nice succinct answer to that. Let me see if I can find that here. It's in the Q&A section on the website, and I think we might have a, okay, here we go. So okay, so actually, I guess I wrote this. Jonathan was somehow involved in this. So, I mean, the first point is, if there is a definite rule for the universe, it means everything about the universe is determined from that rule. There are no external miracles in the universe. There's just this rule that determines how the universe works. And so then to say that the universe is a simulation would be to say there is something intentional about this rule. There's something set up this rule to be the way it is. Okay, so there's a notion of some programmer programmed this rule on purpose to be this way. Okay, well, we already get into trouble trying to go take intentionality outside the domain of humans. Maybe even to animals we have trouble. But by the time we're dealing with AIs, we have a lot of trouble. And by the time we're dealing with other systems in nature, like, we might say the weather has a mind of its own. What's the weather trying to do today? Is the weather trying to make us wet? What is it trying to do? Is there a way of transferring our notion of intentionality to these other kinds of things? That's already very hard to do. So in this case, what we'd be doing is transferring intentionality to the whole universe and saying, in a sense, was something outside the universe intentionally putting in this rule? Okay, that's first problem. The second problem, that in a sense is an even worse problem, is that in a sense, this rule-space relativity idea implies that all possible rules for the universe are in some sense equivalent. The rule that is the one that we are identifying in our sort of foliation of the universe is the one that corresponds to our particular way of understanding the universe, our particular description language for the universe. And so it doesn't really make any sense to say, somebody can decide on a rule, but any possible rule would work. The rule that we kind of consider is the one that is operating, is the one that fits into the description language that we can create. So it's not something you can really insert from the outside. So I think we're really pretty unraveled in terms of being able to say the universe is a simulation. I think that really isn't a sensible thing to say, I think. I'll add one weird footnote to that. The one thing that in the end one could say about the universe, after you cut out all these different possible rules, all these different possible description languages, the one thing that shines through is the universe is a universal computer and nothing but a universal computer. So people have wondered, is the universe capable, when we have all the computers that we can construct, so far as we know, are all ultimately equivalent. We can program one computer to behave like any other computer. We can make a Turing machine be able to model any kind of, be able to emulate any kind of computer that we construct, whether it's the computer in our CPU chip or whether it's the computer that corresponds to some physical process. All of these things can be emulated. Well, we know we can do it for the things that we normally think of as computations. But the question, what this model is implying is, the one absolutely certain thing we can say about the universe is the universe is just a universal computer and nothing but. And for example, can you say, well, what could be more than a universal computer? Well, here's an example. A Turing machine, for example, it might just go along and it might go along and you might say, is the Turing machine ever going to halt? Ever, even after an infinite time? Well, to know that, it's a computationally irreducible thing. So you might have to go an infinite time to find that out. But you can imagine building a sort of super Turing machine, a hypercomputer, that would just immediately be able to answer the question. It would just say, yeah, this Turing machine you've got, after an infinite time, it will halt, or it will never halt even after an infinite time. And so a hypercomputer is something you can imagine, but the question is, can we build a hypercomputer in our physical universe? And this model says, no, you can't build a hypercomputer in our physical universe. And in fact, this kind of rule-space relativity thing implies that even if there was a hypercomputer that was sort of, that our universe, even if there were rules for our universe that were possible, that corresponded to hypercomputing, there would be essentially a cosmological event horizon that will prevent us ever communicating with those rules that correspond to hypercomputation. So there really isn't a lot of room for a programmer in this whole story. Okay, let's see. So this question about an approximation to how large the bits in the underlying rule are, we have a way of estimating that. I think it's a little bit flaky, but the estimate we have is 10 to the minus 93 meters, which is really small. Let's see. Okay, if we calculate a very fine grain, we should be able to converge to something which seems continuous. Is that a way of doing continuous computation? Well, the answer is that what we're saying here, sorry, I'm a little confused by it's on my screen here. Yeah, what we're saying here is that ultimately things are discrete, but at 10 to the minus 93 meters, that's really, really small. And so to a very high degree of approximation, we are still seeing things which appear continuous, like continuous space. This doesn't really give us any more of a way to do continuous computation than we're still doing the computation in the universe, so we still have to construct the computational elements out of things in the universe. This, I think, might give us some interesting ideas about how we could do sort of massively parallel computation, but I think that's a different kind of story. Question about why there are 4 fundamental forces. That relates to this question about local gauge invariance. The 4 fundamental forces of the standard model is about 3 of those of particle physics. 4 fundamental forces: gravity, the strong nuclear force, the weak nuclear force, and electromagnetism. Gravity has always been the odd force out in that sequence. In our models, we do explain how gravity works. The other 3 forces, we can see how those might arise. Those forces are all related to quantum mechanics. But the real test of those forces, they're known to be associated with local gauge invariance. And if we can reproduce local gauge invariance, we will reproduce the possibility of those forces. But we haven't done that yet. We have an idea of how that might work. Okay, suppose you had the rule to make useful descriptions of large-scale phenomena, would you need to run the simulation because of computational irreducibility? Ultimately, yes. To find out that I'm doing this live stream right now from the underlying rule for the universe and the initial condition for the universe, we'd have to run that rule for whatever it is, 10 to the 500 steps to get to this point. And unfortunately, computational irreducibility means we probably have to really run basically those 10 to the 500 steps. And that's something that we don't get to do in our universe. Our universe just did it, but we don't get to do it in our universe. Now, the hope is that there are pockets of computational reducibility that will allow us to make general statements without having to run all of that irreducible computation. And one of the big surprises in this project is how thick the layer of computational reducibility is that allows us to derive Einstein's equations, derive the Schrödinger equation, derive the path integral, all these kinds of things that don't seem to get enmeshed with computational irreducibility. Their detailed parameters, the detailed features of particles may very well get enmeshed in those, but these general features of physics do not get enmeshed in those things, and so we're able to derive them. And so that's kind of the how far the boundary of reducibility is, we don't know. I mean, the realization sort of after the fact is we kind of know there's somewhat thick layer of reducibility because that's why we humans can make any sense of the world. If everything in the world was immediately thrust into computational irreducibility, we wouldn't be able to make any sort of general statements about how the world works. We wouldn't think that there was sort of, that the universe worked in a coherent way. It would be all thrust into this sort of very low level computational irreducibility. Let's see, how does the observer effect fit into this theory? Well, I mean, a lot of what we're talking about is the interplay between the observer as part of the system and the system itself. The fact that when we try to analyze the system, we're analyzing it in terms of causal graphs that represent causal relationships between events. And we're analyzing it in terms of these foliations of the causal graph and so on. That's all about trying to effectively model the way that an observer who is embedded within the system interacts with the system. You may be meaning by observer effect, you may be meaning things like the uncertainty principle. Talked about that a little bit earlier, well, again, it's all related to the observer as something embedded within the system, but that's also related to the geometry of branchial space and some other kinds of things. But I'm not completely sure what's meant by that. Hey, Jonathan, do you have a better thought about that?
Okay. I may be able to add something. So when people talk about the observer effect in quantum mechanics, as you say, they're normally meaning sort of the effect that the observer can have on the outcomes of certain classes of quantum measurements. And effectively in our model, this comes down to the thing Stephen was talking about earlier about these QOFs, these quantum observation frames, where, so in the same way as in relativity, if you have different relativistic observers, they can see different orderings of space-like separated updating events. In the quantum mechanics case, where you're in the multi-way evolution graph, different quantum observers, depending on the identity of the quantum observer, you can see different branch-like orderings of measurement events, effectively, is how that works. And again, this is probably something we can address in more detail later.
Oh, good answer.
Thanks.
Okay. Let's see. Does the amount of computation in the universe increase over time as it grows in richness and complexity? Is it possible to quantify how much that is? What is the clock speed of the universe? Okay. So the answer to that is yes. The amount of computation that's happening, in a sense, does increase in time because, well, at least time as we perceive it, because the way that we are foliating time, the way that we are deciding what counts as the next moment of time, we're imagining that moments in time sort of go across the whole universe. So assuming that we use the way of measuring time that is the typical way that we think of measuring time, then the answer is that the spatial hypergraph is increasing in size as the universe evolves further, and we kind of, and it's basically certain the spatial hypergraph is increasing in size, probably related to the expansion of the universe. And that means that, in a sense, for every new time step in this kind of foliation of time, more pieces, more underlying nodes in the hypergraph, more underlying relations have to be updated to get to the next thing that we consider the next moment in time. So in that sense, yes, the amount of computation is increasing as we go through the evolution of the universe. What is the clock speed? We actually have an estimate of that. Let me just look up because I'm forgetting, which I shouldn't be doing, but let me just see here. Let me see. I should know all this immediately, but I also don't think these estimates are yet that solid. Let's see. Okay. Yeah, so the estimate for the elementary time is 10 to the minus 101 seconds. So that would be the clock speed of the universe. That is the time elapsed between two updating events on a single causal edge. Between two updating events will be 10 to the minus 101 seconds in this estimate. And that would be, in a sense, the clock speed. This question, so there is an interesting feature in rule space. There is also the notion of a maximum speed in rulal space, and that maximum speed is related, and we don't understand that well yet, is related to essentially a maximum speed of translation between different description languages. So I think what that's going to do is it's going to link algorithmic information theory, which talks about the complexity of program sizes, with features of physics. And I think just like we have the speed of light as one fundamental constant of the universe, I think we have another fundamental constant, which is the maximum entanglement speed that I'm calling zeta. I think there is another fundamental constant of nature, which is the maximum speed in rule space, which we're calling rho. And that maximum speed in rule space is essentially the maximum rate at which translations between description languages can occur. And that, as I say, is somehow related to gives a scale for program size, which is, so just as the speed of light translates from elementary time to length, the maximum entanglement speed translates from elementary time to essentially quantum units, essentially h bar. It translates to sort of quantum to distance in branchial space. So there is a translation from elementary time to distance in rule space, and that distance in rule space is somehow related to program length. And so there's a way, I think, of connecting program length, which has always been this rather abstract thing, to something sort of physical. don't yet fully understand that, but I think it's a coming attraction, so to speak. Okay, next question from Peter here. Does the theory predict how the universe ends? No, we don't know that. We strongly suspect that the universe will go on forever, that it corresponds to a computation that will not halt. There's a whole bunch of reasons to believe that in this kind of model, but we can't say that for certain. I mean, there is the possibility that this computation will eventually reach a final state where it just says, and the answer is 42 or whatever. But it seems very unlikely. That would, it's very hard to make that consistent with causal invariance. It's hard to make that consistent with things we already know are true about the universe, but it is not absolutely ruled out by this kind of model. Okay, if experiment produced a Turing oracle or a hypercomputer, would that disprove the theory? Yes, that would disprove this theory. However, good luck on connecting such a hypercomputer to anything that our senses can deal with. Because in everything we've done in science, we have tried to reduce what we observe in science to essentially symbolic representation. And a symbolic representation is a finite symbolic representation, and it is incapable of representing the kinds of raw material that you need to actually interact with a hypercomputer. So even if we had a hypercomputer sitting under our noses, we wouldn't know it because we just don't have a good way to interact with a hypercomputer because of the fact that our way of describing things and even probably thinking about things is rooted in kind of this symbolic notion of doing things. Somebody is asking, can we get a copy of the project's book signed by Jonathan, Max, and me? Sure. We were considering, as we thought about this project, and we tried to understand what things we could provide for people in this project, and how people could be involved. I have to say that swag was up there in the list, and kind of the adopt the universe kind of idea from the registry is also something that's on the list. And so we're hoping to be able to provide some of those things, but mostly we're just really keen. I mean, we see this as being a sort of a big intellectual adventure. It's kind of like, can we climb the tallest possible Mount Everest of science? We don't know if we'll get to the top, and we don't know whether it'll take a century to get to the top, but we think it'll be fun to see what happens on the climb. And we hope other people will help in that climb, but we hope also that people will find it interesting to see what's involved in getting there, and to see what in our efforts to kind of do sort of frontline science, what's actually involved in doing that. Let's see. So a question here: do the updates to the hypergraph happen in parallel? What happens in the case of collisions? Yeah, that's the whole point. There are many possible updatings that can occur, and the fact that there are those possible updatings defines this multi-way system, which is the source of quantum mechanics. And what does it mean that they operate in parallel? Well, there's a set of causal relationships where one thing has to have occurred before another can occur. That defines the causal graph. It defines a partial ordering of those kinds of update events, and it's the whole story of what possible sort of total orderings are consistent with that partial ordering, which translates into what do we consider this sort of the successive steps of time in our universe. That's kind of how the whole thing sort of works out. And it's this invariance of the ordering of what happens when things occur in parallel that corresponds to causal invariance, that implies special relativity, that implies sort of objectivity in quantum mechanics, etc. So yeah, it's a very critical thing that these things can happen in parallel, and that the quotes collisions, those collisions are precisely the sort of those lead to the entanglement, so to speak, that happen in quantum mechanics and so on. How can the nominal average guy contribute to this project? we're going to have a distributed computing mechanism where you can run some little fragment of searching for the universe on your computer. That's one nice way to contribute. I would say that we don't know what kinds of thinking are going to be needed to figure out everything that needs to be figured out here. And there's a lot of kind of both. Some aspects of this are going to be at the front lines of sort of quantum field theory, general relativity, those kinds of things. They kind of need sort of a PhD's worth of physics knowledge to really be fully engaged in them. But there's a lot that's happening at sort of the computational level where, we're operating really from the ground up. We don't know anything yet. I would say that a lot of the work that I did in New Kind of Science and so on, exploring different kinds of systems, there's a lot to do there, and there's a lot of intuition to build. I mentioned using string substitution systems as a way to get an understanding of the multi-way graph and so on. There's a lot more that can be done along those lines, and this is a very young field. So there's a lot that can be done by, without having a physics PhD. There's a lot that can be done by just doing computational experiments, trying to make conclusions from these computational experiments, trying to devise kind of general principles on the basis of those experiments. And I don't think anybody has a great advantage in doing that. I mean, I've been doing that kind of thing for 40 years now, so I kind of have developed a certain amount of intuition about it and can do these things at a certain speed. But in particular, the tools that we have in Wolfram Language, part of the reason I built Wolfram Language was to have what I needed to be able to do those explorations. So those tools are very well optimized for those kinds of explorations. And as I mentioned, the Wolfram Language functions and things for doing evolution according to these hypergraph models and so on are all, as of today, available through our function repository, and you can get them through the website and so on. And so you can explore these things. And it's really an open field. Nobody's explored these things. We've just started. We've just been picking away at the edge of it. So I think exploring kind of both these full hypergraph rewrite systems, those are just a bit complicated, but exploring these analogs and string rewriting, even in things like cellular automata, highly useful. And it's just like this, it's a really wide open field where there's just a huge amount to do. And I think my only, one of the things that's happened from my work on New Kind of Science is, I really pushed this idea that one can make models for things in the world, for just things in nature, things in social science, whatever, on the basis of programs rather than mathematical equations. And it's really a pretty neat thing that's happened in the past probably 15 years. And I'm not saying that it's all my fault, so to speak, but I think the New Kind of Science book kind of was, that was really the idea that I really pushed in that book, was this idea: use programs to make models of things rather than using mathematical equations. And after, it's basically been a 300-year run of people primarily using mathematical equations to make models of things. Last 15 years, there's been a pretty thorough transition to using programs to make models of things. And that's a pretty neat thing to see. It's kind of, to me, it's a little ironic because a bunch of people, when my book came out, said, couldn't possibly work, never going to be useful. Program's never useful for anything. And now that's basically what everybody does. So that's kind of nice. But the one area where that really hadn't made progress is in fundamental physics, where the idea of using programs to make models of things hadn't made progress is in studying fundamental physics. And I think now we kind of cracked that nut of seeing how one can use programs and computational ideas to model fundamental physics. So that's something that I'm sort of excited about here. But I think, as I say, the best contributions to be made, if you really want to get into the intellectual meat of this, is study simple programs, study what they do, either the real full hypergraph case or the simplified cases, and try and build up principles about what happens and try and find phenomena. You might find some weird kind of new singularity that corresponds to some bizarre sort of mixed quantum mechanical relativistic black hole or something. You could find that by just studying these hypergraphs and the evolution of these hypergraphs. The trick in these things is always, you see some weird phenomenon on the screen. The thing that's just maddeningly difficult is understanding what does that really mean. But there's a lot that can be done by just saying in the simple cases, just look at these cases, make a systematic study, describe what you see systematically, and that's part of the building block that can make science. And that's what a lot of science is. Just good science is about doing things systematically, being able to have a good presentation of what you find and so on. I mean, I would say that in this project, the thing that sort of happened over the sort of 40 years or so that I've been sort of picking away at things somewhat related to this, it's been sort of a gradual understanding of more and more of what the significance of things is, and a gradual realization that, you know, often it's that thing that I sort of understood, I sort of had seen, but I didn't really understand its significance. And then I progressively understand more and more of its significance. And that's typically the slow part, at least in my experience. All right, we should take a few more questions and then probably wrap this up for today. Let's see, what amount of simulation is required before enough information can be found to compare the rule to existing theories? We don't fully know the answer to that. I've said this several times here. I mean, we just don't know. We don't know. What's special about the universes in the registry of notable universes? I think we haven't finished, actually. We were rerunning the registry just last night, and I think they didn't finish running. So I think we've got about 1,000 universes. Those are really just universes that came out of various searches. They were based on various criteria. They seem to have some interest or another. They're really pretty arbitrary. I mean, that's just the universe that just does nothing or makes this very simple tree. Those don't make it for the registry. These are universes that for one reason or another, it's like, oh, that's kind of interesting. Put them in the registry. We're sort of over-generating things for the registry in the hopes that we'll capture things that will be useful examples to study. And talking about, you know, what does the average person do in this project? You know what? We haven't even looked at every page in that registry. We don't know what's on there. We don't know what, there may be a bunch of really weird and interesting phenomena there that we haven't even seen yet. So that would be a good place to start. Let's see. Does the theory explain whether a hot dog is a sandwich? You know, one of the things this theory says is there's a lot about the way we perceive things that is in the matter of how we perceive them. And so I don't think we have anything directly to say about that, other than that there are different description languages for the world, and that there's sort of equivalence between these different description languages, and it doesn't answer your question. This is somebody commenting that they like what Jonathan had to say. I do too. Jonathan has been a great contributor, as Max has also, to this project. And I hope tomorrow Jonathan will be a big part of the more technical explanations that we're giving. This question here, can we explain the principle of least action in the context of hypergraphs? The answer is basically yes. We can reproduce the path integral of quantum mechanics, from which you can derive the mechanical principle of least action. And the way that works, as I was mentioning, is it's kind of the analog of things, sort of the analog of Einstein's equations in branchial space rather than in physical space. And that's what that's what can that's what leads to this. Okay, there's a question on using the Turing completeness of the rules to do massive computations using tiny structures in the network. That's kind of how the universe is building itself for us, I think, all the time. Is it's doing I mean, one of the things that really took me a while to come to terms with is this universe is such a waster of computation. I mean, there's just unbelievable amounts of computation happening to just maintain a little tiny piece of space. And that's something very weird. Now, can we harness that computation for something that we think is useful? I think it's useful to maintain space, but can we harness the computation, in a way that's sort of purposeful to us? We don't know how to do that yet. That's obviously a very interesting thing to think about. The length scales that are involved here are really, really tiny, so that's a challenge, but there may be ways to do it. Okay, so there's a question about low entropy at the Big Bang. Yeah, I think I talked about that a little bit. What I think is happening is that the initial conditions may be very simple, but essentially what's happening is that the evolution, the irreducible computation that's happening in the evolution of the system is so encrypting those initial conditions that for us as sort of computationally limited observers, we can't decrypt that. And when we can't decrypt it, it looks random to us. So it looks like it has high entropy. And it's that phenomenon that leads to the second law of thermodynamics and the apparent increase of entropy and the low entropy of the initial, which means that we can start from this low entropy, this very simple initial condition, and wind up with this higher entropy, with the law of entropy increase and so on. Do we get comments from established physicists already? Oh yes, lots. It's been kind of interesting. We haven't had, partly because of the pandemic, we haven't been sort of communicate as much as we might. We had only one sort of fully interactive session with a group of friends of mine who are sort of established physicists. It was a lot of fun, as I would say. They were getting it, which is really good, and they were like, this is really neat. So that's good. I've been, just in the last 24, 48 hours, we've been sending out sort of preliminary versions of some of this stuff. And I'm sure while I've been on this live stream, I've had a whole bunch of other responses. You know, what's interesting here is the methodology, the underlying methodology is a bit alien. But as soon as we've gotten up to the level of sort of connecting to things like quantum field theory and general relativity, it's actually quite familiar. And as I mentioned, one of the really nice things is this correspondence to a lot of kind of theories that have emerged, particularly in the last decade or so in physics, particularly as coming out of this ADS-CFT correspondence and so on. And I think that really helps in making this connection to sort of you know, I used to be an established physicist, so the established physicist is probably the wrong description. I think I'm part of that group, although I've been kind of out of the business for a long time now. You know, what's happened, it's kind of a funny sort of time warp for me because you know, a lot of the people who've been sort of leading physicists were, you know, friends, colleagues of mine back when I was doing physics. I happen to be a bit younger than most of them because I started doing physics when I was pretty young. So it's been really strange for me because I've been following physics all these years, but I haven't been really deeply involved in it. It's kind of interesting for me to go back and look, okay, what happened to this particular thing? One of the things that has happened actually in physics is that there were many different strands of development that existed. And one of the things that has happened in sort of the established physics kind of thing is a lot of those strands have merged in different ways. So things that would be in completely different papers will now find themselves as words in the same sentence. And actually that unification, I think we can take that a lot further with this theory. But the fact that we're kind of relating to a lot of those things, I think is very helpful in making a connection to physics. You know, one of the things that so I'm really hopeful that we'll be able to leverage what people have already studied, and a lot of the sort of technical work in string theory, twistor theory, all these kinds of things will be, oh, okay, that means we can say this and this and this, in addition to what we've been able to say. And one of the things we hope to do on our live streams is have discussions with some of the leaders in those various fields, many of whom I think I would consider to be friends of mine from back in the day when I used to do physics, and be able to talk about how their theories and the mathematical development of their theories particularly relates to what we're doing here. How does this compare with defining a context-free grammar for physics? Well, okay, so these hypergraph rewriting rules are like graph rewriting rules. Typically, context-free grammars operate on strings, just sequences of things. These are like graph grammars. The theory of graph grammars is not particularly well developed, but you can think about these things as being kind of like hypergraph grammars. except that our objective is a little different from a typical grammar. In typical grammar, what you're trying to do is say, parse this English sentence, for example, or parse this piece of programming language code or something. And you're saying, break it down, make a tree out of it. And you're doing that by saying there are these rules, and I'm going to reduce the thing down to the tree that could be used to generate it. What we're doing instead is sort of running that process in reverse, and we're saying, take this starting point and sort of do all the possible treeing out of what could happen. And in some sense, what we're doing is like running a graph grammar kind of in reverse, running a hypergraph grammar kind of in reverse. And that's sort of what is really going on here. And we are the intermediate, our whole existence and the whole universe is the intermediate stages, the non-terminal nodes, effectively, in the running of that hypergraph grammar in reverse. Is it possible to write unit tests that would validate the presence of certain physics analogous features when a particular rule is run? So, gosh, how to think about that? Okay, let me try and take that in the following way. So one of the things about existing science, particularly experimental science, is the idea of doing isolated experiments. So in experimental science, the typical thing you try to do is to say, I'm going to do an experiment on this piece of this system and nothing else matters. I'm going to be able to try and isolate the effects in this particular area of the universe to just do an experiment on this. Now, that's something that has been really critical in doing experimental science. One of the features of these models is that everything is really connected together. So it's actually more difficult to be able to, as we've been working on studying these models, one of the things we've often done is say, let's idealize everything away. Let's just make a Schwarzschild black hole and nothing else. Well, it turns out you can't do that. You have to have all the other stuff that goes around it. You can't just make this isolated black hole thing without any of the rest of the universe sort of hanging around it. Or at least we don't think we can do that. So we spent a bunch of time trying to do these idealized experiments based on sort of separating out, isolating out particular effects in the universe and being able to study those separately. And that turned out to be pretty hard. In other words, sort of everything comes together in this model of the universe. So teasing out, being able to look at these limiting cases where you can sort of do a unit test and just test that particular feature without testing other features is quite difficult. And that's one of the challenges in sort of finding those ways in which you can use sort of computational reducibility to tease out those unit tests. I might say that it's a little bit of humor here that Max is a big enthusiast of unit tests. Max is probably the most software engineering of our little team here. And one of the things that I've continually given him a hard time about is that he insists in building the fundamental code that we've got that runs these models in setting up unit tests for every possible aspect and doing continuous integration of all of this code. And I've been sort of complaining that we don't even know whether certain aspects of this model are right. And so, you shouldn't be doing all these precise unit tests, but I'm really glad he's done those because it means that we know the code is really doing what we think the code is doing. But I'm just kind of amused that the unit tests of, the question of doing unit tests on the universe is sort of reminiscent of doing unit tests on the models of the universe, which we've been, Max has been a big contributor in doing in this project. Okay. So a question is, are there general methods to discover where computational reducibility is? That's a really interesting question. I do not know the answer. Machine learning kind of might accelerate what is essentially our human poking at things. And we've used machine learning. I've used machine learning a bit in analyzing some of these models and so on. But I don't have a really good answer to that. I think that's that is like the automated scientist, so to speak. Looking for computational reducibility is looking, the reducibility is the place where you can make a scientific law. So asking to sort of automate computational reducibility finding is like looking to automate the doing of science, so to speak. And we're a little bit of the ways towards that, but we don't know a really systematic way to do that. All right, well, I think we should wrap up here. Thank you all for coming. This is, I'm really excited to to launch this project. I hope people will choose to get involved. I encourage you to check out all the things on the website, start playing with the actual tools that we've provided, give us feedback. I bet there are a bunch of professional physicists on this live stream and mathematicians, so there's really, I hope, things to dig into there. As I say, tomorrow we plan to do 2 more Q&As, one for primarily more professional physicists and mathematicians, where we'll really get into the into arbitrary levels of detail. Other people might find it fun, but I don't guarantee that we'll explain everything we're talking about there. Then following that Q&A will be a Q&A about kind of the philosophy of this, of what it means to find fundamental theory of physics in this kind of way. Then we're planning to follow up on Thursday with a Q&A about computer science, where we'll talk about the kinds, both sort of this from a computer science point of view and possible implications of this for thinking about fundamentals of theory of computation and so on. Well, thank you all very much. And we'll hope to see you all on another live stream another day. Thanks. Okay, hello everyone. Those who've been following previous live streams this afternoon, this is now not my day job. This is back to studying fundamental physics. And this is a continuation of yesterday's discussion about finding black holes. I think I reset my camera here, so for whatever good that does. So we're going to be looking at we're going to be continuing our discussion of black holes, and I think I will now just go to sharing that. Hold on one second. I'm confusing myself here. Let's see how this works. Great. Okay. Okay. I'm going to just go ahead and do this. Okay, we are talking about black holes here, and we're going to follow on from yesterday. So yesterday, we had looked at, we got rather distracted in what was supposed to be just a big black hole search, and started discussing all kinds of interesting things about space tunnels and so on. But we're going to return here. We're talking about space tunnels and such like, but we're going to return to the pure discussion of black holes. And so here we were looking at, so I want to make another version of this, and this is going to be black holes 03 for today. I'll make this bigger. Right, so the basic idea is we have a causal graph. Okay, so Jonathan has provided new code here. So should I just evaluate this code? Or do I need to evaluate the previous code first?
No. In fact, it probably makes, to prevent us getting confused, it might make more sense just to evaluate this new stuff.
Okay, all right, okay. So let's just go ahead and evaluate these things over here where people can see it. Okay, causally disconnected regions. So this is, you're going to explain what this is. So this is saying, highlight in this graph, this causally disconnected. So these are regions, I don't understand quite what's going on here.
Yeah, okay, so this is effectively the complement of a future light cone. So it's saying from vertex 2, which vertices cannot be reached. And so it's got a whole heuristic for determining, I mean, because obviously, this, as we were talking about yesterday, this is an undecidable problem in general, which requires knowing the whole of kind of future infinity. But it uses a heuristic to work out from vertex 2, which things seem to be unreachable.
Okay, so this is find the list of unreachable events from a given event, correct?
Right, exactly.
So in other words, i.e. events not in the future light cone of a given event. Okay, so something might not be in the future light cone if it was at the same simultaneity surface, so to speak.
Right, exactly. So the algorithm sort of has to account for some of that, which is why it's not, you'll notice it's not just showing everything that's on the right branch, it's only showing the late time ones, because those are the only ones it can kind of be confident about.
Are not what? So I mean, the question here is, what is the definition of a causally disconnected? What's the definition of sort of the black hole type thing?
Well, I mean, that part's easy. It's it's the complement of the vertex out component. The difficult part is determining the heuristic for figuring that out.
Well, wait a minute. Okay, so let's just define this thing. So an event A is causally disconnected from B.
Yeah. If the vertex out components are non-intersecting.
Right. If the future light cone of A and light cones of A and B do not intersect. Correct?
Right. That's a sufficient condition.
What's the necessary? What's different?
Let me try and figure that out. That's probably equivalent.
Okay, so let's look at the contrapositive or whatever of this. If the light cones do intersect, then it means they are causally, it doesn't mean those two events are causally connected, does it? No.
I mean, this is where it gets a little bit tricky to define exactly what you mean by causally connected. I mean, strictly speaking, causally connected means there is a path in the causal graph.
Right.
From
so
one to the other.
But causally connected. Let's be clear. Causally connected means because A and B are causally connected. A is causally connected to B. Means there is a path from A to B in the causal graph.
Right, but what we actually care about is, which things will be in causal contact. So for the black hole case, the thing you have to be able to do in order to compensate for these horizon structures is you have to be able to say, okay, we have some event in the causal graph, and we want to determine, are there any events at the latest time step that do not exist in the vertex out component of that event, i.e. that do not exist in the future light cone?
Say that again? Wait a minute. What? I lost that for a second.
So to determine the asymmetric event horizon case, you have to start from a given event and determine which events on the latest time step do not exist in the out component of that event.
On the latest time step do not exist in the out component. So in other words, you could never get back. I mean, look, if we think about this, okay, one of the confusions is an event horizon. The normal notion of an event horizon is it's something that exists in space. We don't usually discuss event horizons as a function of time. Right? The normal interpretation of an event horizon is, I mean, and clearly that's not in fact correct, because a black hole might, if we lived around some star that might turn into a black hole, it isn't a black hole now, but it might be a black hole in the future. So what exactly is, when we talk about an event horizon, okay, remind me, in the Penrose diagrams and all that kind of thing, where we see an event horizon forming, what does that look like? Can we look at that?
Yeah, I mean,
am I asking the right question?
I'm not sure I agree with the premise. I mean, the definition of an event horizon definitely does involve time, right? The definition is the region beyond which it's impossible for null rays to. It's impossible to.
I've got a whole collection of Penrose diagrams here. Pick out one that we think is a relevant one for discussing what we're discussing.
Right. So I would say that an event horizon is a structure in space-time. Naturally, you can foliate it into surfaces.
Yeah,
in space.
I agree.
But it's
so show me that in one of
in
these Penrose
space-time.
diagrams. Could you pick one of these? What would you like to pick here?
Well, I mean, the first one is a good example.
Right, okay, we're picking the first one. Oh dear, we've got, okay. Well, let's see, Penrose diagram of a Schwarzschild black hole here.
Right, so in the first one, you have there the horizon, right, where it sets the horizon.
Okay, so this thing, we're saying, oh gosh, this has time going up, which is kind of annoying. This is outrageous what I'm about to do, but it will make me less confused. Maybe. Okay, so what's happening here? So this is the black hole.
Yeah, so the horizon exists at 45 degrees, which means, as I say, that it's impossible for null rays to escape to future infinity, i.e. to get, intuitively to get infinitely far away from the black hole, infinitely far into the future.
Right, but so let's understand this diagram translated into our causal graph.
Yeah, that's exactly what I'm talking about. So the definition of future null infinity is the limit of the out component of the event. So what you're trying to determine is which of the events at the latest time step and do not exist in the out component of a given event at a previous time step.
Okay, wait a minute. I'm too slow here. Okay, so let's take this picture, okay? And imagine that we just use this as a template on top of our causal graph, okay? There is a node in our causal graph here, and its future, because this is the future light cone of that event there, is all in the black hole, right?
Yes. So you can't have causal edges going beyond 45 degrees in the conformal diagram.
Right. But so what you're saying is that nothing from that
everything
node,
that's on the outside of,
yeah,
everything that's on the outside of that horizon, which is which you'd have to go at an angle steeper than 45 degrees to reach, will not exist in the out components of that vertex.
I get it. Okay, so let's just walk through this again for me very slowly. Okay, so this node here, its out component lives down here. And the point is that the out component of this cannot include something that, here's what's confusing to me, okay? The out component of a node here could intersect with the out component of the node here. Because
yes, exactly. That's the point I was making about the asymmetric event horizons. That's why we have to consider the cosmic and black hole cases separately.
Okay, all right. So let's just walk through this again, please.
In the cosmic case, the two events that lie on either side of the event horizon, their future light cones will not intersect, which is why I was saying it was a sufficient condition, but not a necessary one.
Jonathan, you're speaking too quickly.
Okay, sorry.
Maybe I'm just dense today, but slow down a second, okay?
So, you have a cosmic event horizon.
This isn't the cosmic event horizon.
No, exactly. So in the cosmic event horizon case, as in the one above, the thing is symmetric. So because there's disconnection on both sides, you know that if you have two events, one on each side of the horizon, and you compute their out components, they're guaranteed to be non-intersecting.
Yes, I realize that. I mean, it'd be good to get a Penrose diagram for that case.
We can get one. Hang on.
Okay, so
then to deal with the black hole case, what you're really asking is, as I say, are there any events at future null infinity that do not exist in the out component of a given vertex? And if the answer is yes, then we know that vertex lies inside an event horizon, a black hole event horizon.
Hold on a minute. So we look at
future null infinity. Future null infinity is the whole bottom of that diagram.
I realize that. For this, future null infinity for that node is
no. Future null infinity is a property of the global spacetime. Future null infinity is the whole bottom layer of the causal graph. That, as I say, all of the events at the last time step. And then the question is, do those events lie in the vertex out component of a given vertex? If that vertex is outside an event horizon,
I understand.
Then the answer is yes.
The black hole test. Okay, black hole test. Does every, quotes, final event lie in the future light cone of any given event?
Right, and so if you look at my code, that's effectively what it's doing, albeit very inefficient.
Okay, so more specifically, for all events, of lie in the future light cone of all events, basically. That's really the question. Do there exist events that for which? Okay, so that's effectively what your code is doing here. This is saying.
Yeah, so in practice, what it's actually doing is it's computing, it's looking at everything up to 1/2 of the time steps. That would be up to step 2 in this case.
Yeah.
And then it looks up to the full time step, and it asks, are there any events at step 4, in this case, that are not reachable from the events that were produced at step 2? And so that's kind of, doubling is our finite way of approximating future null infinity, which is of course very crude.
Let's write that down more carefully. So I mean, what you're saying here is this is asking for these possible nodes. If there were no black holes in evidence, every node, every element of this list would have the same right-hand side.
Well, actually, no, there wouldn't be any elements of this list, right? So because the right-hand sides are showing you which can't be reached. So, okay, if you go to the rule and you change BAAB to BAB, you should get an empty list. Because I think that spacetime has no event horizons.
BAB?
The right-hand side of the first rule, you change that to, because basically the reason it's producing event horizons is because that's a superluminal expansion. But if we remove it, you no longer have superluminal expansion.
Okay. Hold on. So these are, okay. So every element, there would be no, I see, there would be no unreachable elements, i.e. this list of disconnected regions would be empty. Okay, so what this means is, what the list is, it's basically something of the form node and then list of unreachable, list of nodes, list of final nodes unreachable from this node.
Right. And so, yeah, so one thing we can discuss is is if we can construct a better heuristic than the one I lazily came up with.
Okay, fine. But let's first of all just look at this question. Okay, so from a given node, and so currently looking at nodes at step T and at what nodes at step 2T are unreachable.
Right.
So I claim that we definitely need a version of that function in which we have a T0 and a T1 or a T final.
Oh, yeah, okay, sure.
Can I rewrite this? I mean, there's this
Yeah, I mean it's trivial code. We can, yeah.
Okay, all right. So let's go. So I think that will be a little bit clearer. So this is okay. So you say initial condition, then we say, I think we want a T test. Well, why don't we just say T initial, Ti and Tf? Okay, so what do we want to do here? So this is, just tell me where to do this.
So that's the final. So step. Okay, well, first of all, hang on. I'll tell you what.
TR.
There's actually an optimization I want to make as well. So I can just write this and I'll send it back.
Okay. All right. Fine.
All right.
Okay, but. All right. Okay. Okay. While I'm at it, should I be understanding these other Penrose diagrams for these other cases? What is the extended Schwarzschild geometry? What is the point?
So that's the second one.
No, I understand, but what's the? This is simply another solution to Einstein's equations, correct?
So that's the full continuation of the Schwarzschild solution, which has this wormhole inside, say, to another parallel universe. So the diamond. So to understand these diagrams, it's better to start with the diagram of Minkowski itself, which is like one of these diamonds, in which you would have the four boundaries, the two past null infinities and the two future null infinities. So when we have a black hole, then we have the structure of the first one, in which the singularity becomes space-like. This is what we were discussing the other day, that the singularity is more like an instant in time in which everything disappears. You are going to hit it no matter what. And that's why the singularity is drawn horizontally.
Right.
So everything that enters the horizon, which is the tilted line, is trapped inside because it can only evolve towards the singularity.
Sure. But I'm asking, in the normal Schwarzschild solution, so if I just solve the Einstein equations on a manifold that has a hole in it, for example, then both of these are valid solutions to the Einstein equations, correct?
Yes, you can consider this the second one like the continuation, the analytic continuation of the first one. Like the first one is the one that contains the reasonable physics, and the other one is just the continuation.
With different boundary conditions, effectively.
Yes, if you want.
I just sent the code, and I updated it to it also deals with the Wolfram model case, in case we want to do that.
We definitely do. All right. Are there more Penrose diagrams that I should look at just to understand more about? I mean, in other words, we need the Penrose diagram for a cosmological singularity, cosmic singularity.
Right, and the other one which is important is the one of a process of the physical process, because these solutions have the problem that the black hole was always there, and so it's not the process of formation.
Right, that was what I wanted to see. Right, that was exactly what I wanted to see. So can we find a Penrose diagram for the actual physical case?
Yes, if you go back to that big list that you had at the beginning, probably it's one of those.
Pick your...
Yes, so it will be go up, or for example, I see that 1, 2. This is one which has like a gray area.
That one there?
Which one are you? So for example, this one which is to the left of that one.
That one there?
That one, yes. Right, so
Why
there
does
you
it
have
time going upwards. It's so freaking confusing.
It's the standard. To me, the other one was very confusing. So there you have like the surface of the star, and you see how at some point it's at some point the horizon, the event horizon appears, which is this red line, and then the star crosses the horizon and collapses to the singularity.
As opposed to this case, I don't see the difference. I don't understand the difference between...
So, for example, imagine that there was no black hole in the second one. Then the diamond would have a pointy end in the future.
Here. Yes, it would be a triangle.
Exactly. Yes. So the fact that the black hole appeared created the event horizon, which is a surface that appears from the center and grows towards infinity, and then the singularity is inside, and it's space-like. So you might have a situation in which there is a singularity which is vertical. This is the time-like singularity that we were discussing the other day, that is forbidden by the constant censorship.
Right.
And so
but which exists, for example, here in this Kerr black hole.
Exactly.
Okay. It's amazing when you just solve random equations and you can, and there are lots of weird things consistent with those equations. It's just so much more confusing than when you have these evolution rules. Anyway, never mind. That's just a bitch for not.
So what the simulations say is that if you try to create numerically this time-like singularity, it's very unstable. And so physically, it's not going to be there. And internally, as we were discussing the other day, the dynamics is very chaotic and it's going to be very different. So it's going to look more like this one we see on the left, or have null singularities, but not time-like.
Okay, here's quite a nice picture of a cosmic event horizon, figure 1 of this paper. So that R equals L there would be a cosmic event horizon.
And is this the same form of diagram? I don't quite understand this.
This is a Kruskal diagram, which is not. It's similar.
This is not compactified.
Right. The problem with Penrose diagrams is that their coordinate system is not well suited for describing cosmic event horizons.
Okay. That says it's a Penrose diagram for a de Sitter bubble.
Right.
Can you explain this picture?
Let me understand what it's saying. I'm not sure what this is. Jose, do you know?
Well, this is like similar to what we had before with the two copies of the exterior universe and then the black hole area in.
Okay, but that's again not. We don't quite understand whether this is like the. Okay. Fine. We don't understand quite whether that's like, whether that's a cosmological event horizon or something different. Okay, let's go back here. So this is now, it's just code.
I don't know what the Kasner de Sitter bubble nucleation is.
Well, I assume Kasner is like Kasner universe, isn't that what?
Yeah. So it would be the Kasner metric, but coupled to some de Sitter metric, and then there's a bubble nucleation. I don't know.
All right, we got this code here. Okay, so now we've got, again, you've got get causally disconnected regions, right? Yes. Okay.
Yep.
Initial
but
time,
now with initial and final times.
Okay, fine. So let's do this here. So now let's see what this looks like with initial time 1, final time 4, for example. Okay, why am I not seeing all nodes here? Oh, maybe I need initial time 0, perhaps?
Wait, what?
Why is there just
there's only
2?
one event it's at time step 1.
But why is it labeled 2 then?
Because it's seeing what new events got produced. Okay, I'm not sure whether substitution system causal graph includes initialization events or not.
Yeah, I see. Okay, fine. But so let's take this and let's do this and let's do the graph here where we have vertex labels arrow true. Automatic. Okay, I am already confused here.
Oh no, so that does make sense. Yeah, so 1 is causally connected to everything.
I see. 1 is causally connected, but 2 now
is disconnected from everything on the right, which in this case includes 26, 27, etc.
So wait a minute. Why we just said 4 steps here? So why is it showing me the ones from 2 different sets of steps?
It's not.
Oh, because
there's a causal graph.
Depth. Yeah, there's certain depth in the causal graph. My layering of this causal graph is purely coincidental.
Yeah, exactly.
It's not the shortest. Okay, so that is showing. Okay, so in this is showing what looks like a cosmic event horizon here. Is that correct?
Yep, looks like it.
Okay, so let's do our test for. I don't understand. Oh, I see. 2 goes to that side and 2 didn't go to this side here. All right, so let's keep going to make sure we understand what's happening here. So if I go to step 2 there, and let's say I insist on step 5 here. Okay, then what I should get is 2, 4, 6, 8. What happened to, okay, 3 is connected to everything. Why is 5 not showing up here?
I don't know. I'm not sure what time step 5 appears on.
Well, time step. Oh, it's time step. Is it time step 1?
Oh, wait, hang on, wait. No, 5 does appear there. 2, 4, 5, 6, 7, 8.
Oh, yeah. Right. Okay. All right. So then this is all right. So let's. This probably could have been an association, but let's go ahead and ask. Okay. So first question is, what's the first of this? Okay, that's 2, 4, 5, 6, 7, 8, 9. 2, 4, 5. Okay, so these are the left-hand sides are the things whose future light cones are not complete, so to speak. The LHS nodes, events, are ones, does that have a name in general relativity? Whose future light cones are not complete. Does that have a name?
What do you mean? Not
Well, I mean,
complete?
that's just referring to, in general relativity, is there a name for an event, for a space-time point whose future light cone includes the whole universe? Because that's what this is saying. Those events are not, so in other words, any event like 1, for example, doesn't appear here because its future is the whole universe, right?
Right, but and by whole universe you mean future null infinity. So I'm confused by the question because I don't know what the difference is between what you're asking and the definition of an event horizon.
There isn't. I mean, it's just saying, I'm just asking, is there a complement of saying that there isn't an event? It's just, there is no event horizon. Okay, so,
Right.
okay. So here, let's make essentially what we want is a Venn diagram of these, basically, right?
Right.
Essentially what we're asking for is, so is there a way of drawing that Venn diagram, I wonder? Is that how we want to do it? I mean, what we want is the intersections, the relative intersections of these things. So that represents a graph that these things here, if there is an intersection, well, so one question, okay, so
I'm not sure I understand.
okay, what is the quotes causal connection graph of nodes, 2, 4, 5, 6, 8? Okay.
And by causal connection graph, you mean?
Well, I don't know what I mean. I mean the thing that is going to turn into the thing that we can look at properties of to find out if we have a black hole event horizon, a cosmological event horizon, or something different. Okay, so for example, the causal connection graph says that 2 has certain nodes. Look, 2 might completely overlap with 4. See what I'm saying? So 2 and 4 have the same future light cone.
Except for 4.
Fine.
Yeah.
Right, but but in particular, by the time we get to these final states, the final time step, future light cones of 2 and 4 are identical.
Yeah, right.
Okay, so there's an equivalence class here of things whose future light cones are identical. So what are the cases? Case 1, future light cone of A and B is identical, or final light cone. I'll call it final light cone, okay? So I'm saying yeah, let's say final light cone. It's kind of a weird thing to say, but you get what I'm saying, right?
Right, a future null set.
Okay, final null set of A and B are identical. That's one case. Okay. Case 2, final null set of A contains final null set of B. Okay, and the other one is that they're intersecting in some way, right?
Mm-hmm.
So for every AB, we have these relations. They're either identical, or they have a containment, or they're disjoint.
Okay.
Well, no. The next case is they intersect. and the next case is their disjoint. Okay, what is a good graphical way to represent those different possibilities? So do we want to represent them? I mean, in some sense, a Venn diagram would be a good way to represent this. Do you agree?
Sure.
But what else? We need a graphical representation. It's going to get significantly more complicated than this. If these are the cases, what is the right way for us to represent this? Because we don't want to have to look at this right-hand side. We want to be able to just look at a signature, basically, of these events at a given step and what is their future connectivity. See what I'm saying?
Yeah.
Okay, so that's what I'm asking, is what's a good way to visualize that? And I'm claiming a Venn diagram, but is there a graph version of a Venn diagram that would be equivalent, so to speak?
Well, I mean, why not just plot the set relations as a graph? Set containment defines a partial order, so we can define it as a directed graph.
What about intersection? That's not, oh, I see. Intersection, that's not containment. That's the problem. That's a different type of edge. Right, containment is fine.
Yeah, so cases 1, 2, and 4 we can definitely represent.
Yes, that's right. So case 3 is the tricky one.
Well, case 3 is the case where both A and B connects to some common vertex C.
Hold on, let me just look up something. Do we have a Venn diagram? Oh, Venn graph plot.
But why not represent it as a graph?
I guess we could add a fake vertex representing intersection.
What is this?
No, but my point is, if they're intersecting, if A and B have intersecting future null sets, then there is an event that's in their future whose future null set is that intersection, I think.
Oh, right, that is a fake vertex.
Yeah, right. So yeah, exactly. But is that a fake vertex? Or I mean,
Well, it's a fake in the sense that it's not on this level.
Right,
but
so the intersection.
It doesn't have to be specific to a level. I mean, I think this is right. That the signature of intersection is just A goes to C, B goes to C.
Fine. Okay, fine. So that's A goes to C, A goes to some X, and B goes to some X. And that X then has what property with respect to these other things? That's another node. See, I'm very confused by this, because what we're saying is we've got A, B, which are at a particular level, right? That's your T sub I level.
Right.
Make sense?
Right.
But the intersection is calling for a bridge, so to speak, at another value of T.
Right.
Well,
That's why I'm saying it's fake. But if he covers this vertex differently, for example, and don't label it, it might be clear enough as visualization.
Well, the other thing we can do is just have an edge between those two things. It's a different kind of edge, tagging that edge. Let's try doing that with a tagged edge for the intersection. Okay, so these are partial order edges, and that one is okay. So let's write the function that basically makes the and I don't know how it's related to this. This looks like a very similar.
Maybe I'm slow. I still don't understand. Why are we constraining this only at the same time step? That's not the case you were describing before, where you were talking about future null sets of 2 and 4, which are different.
Because your function, Jonathan, has two time steps in it: T sub I, T sub F.
Yep.
And what we're asking is, we don't care about T sub F except as an indicator.
Yeah.
Right? T sub I, we're asking the question, given the set of events at time step t sub I, what are their relative causal connectivities?
Yes, I understand that.
Okay, so what I'm saying is that to say that they have an intersecting future null set, intersecting final null set, is to say, as you're saying, and correctly, I think, that there exists a future, a time-like connected or null-like connected vertex X that is in both of their futures.
Yes. I don't dispute any of this.
No, right. I mean, that's right. Look, it's just
so I ask again. Why do these have to be at the same time step when the problem as posed does not require that?
Why do which have to be at the same time step?
The claim is that this vertex X is fake in inverted commas because it exists at a future time step, but vertex 4 exists at a future time step to vertex 2, and we're not claiming that that's fake. So why are we making the assumption that the vertices that appear in this graph have to all exist at the same time step?
Okay, we're not, but I think it's going to be clearer. Why don't we do this? Why don't we just have the intersect case be a differently indicated edge, okay, for now, rather than creating a new vertex?
But we're not creating a new vertex. That vertex is there.
If we include all of the vertices, wouldn't we just get the causal graph back?
Yes. Yes. What we're trying to indicate is we're taking a slice, we're taking a space-like hypersurface, basically. T sub I is a space-like hypersurface, and we're asking on that space-like hypersurface, what will be the future mixing of the future, evolutions of the things on that space-like hypersurface?
I understand all of this, but let me ask again. So if we go back up to the graph you showed earlier, if we scroll up, right? So vertices 2 and 4 exist at time step 2, but there is a time-like edge separating them.
I understand.
So this is no different to the case of A is connected to X, B is connected to X.
Okay, the point that I'm making, Jonathan, is this: the set of vertices whose causal connectivity we are discussing is the set of vertices that exist on some space-like slice. That's what I'm saying.
Yes, like 2 and 4, even though they exist.
I realize that, but what I'm saying is let's not confuse it by throwing into, we can pick another space-like slice and we can ask now, at this state of the world, what are the event horizon structures like? But let's not confuse it by adding in to the description of where the event horizons are or where things are going to be causally connected in the future. Let's just try and make this visualization. We can then decide we don't need to look at the future intersection thing. We just need to find out, because we can just purely from what your function returns, we have these cases. So we simply want to work out for every pair here, right? We're going to work out for every one of these. So let's take this thing here and let's find, compute intersections basically, or compute intersection status. Compute intersection statuses. Very bizarre concept, okay? So of this thing, which I argue would probably be better as an association, but it doesn't really matter, okay? Of disconnected regions, okay? That's going to compute this for these disconnected regions. So for every, well, actually, no. Intersection status of a given pair of list 1, list 2. Or intersection rule for these two things. Okay, so I want to make that so the different cases. So it is a which of so if they're not intersecting Q, list 1, list 2, I hate witches. It would have been good in the whatever. Never mind.
I don't
Forget that.
use conditions and multiple definitions for this.
That's a better idea, yes. Yes, thank you. A much better idea. Otherwise, I'm going to get myself in trouble for some Wiccan discrimination thing of hating witches. Okay. Okay, not intersecting is this, right? That case, correct? That's what we're going to build from this. If, on the other hand, subset Q, right? Subset Q, list 1, list 2, then the subset Q is not a proper subset, right? Am I making sense?
That's a good question. I don't know.
Okay, well, let's find that out. So let's say S1 arrow this, S2.
Yeah, non-strict.
Okay, S2 arrow this. Okay, so that one is this. Okay, now S1 arrow this, S2 arrow this, subset Q. So if they're non-strict, if list 1 is, so then list 1, which way? Okay, fine. So I claim that becomes this. That becomes that directed edge. Do you agree? Right? I mean, you see what I'm doing here, yes? Jonathan, Max?
Yeah, makes sense.
Of course.
Okay, list 2, list 1. S2, S1. Okay, so the final case then is that they are, so the final case,
Intersection, but not subsets of each other.
right. Intersecting Q and not subset Q and not subset Q list 2 list 1. Remember, what if they're equal?
Then there will be subset of itself. And we will
Or if they're
have
equal,
edge
then it's a
going both
two-way
directions.
subset relation, right? Then it's
Right.
a two-way
It's an
diagram.
undirected
Okay.
edge.
Okay, so in this case then, this is the dotted line case, basically, right? How do we indicate that? Do we put a tag on this edge, or what do we do? We say tagged edge? Is there such a thing? How do we do this?
Can you make it undirected edge and then style them differently? I don't know if it will work or not.
Okay, so now what we do is up here, we get this. And what we're going to do is we're going to say outer, or can we just do a tuples, comma 2? I can't remember. Tuples of this thing.
I'm not sure if that's the right function.
Which function? This function here.
You want the causally connected regions, not the causally disconnected ones. Don't you?
Yes.
Right. So I'm sending you a new notebook with those functions.
Yeah.
There you go.
Okay, causally connected regions here. Okay. Really? Is this what I want? Well, okay. I'm not quite.
That was the problem as you described it.
Oh, you
Maybe I
want a
misunderstood.
set of reachable points from each of them.
Okay, so it's this, flatten that, and graph that. Okay, so what's this showing us?
But I think we might have a problem. If they are identical, it will actually call both of those functions.
Oh yeah, that's true. You're going to be screwed by evaluation order.
Why?
Because whichever evaluates first, that will be the one that evaluates.
So you're saying we'll never reach this case.
Right, because we're doing conditional evaluation.
No, it will reach the fourth case. It wouldn't reach. If both the second and third one are true, it will only reach one of them.
Okay, but okay, look, what we're trying to do is we're trying to get a map for a given T sub I of what the future connectivity of all these things is going to be. So what we should see, the thing I'm confused by is why are we not seeing every node? Oh, we are 2, 3, 4, 5, 6. Okay, fine.
I think we all.
So this should be strict subset Q, basically.
Yeah, subset Q and not list 1 equals list 2.
Yeah.
Okay. All right.
And then add another evaluation point.
Okay, so here we want this and not. Let's just do it the other way around. Subset Q. Is there a strict subset Q?
Not that I know.
Okay, so now we want intersection rule. So this is the equality case.
Yeah.
Intersecting and not subset and not subset. No, that's the pure intersection case.
Well, yeah, we need a new case for it.
Right. So we need an equality case, which is that the sort of list 1 triple equals the sort of list 2. And then that one becomes the double directed edge. Okay, let's try all of those. That's that. So this is the same thing again.
Well, no, because now it deals with the equality case, so we have 2 loops rather than 1 loops. Amongst other things.
So what do we conclude from this? We conclude that, so if we were to take this and say simple graph of this, for example, what's that going to do?
Right. So we can infer from this immediately that, for instance, 5 and 6 are causally disconnected.
5 and 6. Okay, so how do we draw that in this graph? somehow. How do we deduce that easily from this graph? How do we indicate the event horizon? What is the graph theoretic way of discovering the event horizon?
Well, all non-adjacent vertices.
Okay, so what's the difference then between so you're saying anything that isn't a complete graph. Don't we want the complement of this graph? Isn't that more useful?
Yeah, I agree, but that's not the problem you described. I agree. I think seeing the causal disconnection is in many ways more useful.
Hold on, in the case of black hole, wouldn't it be that we can go one way but not the other way?
Yes, in this graph. Right, this is the causal connection graph. And this causal connection graph is saying you can go from 1 to 8, but you can't get back from 8 to 1. Right?
So we need to find a subgraph which doesn't have any outgoing edges from it.
Yes, that's a black hole, right. So for example, 8 here is something that has an event horizon relative to 1. So in this graph,
well, 8 is a black hole in itself.
yes, but it's okay, right. But so the question then is, what is the subgraph in which there is connection between the nodes, but you can separate this into subgraphs? So isn't there some standard community-like mechanism for describing this question of whether there is a subgraph, whether it separates out? Wait a minute. Francisco on our live stream is pointing out there's a mistake in line 13, line 8. Should be connected with the range of intersection. I'm not sure. I think we probably fixed this. Okay, so again, let's figure out. Okay, so first question is, let me just write the thing that says this thing here, right, is otherwise known as basically. This is our causal connection graph, which is what we tried to do before. Causal connection graph of our rule init TI TF is otherwise known as this thing here. Kind of goofy. Let me just compute this separately. Okay, so that is so here we could say causal connection graph of this thing here. And I don't know whether simple graph is what we always want to apply. Am I making sense? Is simple graph always okay to use?
I guess for our purposes it is.
Why are there multiple edges? I don't understand why there would ever be multiple edges here. The outer...
Oh, actually it's a good point, because we do need... That means they're equal.
When there are multiple edges? No. When there's a back and forth edge, it means they're equal. See, the back and forth edge, it means it's equal. Why are there multiple edges from that node to this node here?
Oh, is it because each tuple appears twice? We probably don't want that.
No, it's the tuple each way round. It's ij and ji, which is
right, and we don't really want that.
Yes, we do want that. We absolutely want that. They're not symmetric. if A is connected to B, it doesn't mean that B is connected to A.
But the way we compute the result from it is symmetric. In that, we produce an edge in both cases because we have the
then we
subset
got this
function
wrong.
going
We got
both
this wrong.
ways.
We're saying subset. Because we're going to do it all ways round, we actually don't want this case, right? Am I making sense? This case should be the null list.
Oh, sure, we can do this way too.
But alternatively, just say simple graph. That's fine. Either way, does it work both ways? Do you see what I'm asking?
Not quite.
Okay, so look. This is going to generate, for A and B, if A is a subset of B, then this will generate a directed edge from B to A. Right? We're then going to test it a second time. It's going to have a second entry in the tuples, and it's going to get the same edge.
Yeah, so it seems to me we just shouldn't do each tuple multiple times.
Well, whatever. I mean, we could do that, but I don't see the point. I think what we want to do is just say simple graph of the whole thing.
So I'm wondering what simple graph would do if we have both undirected and directed edges.
I think it doesn't. Well, we can look it up, but I think simple graph will just leave. You mean if there's both an undirected and a directed edge between two nodes? I don't think that can happen.
Yeah, that can't happen. Yeah,
right. So in this diagram, what we're seeing is, so let's take a look at that diagram there. And we're asking, okay, so let's look at what that diagram does if we go one more step, for example. Okay, so that will probably be stable at that point. Okay, so we can have confidence that that is the correct diagram. So for example, if we go to step 3 here, okay, so we're getting a more complicated thing, but I think the structure is becoming a little clearer.
So I think what we should do here is to find strongly connected components and then make a plot of those, which would be a tree, and it would essentially show us where the black holes are.
Okay, that makes sense. Okay, so fine. So let's take this graph here. Okay, so this graph is already giving us an indication of what's going on, which is roughly that there is a region here where everything is connected to everything, roughly. I mean, this is like, this seems to be some kind of cosmological event horizon, sort of. Do you agree? But
yeah, that's what it is. It even looks like a Penrose diagram.
Okay, but so let's try to understand how to compute. So you're saying we want these strongly connected components, which are exactly the things which have two-way connections between them, right?
Yeah.
Okay, so let's take this guy here, and let's say, give us the strongly connected components of this. What is it called?
I
strong
think
components,
it's connected components because
Say
it's
again?
strong by default.
Okay. Really? Is this right? Okay, so let's look here, the graph. Okay, so this is claiming 1, 3 are a strongly connected component, 5, 9 are a strongly connected component. So this is broken into many strongly connected components. So what is Max's proposal here?
To represent each component with a single vertex.
Okay, and then do what?
And make a tree out of them, according to how they're connected to each other.
Why is it a tree as opposed to a graph?
Well, because if there is a loop, it means they're in the same component, because you can go to every node in any of them.
SWSH on our live stream is suggesting doing an outer complement, but I don't understand that. I don't understand that.
Yeah,
Sorry,
so within a single strongly connected component, you can go from every vertex to every other vertex.
Indeed. So
If
we
you
don't
have a
want to...
loop in a, well, if the graph of connected components have a loop in it, it means you can again go from each vertex to another one, which means it's actually one strongly connected component.
Yeah, so you're saying this thing here. Okay, so hold on. So basically what you're saying is compress every connected component to a single node.
Yes.
Okay. So how do we do that? Is there an easy way to do that? An easy graph theoretic operation that does that?
I mean, it's not hard to do manually, but it might be better doing
Well, we could just take one representative of every connected component and then we'd be done.
Oh, exactly.
Okay, so then essentially what we're doing here is we just say subgraph of this thing here, comma, first slash at those connected components.
Yeah, but you have to recompute the connectivity.
Why?
Because there might not be an edge from that component to another one.
You mean that
you might have to go through other vertices.
That member of that component, basically.
Yeah.
Okay, fine. So you're saying we have to compute from each. So what are you suggesting here?
Hold on. Isn't there a way you can merge vertices into one?
I thought there was.
Why don't we just do a slash dot of all vertices that aren't the first vertex to the first vertex?
Oh, that's
the representation of the graph. Yeah, that would work.
It seems like the easiest way to
let's make an equivalence class. So that basically what we're doing is we're replacing every vertex with the first vertex. But let's just look up whether there is a way to do this by...
there is. I looked a while ago because I had to solve this problem in a different context. As far as I know, there's no way to merge vertices without just doing slash dot.
Okay.
What does vertex contract do, if it exists? It doesn't exist.
It doesn't exist. Edge contract exists.
Vertex contract does exist.
Does it? It's not. Is it documented?
Well, it has a user's message.
Yes, it does exist.
Oh, hang
on. This appears to do exactly the right thing. This appears to do exactly what we want. So this is vertex contract.
So you just do vertex contract of graph, comma, connected components of it.
Right. Yeah, exactly. Contract a collection of vertices into a single vertex of the graph G.
Wait, don't you want to map vertex contract over connected components?
No. Look at the usage. It says contract several collections of vertices. Oh, maybe all together?
Well, if they're all together, why wouldn't they be in the same list?
Okay, creates a new graph by removing all edges between Vi and Vj and merging them into a single vertex V1. Why doesn't it have an example of something with multiple? No, there it does. Oh, this is using fold. It's documented to use, it's documented to use these things, but it isn't. No, we can certainly use fold, but I'm going to send mail to Charles here. Given the documentation of multiple lists,
yeah, looks like it doesn't work correctly.
Okay, but clearly we can make fold do this. Of the original graph, here, comma, connected components. Okay. All right, cool. Okay, so that is then a skeleton of that space-like surface, right? That's showing us. Okay, so let's just.
Oh, that's a nested collection of black holes.
Which is generically what a cosmic event horizon will be, right?
All right. Okay. So fine. So let's just write.
If you have a superluminally expanding universe, locally it'll always look like a.
Yeah. Right. A collection of black holes. Right. Okay. So this is causal connection graph, and so this is what is this? This is causal connection summary graph.
Causal connection DAG.
Let's just call it causal connection summary. And that is rule init TI-TF, which is otherwise known as with G equals causal connection graph of rule init TI-TF, and then we need the fold of that over G comma connected components of G. Okay, so causal connection summary. So then the end result of this would be, we could say causal connection summary of this thing here. And that's going to give us this graph here. So now we can say, let's do the causal connection summary at level 2. And then let's do the causal connection summary at level 3 and level 4. Okay, so that's showing, what is that showing? At level 4, it's breaking into, so let's just see whether we heated to constant weight, so to speak, here, and we did. Right, so we probably could do a nest, we probably could do something where we test whether we've reached the final state. Okay, interpret this picture. So you're saying there's just a nested collection of black holes forming.
Right, each node is a black hole. Okay,
all right, so let's go back then, and let's do this for all rules. Okay?
But I don't think that's a useful way to think about it, because as I say, that doesn't make the appropriate distinction between cosmic and black hole cases.
All right, okay, fine. Let's go back and look at the case that we were looking at here, where we were looking at, here we go.
Right, so I mean, take for instance, the one on the bottom left there would be a good one to.
All right, let's try to take all rules of this type. Okay. AABA was our thing here, and so these we want AABA. All right, let's do this. Let's take this rule AABA, let's say 5 steps, and causal connection summary of this thing, let's say 7 steps or something. I don't know what we could pick. And let's say 2 steps here, 3 steps. What do you want? 3 steps. Hash AABA. And let's just, we can just do this. And now let's say, resource function of parallel map monitored. Okay, this over the enumeration of those rules. All right, let me widen this out because we're going to get a big output here. All right, here we go. So this should be generating, I better put a time constraint here. Five seconds. Okay, here goes. Okay, launch the machines. Since we do want a factor of 100 faster output. It's really annoying. It takes so long. I complain about this every single time that it takes so long to launch these machines. Splat. Okay, I wonder what happened to that machine. Okay, let's see what's happening here. Okay, so these are mostly trivial. Come on. So what this means, what does this mean here?
What was your initial time?
What's that?
What was your initial time?
I think it was 2. No, it was 3. So 1, 2, 3.
Well, we have no idea how many events are at level 3.
We have to look at this graph, right? But I mean, so let's see whether there's anything non-trivial that happens here. Okay, what about this guy here? So that one there seems to be, and that one there seems to be forming what you might think of as a, I mean, notice that we have no undirected edges anywhere here. Okay, that one is very simple to understand. Right?
Yeah.
Well, are we generating the correct results here?
Well, as I say, I think we should analyze that black hole result more closely because that doesn't look correct.
Okay, yeah, let's just look through here. Okay, let's go back up. Which one were you saying?
The black hole, the one non-trivial asymmetric event horizon case. That one.
This one here?
No, down. Actually, I mean, there's one there. Yeah, that one.
This one here?
No. One up and to your right. The event horizon case.
One up.
And to the right.
This one here?
Yeah. I mean, there are several.
Why isn't it correct?
It's what we now want to analyze is the causal disconnection graph, which is what's going to give us the indication of the black hole.
Doesn't this give us indication of black hole? Because you can go to the right, but not to the left.
Right. I mean, isn't that exactly what this is? That's saying that there is causal connectivity between the first connected component, the universe. Each dot here is a connected part of the universe.
Okay.
And I would think if at level 2 we were already disconnected, we already had 2 disconnected universes, like here. Oh yeah, there we go. Yeah, it's hard to see them, but there are the 2 disconnected universes, right, that occur in this case. Right, they're those 2 dots.
Okay, so are there any non-event horizon cases then?
Yeah, this one here, it has 1 dot.
Okay. Which is wrong.
That has only 1 dot. So this one here, what is this here?
Yeah, so that's not a non-event horizon case. That's why I'm confused.
This one has
no. The one with 1 dot is not a non-event horizon case.
Well, I think the issue is the connected components here. You're claiming that that's the wrong result.
Yeah, well, I'm wondering what these results are because they don't seem to make sense to me. But maybe I'm just confused.
They're what we computed from your code, right? Unless we did something wrong. Okay, so
in that case, there was just one vertex on the third level, wasn't it?
Yeah, that's what I'm wondering. Without knowing what levels the vertices are at, it's very hard to interpret what these mean.
so how do we indicate what levels the vertices are at? Do we draw a foliation, or what do we do?
Well, we could layer by step number.
Highlight them.
Say that again.
Well, layer by step number 1, but we can also just highlight those vertices.
Which vertices?
The ones at the level being considered.
Okay, fine.
Right.
Let's do it. Let's do that.
And it might be useful to label them as well.
Fine. Okay, let's do it. All right, so we're going to go here and we're going to say the vertices at that level correspond to taking this thing, and we'll compute for this. So this will say with G equals this. Is the first vertex vertex 1? Did you understand my question? Is the first vertex in the causal graph vertex 1? Do you know?
It's not my code. I assume so.
Okay. So we want the neighborhood graph, if I'm not mistaken. We want to, here, we want to say highlight graph of G comma neighborhood graph of G comma 1 comma, in this case 3. Is that correct? Is that correct? Max, can you follow this? Is that correct?
Looks like it. Well, don't we just want to highlight level 3 only, not all of them?
How do I do that? Okay, I do that by doing a complement, right?
Yeah.
So I'd say graph complement of level 3 minus level 2, correct?
I think it's a graph complement. Well,
what are you saying?
Yeah, I'm not sure what graph complement does exactly.
Oh, graph difference.
We could just use vertex complement.
No. Why don't we just say graph difference? Is that right?
Might be.
Can you look it up, please? I don't think it's correct. So you're suggesting that I say vertex complement here?
Well, I'm suggesting to get vertices from both of them, and then the complement.
Well, then that's the out component, right? Is that correct?
Yeah.
What is it called? Vertex out component?
Yeah, I think so.
Okay, there we go. Okay, so that's showing the level 3 things. And then what you're suggesting is that we label both of these. Is that correct? We label both of these graphs, is that correct?
Yes, but I'm not sure it does the right thing. Because if you look at the first example here, from wherever it takes them to produce a second graph,
I didn't understand. So
inside causal connection summary, it has a list of vertices which to use it for the second graph. So we should just use the same list of vertices to highlight.
I see, which are members, which are the representatives of the connected components. Right? It's not the full connected component. But I don't understand why there's a vertex 1 in here at all. Because that wasn't in T sub I. That shouldn't have been in the initial state there. Do you understand what I'm saying?
Yes, I don't think they're labeled the same. Doesn't look like it.
Okay. Well, let's understand that. So,
I'm not sure what happens.
I'm sorry?
So when you do vertex contract, I'm wondering which vertex does it
It says
keep?
V sub 1. It says the first vertex in the contraction list.
Okay.
That's the representative it's picking. Right. So you're saying, I mean, I think the code we had above, this code, this causal connection graph code, I believe is preserving the numbers, the vertex numbers here, correct?
Well, it should be, but then we wouldn't have vertex 1.
I'm sorry?
I mean, it should be, but then we wouldn't have vertex 1 on the bottom, so something's going wrong here.
No, I'm trying to understand. This one here, so let's take this case here, right? Okay, so this case here, got that causal connection graph, and now let's take this now, I mean, this is only labeling the oh, that's just labeling, sorry, that's just the causal. Okay, so that's this. Okay, we want this rule. I'm sorry, we want this here. Okay, so that's labeling the nodes there. Okay. Right? Yes, understood?
Yeah.
Okay, so what should happen is, that's the things at level 3, right? So the causal connection graph here, if we label it should contain the same, it doesn't, so something is wrong here, right? This contains 1 and 3, which are higher level up here, right? Not the things at level 3. This was supposed to contain only those things at level 3. Jonathan, I think...
let's check how we select the vertices.
I'm sorry?
Let's check how we select the vertices in causal connection graph.
I know, it's Jonathan's code. So Jonathan, can you say?
Wait, causal connection graph is not my code. Get causally connected regions is my code.
Okay. All right. So let's look at causal connection graph here. But what was causal connection summary? That is summarizing this, having reduced it. So let's just look at the causal connection summary and see what it does. Okay. So that has
let's do this
down to level 3, right? So that has vertices.
I think it takes up to level 3 instead of level 3 only.
Mm-hmm.
Yes, I agree. So let's figure that out. So this is causal connection graph. Okay, causally connected regions is getting only at level 3, or I don't understand that quite. Is this causally connected regions, the T sub I here, is down to T sub I or specifically at T sub I?
Down to T sub I.
Okay, that's different from what we, okay, I understand. So then what we'll want to do here is to remove from this those nodes which are above level T sub I, correct?
Above level. Wait, what?
Above level T sub I, prior to level T sub I, we want to remove those nodes from the things in the causal connection graph. True or not?
So by above, you mean before?
Before, that's right.
Right,
Is that
okay,
what we
yeah.
want to do, or do we want to show the complete flow? I think it would be useful to see. I mean, okay, so the disconnection, I see. At level 3, yeah, you're right. We want to remove the things before level T sub I. Right?
If you just want to see the structure at specific time steps, then yes.
Okay. All right. Okay. So what we want then, how do we do this then? So what we want to do is from the T sub I. Okay, so down here, we've got this, and we want to pick we've got this graph. We found those components that are specifically at level 3, right? So then what we want to do for causal connection graph is to get the subgraph. Okay, so let's do that for this case, okay? So here, the vertices specifically at level 3 would be, let's remove that. Oops. Yeah, it's just this. Okay, so those are the vertices specifically at level 3, correct? Yes? No?
Yeah.
Okay.
Sounds like unless I'm missing some subtle.
Okay, all right. So then what we want to do
Or
is
possibly
pick
4.
out, we want the subgraph of line 64 with those vertices, right? Okay, so then according to this, those are 3 disconnected regions. Right, specifically at level 3, those are disconnected regions.
Which will always be the case. It's a space-like hypersurface.
Okay, then what should we be doing?
The time extended case, the one I programmed.
So why don't you walk through then what you think we should be doing? Because you were saying that you didn't think that this was giving the correct results.
Wait, we need to take. Okay, what was that function that was giving us list of future vertices?
Get causally connected regions.
Right, so we need to take a subset of those for the vertices we care about.
Yeah, right.
And then
exactly.
from that on, we do the same thing.
That's what I was trying to do here. Oh, you're saying we look at that the things for which we generate the causal. Can you guys help, please?
Yeah,
the things for which we are generating causal connection summary. You're saying that we don't want to consider in that original list of causally connected regions, we only want to consider those nodes that exist at this particular level. Is that right? Okay, fine. All right, so let's go all the way back here. Okay, so this is get causally connected regions. And so this, what we want here is causal connection graph at, effectively, which then has to also compute, which I'm surprised you can't compute, Jonathan, while you're computing this. Don't you have that?
Yeah, obviously I could. I mean, if you want me to modify the code, I can do that.
Why don't you make a version of it called get causally connected regions at?
Okay.
That just gives the ones at level T sub I.
Right.
I think this is useful as well, but that would also be useful. Okay. Sorry, let me just look at one thing here. Okay, let me know when you have that. Hold on 1 second.
Yeah, it's sent.
Okay, great. Sorry, I'm just dealing with a couple other things. Okay. Okay, fast work. All right, so this is now, so this is get causally connected region at. Okay, so I should just copy all of this. I'll probably want the model case of that in a minute. All right, so now what we, I guess, want is to modify this code. Where was it? We want this code to be causal connection graph at, get causal connection regions at. And then causal connection summary. Okay, what does that mean? Is that what we expect? We can try running this. Should we try running this?
Nice.
Was that what we expected for that case?
Not necessarily. We need to highlight those vertices somehow.
Okay, well, we've already done that here, so let's do that this time around. Okay, so this would be causal connection summary at. Is that right? Is this what you think, Jonathan? Is this correct as far as you're concerned?
It's doing what you requested, I think.
Well, but do you think it's doing the right thing? I mean, so this is now saying, oh, looks like complete nonsense, right? This level, this is highlighting vertices 4, 9, and 10, but that's not what's appearing here.
Mm-hmm. Right, because the out component construction highlights the 4th level.
What level would you like to highlight?
You requested level 3, right?
Oh, so let's do that then. So, okay, so this is...
If you change the causal connection summary at from 3 to 4, do you get the same result? That's what I'm wondering.
This one here.
Mm-hmm. No. Wait. What is that out component thing doing? When you and Max wrote that, I assumed you knew what you were doing, but what is that meant to be computing?
That's computing. The out component is the future light cone of 1, of vertex 1, right?
It should be 3.7, not 4.7, because we are computing level 3 here.
Sorry, what are you saying? Okay. This here should be those edges that are precisely that are contained on the leading edge of that light cone. That is, they are
I don't think that's how causal graphs work.
Yeah, that's not the same as generations.
Yeah, my code is computing generations, i.e. time-separated layers.
Right, so
that's much better. So we should just take list of vertices from causal connection summary at, instead of recomputing from scratch here.
Yes, right.
Okay, so tell me what you
because look, I mean, you can immediately tell this is wrong because there are meant to be 7 steps and there are more than 7 layers.
Hold on. So what do we want to do here? So we want to take the first of this. So then we take this and we compute, let's say GS equals this, and then we would compute. Hold on, that would be GS there, and here we will take first / at GS. Is that correct?
Right. But
I'm sorry?
well, the only problem, it will only give us one vertex from each component.
What will only give us one vertex? That's the summary, because we're doing the summary here.
Yes.
Also, that GS is not in scope.
I know.
And once we get the Wolfram models, we should use layered causal graph for layout.
Hold on. So that's the highlight graph of that. What's that 5 doing now? That's the time constraint. Okay, well, at least that agrees now. So that is the poor isolated object at that level. So this has okay, so here.
Does that mean there's only one component?
That's correct. So 8 to 11 is saying that relative to 8 claims to be able to reach 11, but 11 cannot reach 8. Am I making sense? So arguably here, we should actually draw this graph down to level 7, because otherwise we're not going to be able to tell.
Yeah.
See what I'm saying?
Right.
What connects to what. So let's draw that to level 7. Oh, for goodness sake.
Yeah, we should make it layered, otherwise you won't understand anything.
All right. Wait a minute, what did I just compute wrong? Did I do this wrong? GS. Oh, I just managed to make that into a layered digraph. Not completely useless, but fairly useless.
Yeah. Of the graphs Max said we'd had trouble understanding, that was probably not the one he had in mind.
Okay. Okay, so 11 is the representative of the connected components at that level. So that's claiming there are no, okay, so this 8 to 11 thing.
Yeah, 8 and 11 aren't actually causally connected, but something in the connected components of 8 is causally connected with the connected components of 11.
Oh, how could that happen?
No, that can happen. That's an intersection
yes,
of the future light cone.
Right. So I think when we do the vertex contraction, we should arguably rename the vertex to be the whole equivalence class.
Just a nuisance to do.
Well, we should highlight all of them.
All right. Okay.
Otherwise, you won't understand anything.
Right. I mean, this is pretty incomprehensible as it currently is, because we don't actually know what's causally connected to what. But that's a good sign. That's a very good sign.
What's a good sign?
That we're picking up the black holes.
Well, we're picking up this black hole.
Yeah, which we weren't doing yesterday. Well, my very naive code yesterday wasn't doing, but now we are.
Okay, but so in this case, do you believe there's a black hole here? Looks like it, actually. 11 looks like it's pretty black holed.
Yeah,
right.
Yeah, I believe that.
So that 8 is basically, so right now we don't have any cosmological event horizons here. Is that a true statement? All the things we're seeing here are black holes, not cosmological event horizons.
It looks like it.
All right, so let's go compute all of them, just for the hell of it. And then we can do the Wolfram model case in a minute. And right now, let's just, this is one of these, you're not expected to understand this type things. Let's just see what these come out like, and we can go back and relabel them later.
Well, one of the reasons I don't understand them, because we need to check if they're correct or not.
Fine. Okay, all right, so, wow, that's a weird one. Okay, so a lot of these have okay, so there's a black hole. Okay, what's this guy here? Oh, look at this one. Look at this.
Yeah, that's a cosmic event
horizon.
Yep. Yeah, I think this is working. It's just, as I say, without knowing the connected components, it's kind of hard to interpret what's going on. But the combinatorial structure is right.
Okay, so there's a cosmological event horizon. What's this thing here? Maybe we'll find a space tunnel in one of these.
That's a black hole. That can happen.
Is there a solution in which that happens?
But if you throw a black hole into another black hole, wouldn't it just happen?
Yeah, embarrassingly, I don't actually know the name for a solution for a nested black hole, but...
Does Jose? Is Jose still with us? Does he know?
You're discussing black holes inside black holes?
Yes.
Well, I would say that the event horizon is a unique structure. I mean, when you have a collision or something like that, it will form a single one.
No, we understand. But look, we've just got a structure here that is a black hole inside a black hole. So let's say you numerically solve the Einstein equations with all of that random chaotic stuff that's happening inside the event horizon of a Schwarzschild black hole. Right?
Yeah, so you can have apparent horizons.
What's that?
I mean, there are these apparent horizons which are local structures, and those can be nested. But the event horizon, I think, is a unique thing. It's a unique thing that you measure from infinity.
I see what you're saying. You're saying you can't define an ordinary event horizon because within the black hole, within the first level event horizon, there's no infinity to look at with respect to which to measure another event horizon.
Right. If you try to find the inner one, it would cross at some point the outer one.
Okay, so what does this mean then? Here.
Well, these are nested. I mean, everything we're computing here is an apparent horizon. I mean, as they said, right? Because we can't compute the infinite causal graph.
Fair enough.
So these are nested apparent horizons, and yeah, as Jose said, if you ran this for long enough, they would become a single event horizon, but you'd have to run it for infinite time.
Okay, so there are a whole bunch of cosmological things here. It's pretty cool. Okay, so that one, so wait a minute, 12 to 16, that's really weird.
Wait, why is there an edge from 12 to 16? That shouldn't happen if they're in the same generation.
Well, I don't understand this picture here.
Yeah, if you have an edge from something to something else, it means that something else will be on the next generation, by definition.
Well, I'm not sure what's actually happening here. Let's take a look at this guy. 12 to 16. What? This is a weird case. Look at this. So this 12 goes to 16 by a time-like edge, right? By a null edge, whatever, the causal edge.
No, it seems the graph on the right is correct, but they shouldn't be in the same generation. So computing generations is not.
Why can't they be in the same generation?
Because they're time-like separated.
Generation is defined as, the thing that causal edge goes to have one larger generation.
This corresponds to a non-globally hyperbolic spacetime. because there are time-like because there is no consistent way to foliate it into space-like hypersurfaces, right? Because within what we're seeing here is within a single generation, you can have time-like separated events.
Yeah, I understand.
So this is a failure of global hyperbolicity.
Okay,
What do you mean? How do you define generations?
Because substitution system causal graph runs the substitution system for one generation, or it runs one iteration then the next, and so all I'm doing is I'm computing up to the to get the third. I'm computing everything up to the third and everything up to the second, and then taking.
So these are multi-way causal graphs.
No, these are single.
But for single branch, multi-way causal graph for a single branch.
I presume that's what substitution system causal graph is doing, but
which is not the same as Wolfram model causal graphs,
right?
Because the generations there are defined exactly as each next.
All right, let's take the same code and let's apply it, and we have to wrap fairly soon, but let's try to apply it to Wolfram models, okay? And because I think
and let's take generations from
that. Okay, so can we loop back and what was
but the taking generations is fine because your code already does that, Max, right? I mean, if I put in
I'm saying let's take generations and Wolfram model.
No, but I'm saying that the code. I was assuming substitution system causal graph worked like Wolfram model, where the second argument was the generation count.
Which I think
generation that's causal graph is not. Well, you get generation count for the whole graph, but you need to extract a layer from it. So the question is how.
No, but for a substitution system, there is no difference between iteration. The substitution system has a canonical updating order.
Somewhat.
So
it has a max scan canonical updating order.
So what? Okay, Stephen, what is the second argument in substitution system causal graph?
The number of max scan steps that have been made.
So it is a kind of generation.
I think so.
Okay, so we're fine. This is, as I say, this is just a failure of global hyperbolicity, which won't happen.
Yeah, I think so. Which can happen.
Yeah.
I mean, it's a nice example actually, but it can happen. Okay, can we do the Wolfram model?
Well, that means it's a different kind of generation. Because the way Wolfram model computes them, you cannot have causal edges from one generation to the same one.
Yeah, like I say, the Wolfram model case enforces global hyperbolicity, which substitution system causal graph doesn't. But that's okay. We kind of knew that.
Okay, fair enough.
Okay, all right. So let's do the big case here. Okay, so basic bottom line here is we've successfully found that there are cases that have cosmological event horizons and black hole-like event horizons, which is kind of cool. We've not found any other we found this slightly more exotic structure with apparent horizons here, right? Someone's asking here, the cosmological event horizons differ because these are different connected parts of the universe. Each one is connected, but they simply can't reach one from another. Whereas the black hole case, you can get from one component of the universe to another component, but not back again. It's a one-way trip in the black hole. Whereas in this case, once you're in one of those components, you're stuck in that component. In both cases, you can get, in this case, one-way trip. This case, it's different components. It's great. Actually, this is nice. What's that?
These are weakly disconnected components.
What? Well, what do you mean?
Well, in the sense that no edges at all.
Well, I'm sorry, what? They're disconnected. I mean, there are no edges. But what are you saying? I don't understand.
Well, anyway, I won't make any deep point. I'm just saying the difference between strongly and weakly connected components
is I see. It's the difference between the black hole case, which cares about the direction.
Yeah.
Okay, fine.
And by the way, this nested one on the right is not going to this. I mean, it's not going to collapse in the future because this seems like it already got to the repeating case.
Yes, I agree. So that means
There's
there's a
anomalous, we
component-
can have that, even though in real physics we might not be able to have it.
Well, I mean, so this is saying, this is something where you can fall into black hole 11, and from there you can fall into the inner black hole 10. Right?
Yeah.
Okay, can we look now? Okay, let's loop back here, and let's look at. Okay, so what do we need here? We need causal connection. What we're trying to get is causal connection summary at. We're trying to get this function, basically. Oops, where was it? We're trying to get this function for the Wolfram model case, right?
Yeah.
Okay, let's do it. All right, so what are we changing here? So first thing is your causal connection summary at. I have fed that into, I don't think your code, so your code uses, your code specifically calls into an evolution function, right, Jonathan?
Yes, so you need get Wolfram model causally connected regions at,
Okay.
which is a bit of a handful, but that should be in the notebook I just sent.
All right, okay. That you just sent or that you said, oh, that you just sent, okay.
Yeah, I'm losing track. It's possible it was in the previous notebook. I honestly can't remember. Oh, it's blue, which indicates it probably wasn't.
Okay, all right, fine. So that goes in there. So then we have to map that through into, okay, here we go. That's this. Okay, that has no dependence on anything beyond that. Okay, so now we need the chain that gets the causally connected summary, whatever it is thing, right? So first thing we need is, okay, the summary at, I'm going to copy that into a different notebook here just so we keep track. The summary at, and that depends on causal connection graph at, which is there. Okay, let's go back down to the bottom. Okay, so now let's say, oh, I don't know whether we want to do this. Let's just call it WM. It's a hack. But it's getting late, so we're going to have to hack it. Now, some of these things here, oh no, that's going to make a causal graph, so it's not a problem. So this is now WM summary at, WM causal graph at. Okay, does this look right? Now we need to go back up here. And this
It should just be resource system Wolfram model and then causal graph at the end.
well, what's the initial condition?
Automatic.
And that is just, no, is that going to work?
Yeah.
Okay. So then here,
Well, it needs to be WM. Sorry, it should be WM causal connection summary at, but apart from that, it should be fine.
okay. All right, so now what I did previously, I actually had a nice collection of these things. So let me just look there. Black holes 2. I believe I had a line where I just had, maybe it's in black holes 1. Well, do we happen to know where the initial conditions, I was looking for a 2-2 goes to 3-2. See, I think we maybe had it here. Here we go. Okay, so let's do a random sample. Rules 32, 6, for example, okay? Let's do %87 here. All right, let's see. It'd be amazing if this works. Well, it did something. Boy, these are so similar looking to the ones for string systems. Okay, let's look at this. Do we believe this? 5.
Well, it's really hard. Well, there are only 3 of them. So presumably 6 and whatever is to the left of 6 are in the same component.
Yes. All right.
Well, yeah, by the way, you shouldn't be using layered digraph embedding. You should be using layered causal graph, because that would give us correct layers.
Okay, hold on. Where should I be using layered causal graph?
Instead of causal graph property. Okay, that's better.
Okay, so these are now
yeah, so now we know there's only 3 of them.
Only 3 whats? Oh, things.
In the last example. And the one on the left has to be in the same component as 6 because they're intersecting.
Yeah, which we can see. Right, so there, it's intersecting like that, right? All right, let's run the real case here.
I don't understand why 6 and 5 are not. Oh, okay, because not everything can be reached from 5, but everything can be reached from 6.
Okay, here goes. You know what, I'm going to stop making this 200% because otherwise it's going to be absolutely huge. We are at 2,000 out of 4,700, so let's see. Makes a big difference to have a factor of 100 difference in speed of the computer. All right, we're almost there. Let's see what kind of exotic. Oh, you know what I didn't do? I didn't put the interactive selector around this. We're not going to know what's what. I may have to rerun this. Okay, it's still grinding. I see it's generating generating all those causal graphs.
It means we have the fun of counting, top to bottom.
That's absolutely absurd. It's a stupid idea. This is going to take forever because it's sending all the data back from all the 100 computers.
So I'm afraid people on the live stream won't be able to see anything. Even on my screen, it's kind of small.
Okay, this has everything, but it is not displaying everything here. All right, so that's the complete set of results, all 4,700 of them. What we should probably do is, given the right-hand sides here, given these second things here, we should basically, you know what we should do? We should ignore the first. We should just compute. All right, let's do this. Let's compute. Okay, I'm gonna go back to 200% here. Okay, I've got a better idea here. Let us do the following. Let us compute. I just want to find out what are the structures, what are the causal structures that we can get. So here, what I'm going to suggest is let's remove this causal graph thing. Boy, I'm just trying to understand how I want to get a representative sample. Well, here, there's an easy way to do this to begin with. Highlight graph. So we don't need that first thing there. We just need that graph. And now let's say index graph, because we just don't need, we don't care about that. We don't care about that structure. We just want this. We would set that index graph. And now the first thing I want to do is just find out. So I just want to find out how many of each thing there are. Okay? Makes sense? So this is now not bothering to compute. This is only computing the causal connection summaries. I just want to see what kind of exotic things occur. And I believe index graph will allow us to, will cause them to, it doesn't matter what the labels are. That is profoundly boring, right? So that's saying, oh, I see. Oh, that's kind of an amusing one. Okay, so these are the cases. Right?
Oh, that's, yeah, black hole in an expanding universe.
Yes.
Cool.
Okay, so what we have here.
You maybe go to higher level than 4.
Well, okay, hold on. Let's just, first of all, there's a really very basic thing here, which I'm embarrassed to do and recompute everything, but I'm going to do it anyway because we're going to do the next case later. Just so we can see what the heck is going on. Okay, so these are the different cases, and this is out of 4,700 rules. And then we should figure out what's what in a minute. We can get, for each of these, we probably should just get the rules and gather them for each thing. Very boring to watch this. This is where we haven't done very many of these on live streams yet, is hunts. I mean, this is an early hunt. And this is, I mean, often these things have to be left to run for days. But this one should go, I don't know why this one's going slower than before. Okay, there we go. That was all I wanted to do. Okay, so that case there, what is that one? That's probably when the whole thing died out. This case here is the case of 2 disjoint cosmological regions, of which that's fairly common. It's very common to have a universe without black holes in it. Okay, all right. So now you say we should try a different case here. Are you saying, what are you suggesting we try here?
More steps instead of 4 in case black holes didn't have time to form yet.
Okay, and actually we can get rid of this G equals, we don't need this, right? We just need the GS case, correct?
Yes.
There's no reason to compute the causal graph there.
Right.
Okay, so what are you saying? You're saying we try 5 here. Do we want to be as dangerous as to try 8 here?
Or at least maybe even 9.
Let's live really dangerously. Let's put 10 in here. And worst case is it'll time out, right? The time constraint will work through the Wolf model code, right?
Yeah, should.
That sounds like famous last words if I ever heard them.
Well, we could also take a sample of the 47, although it is interesting that we only have a single case where there's this black hole plus cosmological, plus separate part of the universe.
That seems going faster, actually.
That looks more diverse. Ooh. That last thing's kind of cool.
Okay, what the heck is it?
That's 3 nested apparent horizons.
Well, I understand. But okay, so this is 2 black holes, 2 disjoint regions of the universe with black holes in them.
Mm-hmm.
What are these things here? That's 2 black holes.
2 black holes.
Black holes.
Just 2 black holes.
Right.
Ordinary ones.
I don't know why these 3 are different. They probably, oh, I see, they have different labeling because of where in the causal graph, even in the index graph, they work differently. Okay,
Right.
so this is the universe breaks up into separate cosmological pieces. This is and these are various exotic nested black hole solutions.
This is pretty fun, yeah.
It is, yes.
Yeah, we need to find what the rule is.
Yes. Okay, let's do that. Hold on.
And also, can we do canonical graph instead of index graph because they're small, so it should be slow.
Okay, all right, fine. Okay, hold on. Let me just let's write this correctly so that we actually get what the rules are, and then we can go through and pick it out. Okay, canonical graph. You're saying do canonical graph here. And then what we want to do is, instead of saying counts, I want to say gather. So what I want to do here is I want to say framed of this, but I want to say hash, comma that. And then I want to say, and then I want to say gather by. Am I correct? Gather by last. And then I want to say there, let's take the first up to the first 3, okay? Make sense to everybody?
Yeah.
Take hash up to 3. And then comma. Actually, what I want to do is something slightly different. I want to say hash arrow last of hash arrow take that, map that, and then I want to say resource function well, we could also just compute the causal graphs. Well, no, let's do this. Resource function of interactive list selector. Did I get this right? Okay, and let me just, for the hell of it here, just to check that we're getting this right, let's say random sample of this, comma 40 or something, just to do a quick one. That was not a good sign. That just beeped at us.
Yeah,
that is very disappointing. What happened?
So this is the same rules as last time. So if it's a crash and set replace, it will be random one.
Something went wrong here. Okay, so...
Well, it crashed.
Could it have been a parallel map monitored bug?
Well, not a bug, but just these machines are so... I mean, it's crazy.
No, the kernel crashed.
A random little...
So it is a bug.
What's that?
The kernel crashed, so it is a bug. The question is whether it's a bug in set replace or in the kernel.
Okay, let's try it again.
This isn't going to work. Intersection rule isn't defined.
Which rule?
Intersection rule. The function intersection rule is not defined.
Okay. Oh no.
And your parallel kernels have noticed.
Yeah. Okay, where is intersection rule? Let's go back up here.
There you go.
That is a lot of splatting. Look at that thing. And it's still running and it's not going to finish. So let me kill the kernel here. Oh boy. You know, I'm telling you, this when you're running all of these different kernels and things, it's just a frigging wild west of stuff going on.
We should start using the remote submits that Jesse is making.
Well, and have it run on AWS instead of running on on the servers in my house. I mean, what difference?
Well, we will be able to run them on your computers at some point.
Yeah, no, I agree. Okay, so let's try and figure out what happened here.
I think we're okay. We should just be able to rerun this.
All right. Sigh. You know, I think what's happening here, it's making SSH connections and it's going through and the other question is I might want to actually kill off zombie processors on these machines because that's another thing that can happen. Oh, come on. What is going on here? What is going on? This is no different from what we did before, right? Did we do something different here?
No, other than the interactive list selector and the random sample.
I don't understand what this is saying here. This is 0.2 of the way through something which is 48 out of 40. What on earth is going on?
Yeah, that means some of them have crashed. So some parallel kernels have crashed. So it's overcounting because it has to repeat the same computation multiple times.
Is it possible that the other things are just running on those computers and have gone out of control and are burning up the memory of those computers?
It is possible.
All right, let me see if I can run the thing that the emergency kernel extermination system.
The zombie detonator.
Yeah, right. This is one of those. Okay, hold on. Let me go find it. Story local functions. Okay, let's see what this does. Kill rogue kernels. Well, let's see what this is going to do. Kill rogue kernels function. Let's hope it's got the right hosts. All right, let's try it. Oh, here, let's put it in here just for fun. Well, there definitely were rogue kernels. Look at that. Look at all those rogues.
That's a lot of zombies.
Yeah, on those machines. Okay. All right.
I'm wondering, shouldn't these kernels self-terminate if they cannot
Of course,
contact the
they're
original
supposed to. Yes. They when their parent link dies, they should terminate. But unfortunately, operating systems don't do that correctly. It is not our fault. It's an operating system issue because, you know, the thing has lost its parent link, right? So it should terminate.
This is the bane of the theorem prover, or was for a long time.
You're saying because the kernel is computing something else, but it can still periodically check for the parent link. Why?
It's supposed to. I don't know why it doesn't work. Okay. Maybe you can investigate that, Max. Okay, so let's look at this. Let's try running this again. See whether, oh gosh, it's going to start up all the kernels again.
After how much debugging do we lose the efficiency gain of having 100 parallel kernels?
No, that's a good question. It's quite a bit, actually.
Uh-oh.
I don't understand this. This thing is really dying. Okay, it's very dead. All right, I do not understand what's going on here. I mean, it was working just fine before. I think we may have to end this on a cliffhanger because I don't see how to. Oh shoot! We should be able to debug this. Okay, what is going on? First of all, let's run the rogue kernel killer again. So there's still rogue kernels running. No, there were no rogue kernels left running. Okay, a graph object is expected at position 1 in vertex out component of blah. So is there some definition that we haven't made again here?
It might be. Yeah, let's rerun everything and just check.
Can we just run a few cases without parallel kernels?
Right, without stupid parallel kernels. I agree.
Very good call.
Okay. All right, let's try random sample here of like 4 rules. Okay, now let's try this. Okay, that seems to work fine.
That's the only non-trivial.
Is there any possibility that canonical graph is failing on one of these? Like the null graph? No, that seemed to work fine. All right, so let's try here. Let's just look at this. Okay, so let's try replacing parallel map monitored with map here for a moment. And let's just try doing this for 5 cases.
We're all good.
Yep, that looks fine. All right, let's now try starting parallel evaluate of $machine name. Yeah, Richard on our live stream is asking very reasonable questions about why SSH connections aren't persistently kept. I may be wrong about what's going on there. Okay, so we've now created those things. So now let's try. Okay, well, I guess we just try the big thing again because there doesn't seem to be any reason why this shouldn't work. Famous last words. Okay, interactive list selector of. Oh yeah, we know the interactive list selector works because it just worked there.
Yep.
Okay, come on, don't. What the heck is going on here?
That really seems like they're crashing.
State defunct doesn't sound too good.
Wait, did they all crash, including the master kernel?
Yes, everything crashed, including the master kernel.
But it works sequentially. Or maybe it doesn't work for 40 cases. Oh, you're doing random sample. So every time it's a different subset. So it's possible that some of them do crash the kernel and some don't.
No, it's not, because we just ran it before for everything.
It's random sample without a seed.
No. We ran it for the whole collection up here. This is everything. We ran the whole thing here.
Was it the same? Wait, if it's the same code, why are we rerunning it?
Because we want to
were
get
rerunning it
separate
to
lists.
gather instead of counts.
Huh.
Is there any possibility that there's some definition we don't have here?
If there were a definition we didn't have, it would show up on the sequential code.
All right.
Is it possible there's a definition that's not getting propagated down to a parallel kernel?
No, but then
unless it's a function repository function that's not loaded, or
Brian on our live stream says, I could be dead wrong. Maybe
Yes.
parallel map monitored needs some work. Yeah, I mean,
I think that's an understatement.
function repository, not somewhere else.
yeah, when I wrote it originally, I never expected that anybody else would ever use it. So yeah, it does need some work.
Well, let's do this. Do you think we can just not use parallel map monitored? We could just use parallel map. Maybe there's something going wrong. What's so weird here? Let's do this. Let's try to evaluate. I can't imagine why this would make a difference here. Forget the gather by. Just do this. TLDR of this stream, parallel programming is still hard. Well, it usually, yes, it's hard because these stupid machines just, okay, let's try this again.
But the great irony is that one of the reasons, parallel computing could be a lot easier if we make further progress on the physics project.
That's true.
But we have a chicken and egg problem.
What's happening here? Why is this just hanging? Why is it not even, wasn't even starting these kernels? I could also reset this so it's not trying to do it in as many kernels, but I mean, or maybe there's something wrong with a machine called Threadripper. I don't know.
I was going to say, all the glitches seem to be the Threadripper thing.
Oh, for goodness sake.
Yeah, actually, can we just see if that error occurs for any of the things other than Threadripper?
We already died. The master kernel already died. Okay, let's take Threadripper out of the parallelization.
Yeah, I think that's a good plan.
Yeah. Is it possible it has a different version of the kernel or something like this?
It's possible. Yeah, I mean, the distribution of the kernels is not... Yeah, that's possible. Somebody's asking, maybe it's an AMD problem. It might be. It might be that. I mean, this is the Wild West, unfortunately, still. Okay, so let's do a parallel evaluate. Dollar version, well, dollar machine name, dollar version. Let's just see with Threadripper in the picture. Let's see what happens. Let's just see whether they're all the same version. Bit frustrating, we can get as far as black holes, but we can't get as far as no, they're all the same. Well, I mean, okay, that's a Linux machine, but so what?
Wait, they're not the same. Today is different.
What's that?
Well, they're the same as the other one. Not the same
those
as
are slightly
the backup.
That's a little weird that those are different. 12.1.0, but they're all 12.1.0s. So there's nothing trying to run 12.2 or anything weird like that. All right, let us try taking in parallel kernel configuration. And if anybody is paying attention here from our team watching the live stream, could you make a note for Roger that I'm doing this so he can back this out? Remote kernels. We are going to disable Threadripper. Oh, it's 32 cores. So sad. Well, it's going to make this a lot slower, but let's try it again. The other thing that occurs to me is that there might be a problem in the definition distribution to do with the way that this is the sequence of those rules.
Yeah, that seems plausible.
That's a good thing about using Docker, because then everything is guaranteed to be the same.
Okay, let's try this now.
Uh-oh, it begins.
But why is it going to Threadripper? We just
Did you close kernels after removing it?
What is an EYPC? I should get the 64 core version of this. Yeah, I mean, this is a quite new machine as well. What the heck is going on here?
Yeah, Max makes a good point, right? You already launched these kernels. So you have to...
I didn't now. So now we will not get Threadripper. All right, let's try one more time. Okay, local, fine. Why are there only 25? Oh, I know why. Because I don't launch 28. I've got 28 cores on my desktop machine, but I don't launch all of them because otherwise the machine grinds to a halt. Oh, come on.
Wait, local is failing.
Okay, so it's not Threadripper specific.
Not only that, it's also not to do with the distribution of definitions, because local will not require definitions to be redistributed.
Right, something very weird.
Why? It would.
No, it doesn't. It doesn't do that.
It's still a different process.
Oh, that's true. Yeah, you're
Although
right.
it means it wouldn't have anything to do with Packlet installation, anything like that.
Right. It won't be Packlets, and it won't be yeah, this is okay. I'm going to try one more thing. Okay. I'm going to try just restarting the whole shebang here. And then if this doesn't work, I'm afraid it's time for my dinner. Okay. All right, here we go. So sad, we were getting so close. All right, try it one more time. All right, I'm going to just pull this out just for the sake of, so it's repeatable. And I'm going to do something else as well. I'm going to, well, first of all, okay, so with map, we believe this works. Should we try this with map just one time? Let's try it with map, just to see that it works locally. That's going to be really slow, but anyway, let's try it. See, this is the problem with. Okay.
It ran.
No, now it crashed. At the
it's like, I didn't notice.
So essentially, the code with Kazaa crashes and the one without doesn't.
The code what?
So we just used Kazaa and everything else is the same.
No. We didn't even use gathered by here. This crashed.
There was a different compared to the previous one.
Okay, but so now let's do this. All right, let's do this here. And then let us go through here in the map and let us go ahead and echo I mean, it's really weird that it crashed after this. Okay, so I'm going to echo, actually, I'm going to echo each thing as it comes out. It just crashed. It just crashed. So the second one of these caused it to crash.
So what exactly is the difference between this one and the one that worked before?
Well, as you pointed out, there are random rules involved. So it could have been, so let's rerun this. But what's really weird is what could cause it to crash. I'm suspicious about Max's code here, but let's not go there yet. Okay, so let's do this. Now let's echo this before we do that. So we'll see if this crashes, we'll see what the actual, it'll echo that before it echoes. In fact, why don't we go ahead and echo them in sequence there. No, let's echo that. Let's do this. Okay, that crashed. 1, 2, 2, 3. So this one we know crashes.
You can just run Wolfram model with it.
Yeah, I will. Okay, automatic, let's say 10 steps. I have a bad feeling about this, that what's going on. Well, I have a bad feeling, but anyway, lead causal graph. I mean, this might be huge. We may need a time constraint here.
Or it could be trivial.
Yeah, it's trivial. Okay. So now let's run this. Okay, let's evaluate this. And we're computing this quantity, WM causal graph summary at, with that thing. And then, such a shame, we've gotten so far here. Growl. Okay. All right, so now WM causal summary at, let's do this. I predict this is not going to crash. And it didn't. Just produced an empty thing.
It'd be pretty embarrassing if it failed on a 2-event case.
Yeah. Okay.
So what's going wrong?
What about canonical graph of that?
I tried that before, but let's try it.
Can you try a table of hundreds of those? Yeah, and can you do table of hundreds of canonical graph of empty graph? Yeah, that's better.
It crashed.
Good spot.
Okay, can you just do Wolfram model of, just do Wolfram model 100 times, the function above. Because it might be a random bug in set replace.
Oh, you want me to try it again?
Yeah, try it again. Try for 500 without knowing the result.
This is the problem. I mean, just for people's information, the way this works is it has low-level C++ code that it's calling ultimately to do various things. And that's
that returned
directly into the system. What's that?
Did that return? Looks like it returned.
Yeah, it returned.
Okay, now try the line below without canonical graph 50 times.
This is very fun.
Oh, it's very horrifying.
Brian on the live stream points out that this is the cosmic censorship conjecture in action, trying to prevent us from learning about black holes.
What's inside black holes? Yeah.
Yeah.
Well, that could be ultimately.
So it has a long arm.
Okay, so then this. Worked just fine.
Good.
And now map.
Another 50 or 100.
Well, now let's do the canonical graph.
Yeah, can we map canonical graph over that?
Yeah, just canonical graph of an empty graph a bunch of times.
No problem.
That's okay.
I'll try it again. Maybe 50 is not enough.
I crashed.
This is so weird.
It's probably 50, just not enough. Try both of them for 500.
This is what experimental scientists have to deal with all the time. There's things sort of randomly failing like this. And us computational folk usually have it really easy.
Well, we had a bad send and set replace recently where it would crash, but not on master branch, on some other branch. But with CI will still report then it passes because the return code was 0.
What? Because in the continuous integration?
So it crashed, but the return code was 0. Yeah. So CI returned it as passed, all tests passed. And it's good seeing somebody spotted that, because otherwise.
Okay, so that succeeded there. But now the canonical graph case, which has.
Can you just do? Both of them succeeded.
No. I didn't do the canonical graph case.
Yeah, can just do canonical graph of the output only, separately.
Of this one.
Yeah.
Fine. Just worked.
Interesting.
So shall I do this canonical graph thing here?
Well, we know this crashes.
What do you mean we know this crashes? We don't know.
It crashed before.
Yeah, it did.
Well, you can try it again.
You can echo I, see where it crashes.
Yeah, I'm going to monitor this. I. Is that right? Did I get this right? I think I did.
Yeah, that's okay.
See, I think it's crashing at the very end, which is even more bizarre. Like it's crashing when it gives up memory or something.
Yeah, someone on the live stream is saying that they reckon it's a memory leak.
Yeah, but that's the generic. Yes, I agree that's what one would normally. But
But can you check your memory? If you use too much, well, actually on the Mac it shouldn't be a problem because it will just keep using swap until your hard drive.
Yeah, right. And I've got very big configuration here. If I can figure it out.
It
worked this time.
Oh no, and then it crashed.
I told you it crashed at the end.
That's very
weird.
Crashed
at the very end.
So is that some kind of data return issue?
Possibly.
Is it trying to return something to the front end and the front end is freaking out?
No, that's
But
very...
it's not front end, it's a kernel that crashed. Unless it's some kind of weird call to the kernel from the front end at the end. And also we don't return anything because there's a semicolon at the end.
Yeah, right. But I'm wondering if something's still getting passed even though there's no return.
No, the pathway, the code path here is so deep inside its, low level of its brainstem. There's no way this can, okay, this is something weird going on, needless to say. And I think set replace is implicated, but set replace is a library link function, is that correct?
Yes. I don't see how it would be implicated unless it overrides some kernel memory. Well, that could happen. Maybe
Yes,
it overrides kernel memory and nobody notices until until the final step. Given that it's so simple, you could try to
we added the 10 there.
Yeah, that's
we had 10. We already had 10 here.
But it's a good question.
Can you try doing method goes to symbolic in the Wolfram model? Because these graphs are so small, they would be fast enough anyway.
Okay, but the thing that is totally mysterious is this worked just fine up here.
Well, if it's a memory override, that's
no, but it doesn't make sense because it worked just fine here.
Well, yes, it overrides some memory, and then it's a question of memory arrangement of whether it's.
No, it's repeatedly crashing right now.
Well, yes, because it's in a different way of kernel setup. The memory goes to different places.
I understand the claim, but I think that's, that is a hypothesis made to fit the data, so to speak, or whatever. It's a... Okay, let's just think about what is happening here. So, first of all, why would it fail right when it is returning?
You just try Wolfram model method goes to symbolic.
Yeah, I will, but I won't start running that exact same code, just in case there's something that we're missing here. Okay, I think this is going to crash, but I don't know. And so this is the exact same thing, except I think I've re-enabled Threadripper. We're doing the exact Okay, this is much more mysterious. See this? This is working. What did we do wrong here? Something weird is wrong.
Well, yes, we need to try the symbolic case of Wolfram model.
No, but look at this. This is the exact thing we were just trying to do before, and it's working.
Well, almost. But because it does slightly different things, the memory, arranged in a slightly different way.
Well, the only thing I can see that's different is the index graph here.
Yeah. Well, these memory things are very hard to debug.
Of course, but this is what's implicated here is Wolfram model scribbling on kernel memory.
Yes.
Which is very bad and needs to be, hunted down.
And also we should try to do it without resource function because it changed slightly since then.
Okay. Ooh, that's interesting. Look at that. That's different. That's not what we got before. That's kind of weird. So there are 42 cases there where, okay, but otherwise that looked the same. So just for the hell of it, let's try and do this without the counts so that we could then do the gathering, because this should just work. And let's not worry about the index graph versus canonical graph because I want to have my dinner. And then this should be that, gather by last. And this is all okay. Okay, do you think it's correct? The gather by wait a minute, what did we do here? This is oh, drat. You see what I did wrong here? I didn't keep the rule here. I have to redo this. See that? This should be hash like that because I didn't keep what the rule was. Okay, I cannot imagine. Why is this different? Why is this behaving okay and the other one was not? I mean,
Well, it's index graph, not canonical graph.
I know that. But why canonical graph? I mean, so canonical graph must be interacting with some memory scribbling on the part of...
Yeah, that would be my guess.
That is really wild.
Well, this thing is atypically wild.
Okay. I don't know why this is slow.
It's just a lot of stuff.
Oh, well, what did we do? We gathered the wrong thing here. Somehow this went wrong. Oh, maybe those are distinct index graphs?
Yeah, that could happen. Right? That's why we used canonical graph.
No, but I think there's something else going on here. This is, okay, hold on. I think we just have a trivial bug in this code here. What we've got here, before we do the gather by, is let's just take %12, -5, for example. Okay, so here are those, and we've got rules, and we're saying gather by well, we could say, am I right that we should be doing gather by of last here? Because that's what counts will do the same thing that gather by would do.
Wait, is it last or is it last of last?
No, each one of those is just a single
Fine. Yep.
thing there. Oh, I did something much stupider than that. That is embarrassing. That is embarrassing. Look what I did. Look what I did. I put the framed around the whole thing.
Yeah, but that's what I'm asking. So the part specification should be able to... The framed is just the head, presumably, right?
I know that, but let's get rid of that because that was goofy. Because that should have been just for the graph there.
Right, but that shouldn't mess up the last.
Yes, it should. It was picking the last, as you say. It should have been the last of the last.
Yeah. Okay. Right. That makes sense.
Okay, come on, don't crash. Very good. Okay, here we go. Thought I'd asked it to take up to 3. Oh, I see. These ones only have 1. Okay, so these are samples of different cases with different... Okay, so should we look at...
I want to see the 3 nested apparent horizons case.
This one here.
That's a cool one, yeah.
Okay. So this one Oh, actually, you know what I was doing here? Oh, I see. This is first of that. Oh, I did this stupid thing there. Never mind. It doesn't
If we're
matter.
outputting the rule, do we need to have the interactive selector?
No, because I shouldn't have been outputting the rule.
Right.
Okay. Because what I was actually doing here, this is completely goofy, but that's okay. That's okay. All right, so we have this rule, and let's go ahead and look at its causal graph. So this should be this rule, automatic. What were we doing? 10 steps and layered causal graph, right? What the heck is that doing?
That makes sense.
And what way does that make sense? You're saying there are 3 black... Where are the black holes here?
So the part to the right is normal space because it's all connected.
Right.
But the left ones are unreachable.
Oh, I see. I see. So this is actually a cool...
This is very Penrosian, yeah.
Really cool rule because it has a very simple Minkowski-like structure here.
What does a state look like?
Yeah, what does a state look like? Good question.
It's presumably going to be manifoldy, right?
Well, let's see. States.
Plots list. Ah. Amazing.
What the heck is this? What is this? Okay, so let's understand what's happening here. So this is Minkowski space, basically. That circular region is something with a simple back and forth causal connectivity.
Right. And then each one of those threads is a black hole-y thing.
But why aren't we seeing more black holes here then?
Well, because we only went up to 5 steps, remember?
What do you mean?
No, but this causal graph has more than that.
Yes, but our detector only went up to 5. The initial only went up to 5.
So
we only have the states in the 5th thing there.
Well, this causal graph only has 3 also.
Let's just see what happens if we go to like 25 steps in the causal graph. So it's gonna look very, it's gonna look very much like that.
Right. So presumably, if we change the 5 to a 10 or something, we'd see a lot more.
So it has a generator on the left, which produces something.
Yes, but that causal graph. So in this thing here, what we're basically seeing is, this is a nice example, actually. I mean, there's sort of the ordinary universe, and then it's extruding black holes here. But why is it doing that hierarchically?
No, there's only one. There are a finite number of black holes. So those branches are not black holes.
Why not?
Well, because we only got 3 of those.
No, but that's because we only went to 5 steps.
Okay, can you try more steps?
What's that?
Can you try more steps?
Yeah.
I predict it's not going to increase so very much.
Okay, so you say let's try 7 steps and 10.
7 and 14 probably, so that goes far enough.
Wait a second, why did this give that?
You need more than 10.
No, but I don't understand why this rule... Okay, well, let's try 14 there. Oh yeah, okay.
There you go.
Well, let's try this going out to like 20 and check that doesn't change.
Right, so it's not more black holes, it's the same number of black holes. Because black holes are things on the left.
Yeah. You're right.
Okay, then I don't understand where they are in space-time. So explain that. So hold on.
You mean in space?
So there seems to be a branch that produces something. which is different.
Okay, so let's go ahead and do this. Okay, so what appears to be happening is that these seem to not change as we increase above 20 steps. And this seems to not change as we increase t above about 5 steps, right?
Right.
So let's go back up here, try to understand in space-time what's going on.
You mean in space?
Space, yes. What other...
What's that thing coming off that big thread?
What were you looking up here?
No, I mean any of the late time ones. There's a single filament that's longer than all the others, and it has a protuberance.
Right.
Unlike all of the others.
Let's go investigate the protuberance. Okay, so let's go get that thing. Let me just get the graph, because this is just.
Isn't it a double edge?
Oh, let's find out. Okay, so let's say final state here, and then let's say graph. Can you do this directly, Max, in the code now?
Return graph? No,
Yeah.
you can't.
Okay, so there it is. So let's look at the 3D version of that. By the way, we should have this.
Yes, I reckon that protuberance is what's yielding these 3 black holes that Max is saying exist on the left of the causal diagram.
Yeah.
Okay, so hold on. Oops. Lag. So wait a second. This is where we need the VR system. Okay, so
that thing there.
Well, look at what's happening at the end of that. Look at that. Look at that. All these other ones have an outgoing arrow.
Yeah, but there's one where it's bidirectional.
Yeah, so that's a
what does that
source
mean?
of some kind.
But look at these here. Okay, so these here. Look.
Okay, my guess would be that the other branches don't evolve. They just get produced in the circle and go outwards. But this one probably does something there.
Yeah, but
Like
why?
go in the circles.
Look, what's happening is in this circle, there are these outgoing. There are these things that are outgoing. Each one of these is an outgoing piece, right? That one has an outgoing piece. All the other tentacles are pure. I don't mean outgoing. There has a divergence basically. From
Right.
that point,
All the others just go in the direction of the filament.
yes, but this is also a generator in some way. So let's look at that. If we look up here,
Can we check where the events are?
how do we do
The
that?
event states plot list.
What should I do?
So it's event states plots list. And then, it'll be a bit inefficient, but we have to do it for...
Okay, how do I do that? To 10 events?
So it would do each event, not every generation. So 10 might be too much.
3.
Well, let's start with 3, okay. So you need more than 3. I think it's too much. Oh, okay. So now we can see where is it updating.
So wait a minute. It's extruding these hairs.
And it from time to time it does do something. It's a protuberance over there. You can see.
Yeah.
Wait a minute. So what's happening here? So this. The main circle. By the way, we could try a different initial condition and see what happens. So many of the events are on the main circle, but some are in that particular filament. Is that true?
Looks like it.
Yeah.
But yeah, this does look like something that's going to be fairly initial condition dependent.
Well, it's also the case that in a sense, these hairs, I don't quite understand these hairs, but I think they're growing the same way that hairs, for those of us who still have hair that grows on their heads, so to speak, grows in the sense it's the base that grows, right?
Yeah, so it seems what's happening is that, so this thing, one of them is long and it has a structure which is also growing.
Mm-hmm.
So presumably that's why it has, because something, let's see. Yeah, I guess you need to start there and then you go to the main circle and you get into this grid in the causal graph. But you can't
Where's
go
the
back.
grid? The grid is from the main circle. Is that what you think?
I guess, because it's growing.
Let's do the following. Let's make the main circle. Let's make the initial condition instead of automatic here. Let's make the initial condition. Let's just try the first sort of trivial thing, which is to make the initial condition 2. So right now we'll have, let's make it a square. Okay, 1, 2, 2, 3, 3, 4, 4, 1. Am I right? This may be very dangerous. Let's see. Let's ratchet that down a bit. Oh, great. No growth.
1, 2, 3 wouldn't match to that.
Right.
The ones go in opposite directions.
Okay, all right, fine. So forget that.
Just reverse 2 of them. So do 1, 2, 3, 2, and then 3, 4, 1, 4.
It's a harmonic oscillator.
Or a shield ladder or something. More like a shield ladder, right? Because it's in the causal graph.
Mm-hmm.
Okay, but let's try looking here at if we do just a 0, 0, let's do like 8 of those or something. Oh my gosh. I suspected this. This is in the, so I predict that in the spatial graph, this is going to end up being a higher dimensional spatial graph. And then there's a question of what does the black hole structure of this thing look like, which we can find out in just a moment here. Let's be a little bit more conservative there. I see. Oh no, okay, so it's basically just a multi-looped creature.
Yeah, it's still one-dimensional, but just more hairy.
Well, it's got more sort of compartments in there. Okay, so let's try this thing with, where was it? Where was our actual black hole detector? Here we go. So, what do you reckon? I reckon it's going to have many more black holes in that structure.
Yeah, because you can see there are a bunch of filaments that have many protuberances on them.
So it's going to have much more nesting in the structure.
Yeah.
Oops.
Or not.
Oops.
Interesting.
We are wrong. All right, let's try as a function.
Can we run that for a later initial time?
Later initial time.
Yeah, like 12 or something.
Sorry.
Interesting.
Okay, so let's try initial time 7 here, and let's try as a function of 8, so to speak.
Oh, but does it have this protuberance in there?
I thought that's what those, you see that big filament on the right? I thought that's what those subfilaments were, but maybe they're not.
No, well, I think we have to look at what that graph looks like.
Huh.
Oh boy. That's not what I expected at all. So this means the universe is staying completely connected here, but in these cases it's forming these weird nested black holes. The automatic initial condition just does 2, 0. It's the minimal initial condition that makes this grow, which is the left-hand side with all the element names numbers to 0. All right, just because I'm curious, I just want to do this up to, let's say, 15 or something, and I want to, let's just make that 25. And we should be using parallelism here because this is very inefficient. Oh, come on. Oh, there we go. Was it there before?
No. It was because we ran to a later time. I'm not convinced by many of these single dot ones.
You think that they're really going to break up?
I don't know. Maybe I'm wrong.
Well, let's look at the 3 case, which I think is the simplest case here. So let's look at that case in particular. So let's look at the causal graph for that case. Okay, that's already kind of messy thing.
But it doesn't have those obvious 3 things that Max pointed out on the last one. It looks very connected.
It does look very, very connected. So let's go.
Maybe it's right. Maybe it's right.
So this is saying, at least with this updating order, and I mean, we could also look at the multi-way graph for this stuff, but although that's more exotic. I mean, that also is interesting because, if the multi-way graph is different, that's saying that there will be a black hole on some branches of the multi-way causal graph and not on other ones, which is itself quite interesting. What is the interpretation of that? In other words, if there's a black hole that forms, if you look at one slice of the multi-way causal graph, but not on another slice of the multi-way causal graph, what does it mean? It means one place in quantum space.
What's weird about it?
I'm afraid my dinner is going to be cold if I leave it much longer here. Just terrible. That's terrible. This can affect the fate of black holes in the universe.
You should get some Soylent, Steven, then you don't have to stop doing physics to have dinner.
All right, hold on. I really want to go on with this a little bit. So let's okay, so we're trying to understand this one here. So this is a connected universe in the end, right? So unlike this one, we claim, so in this case here, let's go to this. For some reason, that one is connected, but then this one, if we go for the triple case here, it looks so identical to that other one. Okay, graph 3D of that. What the heck is going on here? I don't know what's happening. Well, okay, we can also do let's do the evolution events, whatever it is, plot for this case. What is it called, Max?
Wait, what's called?
Isn't it events states plots list?
Yeah, events states plots list. Which makes me wonder if you have the same scene but one generation at a time.
What are you asking? What are you saying?
That would be useful.
It would be useful to have the one which would just combine every generation.
Yes, to show the event, all events at a particular generation.
Yeah.
So what is this doing? Well, for some reason, this doesn't get stuck. All right, are we going to keep going for a little bit? I'll be right back. Sorry, guys. Keep everybody entertained, guys. I'll be right back.
Is Stephen going to speed eat or? Is he going to come back chewing?
It's possible that either of those may happen. But Jonathan, you could probably take a look at some of the Twitch chat questions.
Okay, yeah, let's do it. Black hole refrigerator to keep your dinner cold from Salmon Hugh. Well, the universe invented microwaves. Yep, okay, all good points. How many people were involved in coding this framework? So it's mostly Max, right? The set replace framework was entirely developed by Max. And then all of the other functionality was developed jointly with between Max, myself, and Stephen, I think.
Up to the point that we had Wolfram on the function repository, it was mostly me. But now we have some other contributions to set replace.
Right.
It's optimizing C++ code.
Right. But then there are a bunch of the multi-way system framework and all the helper functions and all of that, and that's all collaborative. Could you imagine in 10 years a 5th grade science fair, a kid who wants to looked into this physics project has a library of black hole structures for their project? That is going to be fun. These would be excellent for like science fair projects because they're very visually appealing. It looks like part of a Penrose diagram horizon boundary. Yes, it does. The previous thing that we showed definitely does look like a Penrose diagram for some kind of, for a black hole, but not for an event, not for a cosmic event horizon. Okay, here are a lot of memory leak suggestions. Cosmic censorship, Threadripper, people throwing shade on parallel map monitored, which, yeah. How does the cosmological event horizons and black hole graphs differ? Okay, so yeah, we've mentioned this a couple of times. So the cosmological case shows up as a complete disconnection in the causal graph. The black hole case shows up as basically monotonic directions for causal edges. So if you have a region of the causal graph where there are causal edges going in but not coming out, that's the black hole case. So they're both versions of causal disconnection, but kind of the cosmic case is somehow stronger than the black hole case. And as Max says, this is effectively the difference between strongly and weakly connected components. How does the apparent cosmic horizon and UNRRA effect fit into this discussion? That is an interesting question. So the UNRRA effect, okay, for those of you who don't know, is basically, it's the analog of sort of Hawking radiation that occurs in accelerating reference frames. So the idea is kind of, if you are moving very quickly, if you're moving at relativistic velocities, then you will kind of observe, you will observe heat that someone who is in a rest frame would not observe, because as a consequence of your accelerating reference frame, you're effectively producing some kind of apparent horizon, and that apparent horizon will have an effect that's like Hawking radiation. We should be able to see this in our models, right? So once we have and we're planning to do a sort of a live stream reasonably soon about kind of quantum effect. Once we're further along with this black hole stuff, we want to do a live stream about quantum effects around black holes, and in particular, we want to investigate Hawking radiation, which we think emerges when you have disconnections not just in the space-time causal graph, but in the multi-way causal graph, where suddenly you can have branch pairs which are no longer causally connected. And so one element of the branch pair can effectively escape from the black hole, and we think that's the analog of Hawking radiation. And if that's correct, we should be able to see the analog of the UNRRA effect, because effectively if you slice the multi-way causal graph at a particularly steep angle, you will also be able to have branch pairs which exist on one side of the slice, but a branch pair at the slice where one element exists on one side of the slice and another element exists on the other side, and that would be sort of the analog of the UNRRA effect. And we're looking forward to seeing things like that. That's a great question. How many orders of magnitude above the causal graph do you need to be to see an electron? This is a good question, and one probably for Stephen. I think he was talking, Max, do you remember the estimates Stephen came up with for electron sizes? They were huge. I mean, we're talking like 10 to the, I don't even know, 50 plus nodes. I can't even remember. Do you?
Yeah, I don't really remember.
It's a lot. But those estimates they're in Stephen's tech paper, but they were achieved by very crude dimensional analysis techniques that I'm not sure any of us completely believe. So the answer is we don't know, but we have reason to suspect that it's a lot of nodes. That effectively the underlying hypergraph dynamics are occurring at a much, much smaller length scale than anything like we conventionally see in particle physics.
Here I'm back with the partial eaten. I have more food to eat, but
perfect.
I was somebody was asking about electron size. I think it's about 10 to the 30th nodes was a.
Was it 10 to the 30th? Okay.
But, and by the way, you're talking about branch pairs, and what we're looking at here is space-time causal graphs, and it will be really. I mean, what we were hoping to do is be able to see the entanglement horizon as well as the space, as well as the causal horizon.
Right.
And I mean, this is because we could actually work out the multi-way causal graph for this very rule, could we not?
Mm-hmm. Yep.
I mean, we may be, okay, so we have some slight confusions here about when it has various kinds of, how many black holes. I mean, this rule may not be the simplest one in which to look for a black hole, but this is because it has this nested black hole structure. But just for, we could look at, let's look at the multi-way causal graph for this rule, for this case, right? So that's the ordinary causal graph. Should we look at a simpler one with a sort of simpler black hole? Let's pick what's your favorite simplest black hole? I think the simplest black hole we have here, what about this guy here? That looks like a minimal black hole case. Do you agree?
Sure.
Well, I mean, that's what we should see. So let's look at. We think this is a minimal black hole. So let's go down here. So because I mean, what we really want to see is this thing. Okay, so now let's get the causal graph. Gosh, I'm doing a lot of scrolling here. Okay. So the causal graph for this should show sort of the rest of the universe and then the piece that is the black hole piece. Oh, wow, that's complicated. For something that had that simple of a causal connection graph. Gosh. Okay, so let's try to understand the causal connection graph for this thing. Just to check that we're not making a mistake there.
Oh, the piece on the left seems to be a black hole.
Okay, hold on. Why are you saying that? Let's see. Oh, because it has, this is cool. Has a bunch of stuff flowing into that, but not flowing out, is what you're claiming.
Right.
Okay, so let's take this rule and...
Yeah, that's actually really neat.
Okay, so let's go 7 steps, 25. So that only got, that was the universe on its own, so to speak. So here, let's try going 10 steps. This is a bit suspicious. Did I get the wrong rule? No.
What about 4 to 15? Maybe it connects afterwards.
Yeah.
Well, what
about
what was
10?
the parameter value that we used before? Was it 5 to 10?
There we go.
Whew.
Yeah. So let's see if that. So if we do 5 to 15, does it reconnect?
Actually, if you look at it, you can see that it does reconnect because there is one. Although actually, no, never mind.
There's a thing at the bottom where it looks like it might reconnect, but I can't see which direction the arrows are going in.
No, it still goes to the left.
Does it? Okay.
Well, I think we have a black hole there, formed at time step 5.
Yeah, but why it disappears after that? Can you check at which step does it disappear?
No, so what's the interpretation of the thing then disappears by step, let's try step 6. Yeah, I don't understand that. What does that mean? So at step 5, there's a part of the universe that has only a one-way causal connection to another part of the universe. But later, that's not what's going on. explain. Okay, shall I indicate where step 5 is on this?
That would be very useful. Yep.
All right, so let's take this layered causal graph. Let's call it.
Step 5 only has 2 vertices in it.
Okay, how do we get to step 5? We say out component, vertex out component. What should we do here?
No, not really.
Okay, what should we do to get to step 5? It's a layered causal graph, so it should be the case that this thing...
Okay, I'll have to look it up. No, you have to use proper to the Wolfram model. It's not that trivial.
Sorry, can you show me the causal graph again?
Yeah.
The big...
It isn't layered in that 5. It doesn't mean actually layer 5. I mean, it's like 1, 2, 3, 4, 5 down here.
Yeah, hang on, there is. Am I misreading that arrow? The thing I was indicating earlier, that is an edge coming out.
From what to what?
From the interior to the exterior. Can I see it bigger, please?
That's not the exterior, because you can just include this vertex to the interior as well. If you're talking on the bottommost layer...
Well, it's on the penultimate layer. On the penultimate layer on the left, there's an edge coming out.
To where?
To the exterior of the black hole.
I don't think it's... Why do you think it's exterior? Well, maybe it is. Can you plot actually 16 layers instead of 15?
I think that's an outgoing connection. Yeah.
Which means what?
It reconnects. So it's only an apparent horizon, which, fair enough.
Well, so this is, okay.
But it still doesn't explain why it appears at level 4. Oh, 5.
Okay, well, so anyway, this one is not a convincing black hole. So let's go back and
No, but it's a good example of an apparent horizon.
You know, I still survives for a certain amount of time.
Right.
Well, so that is interesting. I mean, clearly, what we imagine with Hawking radiation is that, is this what we expect is going to look like when we have Hawking radiation? Or are we going to, in other words, if we project the multi-way causal graph into some particular, updating order, isn't this what we would expect to see happen?
Well, yeah.
So there may be a different updating order. I mean, I think this is not a clean enough black hole that it's worth looking at the multi-way graph for this. What do you think? I think it's going to be a mess. I think it's going to be hard to understand. I think we should pick a simpler case.
We can just see it anyway, just for fun.
I agree that it's a temporary black hole, but it is there for a different reason than we think, because at the level 5, it doesn't appear yet. And it already disappears by level 20. So the 2 vertex graph you see there, it's not because of this black hole, because of something else.
I don't understand what you're saying. You're saying that the
If you look at level 5, it's too early. This black hole didn't form yet at that level.
Yes.
So it's something else going on.
What's wrong with that? I mean, black holes don't instantly form at the beginning of the universe. I mean, they're black holes. The universe might be born with some black holes.
Yeah, but we are computing it at level 5. And we will get in a 2 vertex graph.
Oh, you're saying it hasn't formed by level 5?
Yeah,
I don't know how you can
but we are still getting it.
I don't understand how you can tell that. It depends on the future light cones of all those pieces. But, okay, but let's go back. Okay, you want to compute the multi-way causal graph. Let's go ahead and do that.
Well, because you can go to this black hole from both vertices in level 5. You can just check that. Yeah, if you go to level 5.
Yeah, level 5
is literally
here.
Level 5 in here.
Yeah, those two.
Yeah. You can go to black hole on the left from both of them.
I don't see that. Oh, you mean through?
Well, just go down and then keep going left as much as you can.
Yeah, that one does seem to go there. I mean, it seems to go down through this. This is confusing and probably should be checked. But let's just take a look, just to get a comparison of what happens in the multi-way system.
Can you go to 20 levels and see if there's another black hole somewhere?
All right. It's going to get very big at level 20. Let's go to level 20. Can I use oops, level 20. Let me use an aspect ratio here. Oh, can you understand that?
Not particularly.
Good, because I can't either. So. Okay, let's look at the multi-way system just for a moment. All right, so we got this. Jonathan, can I say Wolfram model arrow this, is that correct?
Yep.
Okay.
That should be in a list.
What?
That should be in a list.
This one here.
Well, actually both, but yes. No. I mean, the rule should be, because otherwise it doesn't know which thing the arrow is applying to. There's an arrow precedence.
Okay.
Ambiguity.
Okay, 2 steps, and then we say states graph, right?
Okay.
States graph structure. Yes. Okay, that wasn't very exciting.
The ever thrilling.
What the heck does that mean?
Oh, that's only 3 events.
Right. I mean, this looks like a fairly standard multi-way system. Can we see the causal graph?
Oh, I see. This is the multi-way system. Let's go to 5 steps.
That's already.
It might even have some causal invariance to it, but let's. Okay, so you're saying causal graph structure, and then I want to see the branchial graph. Okay, can you read that? I mean,
no.
Okay, let's look at the branchial graph.
But actually, look to the left of that causal graph.
Yeah.
That looks like the H event horizon.
You mean where it's going? So if I look at this causal graph, and I make a simple graph here, which is not necessarily, well, actually, if we look at causal graph instances, that will show us the complete. Well, you're saying there are things that go into that side.
I think we really need more steps than this, because last layer will always be a black hole.
No, right.
Okay, now notice the branchial graph here, which has...
Why are we plotting the branchial graph?
Why are we looking at it?
Yeah.
Well, it has disconnected pieces. If there's an entanglement horizon, it better show up in the branchial graph.
Yeah, sure. But we can see that there's an entanglement horizon because there's that.
Where can we see the entanglement horizon?
In the multi-way, in the states plot thing.
Because of this coming off there.
Right.
Right.
Yeah. Can we see a few more steps in the causal graph?
Potentially. I think it's very dangerous. How many more would you like? I'm going to go.
No, let's try. Oh my god.
Well, maybe 6 would have been safer. But what we're getting here, I mean, look, the main point here, again, I think this is a fairly complicated example, and I think we should look for some simpler examples which are more kind of minimalist. But I think one of the things that is, an important kind of meta point is kind of the notion of just a simple black hole horizon. We're going to see a lot more exotic stuff happening here. And, a simple black hole horizon is probably not going to be sort of the whole story. Again, what do you think is going to happen in the case of Hawking radiation? There will be some slices of the multi-way causal graph that should reconnect, right? There'll be causal, because there exist. Do you get what I'm saying? In other words, the fact that there's supposed to be causal disconnection, probably what will be seen is causal disconnection on a certain, okay, there we go. Okay, what would you like to see about this? Well, let's make this layered at least. Well, it's interesting.
Can we do simple graph?
Yeah.
We know that's a plot. Do simple graph of %69.
Not very, we don't yet know how to read these things.
Wait, hang on. But those two things on the left, those terminate. Those events don't connect to the rest of the system.
Actually, terminates. They might just be the last layer.
Yeah, I agree. I don't think we know how to read these yet. I think we should look back.
Well, we can easily find out, right? We can just include step numbers and then layer it. I'm not convinced. That's the same combinatorial structure that we saw above for 5 time steps, and it hasn't changed. So I suspect that's
right, how do we get the?
You see what I mean, right?
Yeah.
Look, that structure on the left looks the same as the structure on the left for the 5-step case. It doesn't look as though it's evolved.
Okay, let's look at the 6-step case, and we'll include step numbers. How do we do that?
Include step numbers gets to true.
And then how do I do the rendering?
Hang on. Did I forget what it's actually called? Does it include step number?
Seems to be happier. Okay. Yeah. What's that telling us?
Well, so now so it's now layered by step number. So it's become harder to read.
Yeah, a simple graph may be easier. And who knows whether it flipped itself around and so on. There's some vague evidence that there's flow in this direction that isn't being, that doesn't have a backflow. But I'm not sure if that's correct. Let's just, for comparison, I just want to look at something with a cosmological event horizon.
That should be easier to spot.
Okay, what would you like to pick? Should we pick the one with how many sub-universes do you want?
If we pick 4, that should at least be easy to identify. But I don't know.
All right, fine. And then these ones here would be interesting. The 2 black hole cases also interesting.
Right. But I agree. I think. Yeah. Okay. This has basically convinced me that I need to get my act together on implementing the space-like and branch-like separated highlighting for multi-way system, because it occurs to me in the black hole case, it's impossible to know, right? Because there could be branch-like causal edges coming out of the causal horizon.
Yes.
So
Right, and that's the interesting case, because that's the case where we can see quantum information basically flowing differently from the causal edges and so on.
Exactly. Right.
And then we want to see the comparison of the branchial graph up. Oh, that was 16 steps already. Okay. So that is...
oh yeah, look, those are disconnections. Are they?
Yes, yes, they're disconnections. This is a fractal, this is a weird fractaloid universe.
Yeah.
So we should be able to see that. Let's see. Okay, so yeah, these pieces are all disconnected. So this is a fractal universe. I wonder what its spatial graph looks like. And then I want to see the case for the two black holes and the let's see, let's go. States, plots, list, right? See how trivial or not this is. Can't be that. Oh. Oh, well, that's why, because it is.
It's a fractal.
Well, that's why it's a fractal. It's because the actual universe breaks up.
Yeah, that's the most extreme case of a cosmic horizon. There are multiple spaces.
Right. So we probably will see, I mean, arguably up here, wherever it was, here, we should just pick out, well, let's look at this. Let's just look at this two black hole case, and I unfortunately really have to go soon because I've got another meeting at 8 my time, and Jonathan is to be commended because what time is it for you?
It's almost 1 a.m.
Oh well,
we've done worse.
Yes, we've done much worse. Okay, so this one is a two black holes question mark.
By the way, can we not see the multi-way causal graph for this case? I thought that was what we were...
Oh, for the cosmological case?
Yeah, because I want to see if... Because I reckon that's going to be easier to identify.
Yeah, so I think it's going to be lots of identical pieces. I mean, as we... Oh, we'll see. Okay, so...
What do you mean? No, I want to see whether we actually observe this point about disconnection in the causal graph implies disconnection in the multi-way
This is
causal
claimed
graph.
to be two black holes. This is something which says it goes, there's an initial...
Oh, yeah, look. So they're like initially black hole event horizons, but they become cosmological ones. Because if you look, there are two events going in to the right and two events going into the left.
Yes.
So it behaves for at least 2 steps or 3 steps. It behaves... 3 steps. It behaves like a black hole event horizon, and then it just becomes a cosmic one.
I'm telling you, there's a lot more variety in these horizons, which is why space tunnels might be a thing. Because there's more variety to the weird kinds of singularities that you can get in, in these kinds of models than there is in traditional general relativity. Okay, so this breaks up again. This is again spatially disconnected. Not particularly. So this is, this is a deeply cosmological event horizon, so to speak, because the actual structure of space is disconnected, which is something that cannot happen in general relativity. Correct?
Well, you can formulate things that have, that are disjoint unions of space-like hyperspace.
I understand. On manifolds, if you build the manifold that way, with the topology that way, but it can't spontaneously happen. I mean, the manifold is stuck with whatever the manifold is, I think.
Right.
Okay.
Can we see the multi-way event, the multi-way causal? Yeah.
Yep. For this cosmological... Let's not live that dangerously. Let's just do 3 there. Okay. I'm convinced we can do 6. Maybe. Wake up. I thought we could do 6.
This is a strong argument for the local multi-way system.
Wow. We were doing 3 before, right?
Right.
Up, there we go.
Oh my gosh.
Okay. Interpret. So I think the fact that there are so many, I mean, these are basically, I mean, this is just events that happen separately in different spatial graph components, I think. The fact that there are many parallel lines here is just the fact that things can happen independently in each component.
Right.
But I don't know what this is at all.
And it's not disconnecting, or at least after 5 events, it's not disconnecting.
Yeah, I understand. But then...
But who knows what will happen for... I mean.
Well, there's more to understand. I mean, you know, and we didn't even get a chance to look at what I was hoping we would be able to see is something about no hair theorems for black holes, but we haven't had a clean enough black hole to be able to see that. We're seeing causal edges going into the black hole. What we want to be able to see after that is that somehow, well, it's a little unclear to me. I mean, the no hair statement must be that there's a certain number of causal edges in the black hole and that's all it's ever going to get, unless more stuff falls into it, which is almost a trivial statement.
I'm not sure it's quite that, because I mean the no hair theorem doesn't tell you about what's going on inside. It just says from an external observer, the black hole can only have a certain class of parameters associated with it. So it's more a statement of, you know, microstates that have gone past the causal horizon are inaccessible to the outside, which is trivially true because that's the definition we're using. But it is somehow stating that there are still features of what's on the interior that we can infer from the external bulk geometry of the causal graph. So in particular, things like angular momentum, you know, our angular momentum construction should still be possible, even though the associated microstates are inaccessible.
But I mean, when the causal graph, it's hard to know how we detect things because we've got causal edges going into the black hole. How do we detect things? How do we detect the properties of the black hole? Look, in the physical case, we would expect that the structure of the spatial graph would be affected by the presence of the black hole because the black hole has lots of T mu nu associated with it.
Right.
And the point is that its effect on the outside of the spatial graph is only as a result of the integral of its T mu nu, so to speak, not the distribution and so on. That would be the claim. So we should be able to see that in, you know, once we can identify a black hole, we should be able to see that in the, you know, in the structure of the spatial graph and in the structure of geodesic balls near the black hole.
Yeah, that's what I'm saying, that there should be features of the bulk, you know, combinatorial properties of the causal graph that allow you to infer certain things about the other side of the event horizon, even though there are no outgoing causal edges.
Right. I unfortunately have to go to something else. This has been good as usual. Sorry, a bit of a cliffhanger. No, it's not really a cliffhanger. You know, it's a cliffhanger would be. I'm going to make a ridiculous joke. I mean, a cliffhanger is like you're hanging on the side of a cliff. At this point, we have a much more dramatic thing, which is the event horizon. And the question is, you know, it's where there are tidal forces as well as just the straight force of gravity. Anyway, never mind. It didn't quite work. All right. Well, all right. To be continued. I think tomorrow we are going to look at. I have just look. Oh, tomorrow we're going to look at Bell's inequalities again, and
Properly this time.
yeah. Well, this time we're really going to focus on Bell's inequalities. I think we're yeah. Well, great. Well, thanks to everybody for joining us on the live stream, and more about black holes soon. So, see you all later, and see you, Jonathan and Max and Jose and so on. Okay, bye-bye. Okay, hello everyone. So today we are about to start a working session working on our physics project, and the goal for today is finding more about black holes and trying to find things about the fine structure of black holes. I just posted a big blog about kind of what's been happening in the first couple of weeks of our physics project, some of the science that we've been doing, and some of the other things that are going on. I just want to point out for people who are interested, you can find, let's see, I can bring this up. Let's go ahead and bring it up here. Just to sort of go through a little bit, we'll be having, by the way, a general Q&A about the project on Thursday, which people are invited to, and I'll be sort of responding to, talking about some of the things that are in this post, then talking about the real-time science that we've been doing, like the thing we're doing today, talking about our summer school, which is approaching rapidly and which we're very excited about, and we are encouraging people to apply. We've been doing the summer school now for 17 years. This is the first time that it will be done as a remote digital experience that has the advantage that it's easier for more people to attend. We will be having, the primary summer school is 3 weeks long, and the focus is on doing an original project. The summer school has mostly covered general science and technology. This year we are adding a fundamental physics track, and there's sort of a 3-week period when people are expected to do an original project. Then we're adding a week 0 for people interested in the fundamental physics project that will be primarily oriented towards lectures, getting people up to speed on what we've already figured out about the physics project. So people will be able to come to that first lecture week independent of the 3 weeks that is the project time. It will also be possible. I'm fully expecting that during that 3-week project time, we'll get a lot of probably quite important low-hanging fruit picked in connection with the physics project. We'll be there trying to help people do that. Okay, people are asking on the live stream here, what's the community response to this project been so far? I would say excellent. I mean, I think it's a complicated picture, but I would say that I can talk about this more on Thursday, but I would say that the number of really great applicants for our summer school, who are people who are at the right stage in their careers to really jump into something and do real work and do important things, has been terrific. I would say that in terms of the sort of the old guard of our field, many of them friends of mine from when I did physics 40 years ago, and they've stayed friends all that time. The old guard is definitely moving in the right direction, but I would say that it's these things. If there was a complete sort of pivot in 2 weeks, it will be a totally remarkable thing, and it's moving in the right direction, and I'm actually very pleased with it. Okay, all right. I think we should let's see. I was waiting for Jonathan to also show up, a important partner in the effort to find black holes. Is he here yet? Okay. Well, let me just say a few other things about what's going on with the project, just as a sort of update. We just started a new Twitter stream, Wolfram Physics, which will be sort of making more granular announcements, for example, about these live streams and the things we figure out in these live streams. That's something that's happening. We're also going to, this blog post kind of summarizes some of the things that have come up in our live streams. And needless to say, as I was writing this post, which ended up being quite long, I figured out more things, and I was really trying to restrain myself from having this post become an infinite post as it was reporting on things that I was figuring out as I was figuring them out, and so on. This is about distributed computing, and let's see. Well, this is the coming attraction, fine structure of black holes. That's what we're about to try to jump into here today. Oh, this is kind of an interesting section for some people about peer review and so on. One thing that we've just done is to add a capability for people to add kind of open post-publication peer reviews for our papers. And this is, there we go. Yeah, there's the form. And we encourage people to do that and to talk about things that the goal of this is really to be able to let other people know that things that you've understood, you haven't understood, that will be helpful to other people who are looking at this, who say, oh, well, if so-and-so has understood it, I don't need to go and check that that's right, type thing. The other things that are happening, we've been adding to our Q&As on the website. We've been getting in thousands and thousands of questions. We've been trying to answer them as quickly as we can, and we've been trying to sort of make buckets of particular types of questions that we can add to our general central Q&A site. We've also been adding to the visual gallery. We just got a new design for the visual gallery, which isn't up yet, and also providing 3D geometries there for people to do 3D printing if they can get it to work, because we haven't been able to get it to work. And the coming attraction that I'll probably be showing off sometime soon, if it doesn't make me motion sick to do it, is being able to explore our graphs and hypergraphs in virtual reality. We're just getting code that's doing this. We will be putting that code on GitHub and looking forward to other people's contributions to it. Okay, so, okay, there's one question here. Okay, there's a couple of questions. Okay, someone with handle Einstein von Rembrandt says, I plan to apply for the Waltham Summer School. Great. Look forward to hearing from you. We'll look forward to finding a Rembrandt in our application list. There's a question here from Viridian. Is the summer school a good idea for a computer science sophomore minoring in nanotechnology? Our general summer school, yes. Specifically the physics track, only if you're up for kind of, well, it depends. The general summer school, that would be a sort of on the early-ish but not super early end of the kinds of folks who come to our summer school, and that background is not untypical. So yes, the physics track specifically depends on whether the interest is in working on something specifically related to physics. With that background, probably some of the more technical physics things wouldn't be readily accessible, but some of the things like, for instance, the virtual reality system, these kinds of things, those are absolutely accessible. It's, let's see, there's one other question here. Now, okay, we are going to get back to this. I realized we're talking about black holes. We should see if Jose can join us as well. All right, I'm going to stop video, but I'm going to and I'm going to get to work here. So our goal is to find black holes. So what is a black hole? Well, a black hole is an area of space-time that has an event horizon. Well, actually, that's a good question to first of all define what we mean by an event, by a black hole, because the presence of an event horizon, that is a place where there are causal edges that go into that area of space-time and don't come out. What happens for black holes, and this is a Jonathan question, black holes, Kerr black holes where J is greater than M. They have a singularity that is not shielded by an event horizon. But so what's the defining feature of a black hole? I mean, it is that there are causal edges that go in but don't come out, yes?
Yes, right. It's there's a region of the causal graph where once you're in there, you can't come out. So there are effectively causal edges pointing monotonically in one particular direction, but not in the other. So as for what happens, okay, if you have a Kerr black hole with J greater than M, the problem with figuring that out is we still don't really know what a singularity is. I mean, we have some hand-wavy ideas about, it's a structure in the causal graph that has a disproportionately large number of causal edges associated with it. But we still don't know in any great detail what that is.
Well, let's talk about that because let's talk about the Kerr black hole for a second. I mean, hold on, I'm just trying to save this in the right place. Just for people, people's awareness, I mean, the communal garden black hole is a Schwarzschild black hole, which is a black hole that has a mass but doesn't have significant, has zero angular momentum in the Schwarzschild solution. And the Schwarzschild solution, it only slowly got understood because there were coordinate singularities, and that's an issue, which doesn't afflict us when we're dealing with causal graphs, right? I mean, the issue in general relativity back in the 1916 when the Schwarzschild solution was first arrived at was that there is a coordinate singularity in it, just like the coordinate singularity in spherical coordinates near north and south poles or something. And people didn't know whether that coordinate singularity was something real. It took until, basically the 1960s before it was really clear that there was a real thing that was the event horizon, and that wasn't just a coordinate singularity. But
I don't think it's quite true that we are not afflicted by coordinate singularities. I mean, sorry, you continue with what you're saying, but
what I was going to say is that the causal graph is much less afflicted by coordinate singularities, isn't it?
But you can certainly introduce them.
By choosing a weird foliation.
Right, which is exactly what you're effectively doing in the continuous space-time case. It's just that for us, that's a less natural thing to do. But I understand. But
let's talk about that because I mean the fact is that in the case of let's see, I had a nice a thing that I wrote when gravitational waves were discovered in 2016, or an announcement was made. I just had this piece about how black holes work, and I think I had some pictures in here that might be useful for us. Along with gravitational turbulence, which is something we need to study. We might actually be able to study this, perhaps. Let's see, maybe I didn't have this here.
Jose here.
Oh, great. We are talking about black holes, so we figured we needed you.
Okay.
So we're talking about, okay, so let's go through a couple of things here. All right, so in the normal Schwarzschild solution, which we can probably get up on the screen somewhere, what happens is we have an event horizon where there are causal edges that go into the event horizon, don't come out. At the center of the Schwarzschild solution is a singularity in the curvature, right?
Yeah.
At radius 0, the Ricci scalar goes to infinity, if I'm not mistaken. Correct?
Yeah. Yes.
Okay, but because the causal edges only go into the event horizon, never come out, nobody can ever be nobody in the outside universe can ever be aware of the singularity at the center.
I'm not sure the Ricci scalar is defined at the center.
Exactly.
It's zero everywhere where it's defined, right?
Right. So it's the curvature of the Riemann components that go to 0. But because it's vacuum, Ricci scalar and Ricci are 0.
Well, you're saying the Einstein equations say the Ricci scalar I mean, it's a very weird situation, because the fact is a Schwarzschild black hole, I mean, this is one of the super confusing things to people about black holes, is that, black holes are formed when stars collapse, but yet the actual solution is a vacuum solution. So in the actual Schwarzschild solution, there isn't anything inside, or there doesn't need to be anything inside, right?
It's Ricci flat, but has non-zero Kretschmann scalar. That's what characterizes it.
What, non-zero what?
The Kretschmann scalar, which is another quadratic scalar invariant, is non-zero.
Depends on what? On the metric or what?
As Jose said, it depends on higher order contractions of the Riemann tensor.
It's Riemann contracted with itself. So you contract the 4 indices of Riemann with the 4 indices of another Riemann.
But I mean, so that's something that is not constrained by the Einstein equations, right?
It is in the sense that the Einstein equations determines the metric, which in itself determines the Riemann tensor.
Okay, but wait a second. What's the difference between a Schwarzschild solution that has, quotes, nothing inside, except that point at the origin where the equations don't apply, and a Schwarzschild solution that has the remains of a star inside? Isn't it the case that outside the event horizon, there is no difference?
I believe that's true, yeah.
Right. So I'm trying to understand, for example, for our purposes, maybe this is just a general piece of general relativity that we don't need to go into in great detail, but it is very weird that, you've got this thing. I mean, it's like happens in electromagnetism with Gauss's law and so on. What happens inside, what happens inside stays inside, so to speak. And all that matters to the field outside is, in the case of electromagnetism, is the overall charge. In this case, it's the overall mass. But the fact is that in the usual way of thinking about it in general relativity, well, tell me how you would think about it, okay? So you've got a Schwarzschild black hole that's forming, and you've got the remains of a star inside, but actually you don't need the remains of the star. All you need is this vacuum solution, and the only place where there's sort of really anything going on there is at the origin, where the equations don't apply. Can you comment on that?
So I think that the way to think about this is that we have a star which is collapsing. It may have some sort of atmosphere or something like that. And then it's going to go through a horizon. Then from the point of view of that side, there will be some remainings that will be radiated. And then what happens inside doesn't really matter. It's actually...
I know it doesn't matter, but the confusing thing is that the confusing thing to many people about the Schwarzschild solution is you get, the thing is essentially generating its own mass, so to speak. The remains of the star that originally formed this black hole, they just, all that matters, it could just be vacuum inside. You go in there, you go and you take your one-way tourist trip to the black hole, you pass the event horizon, you're inside the black hole, and it's like, well, where's that star? There's nothing here. All there is the origin where the Einstein equations don't apply.
Yeah, it's like a delta function.
Well, I understand it's like a delta function, but it's also a delta function where the equations don't apply. So it's like, if you thought the Einstein equations applied to the whole universe, well, actually there's this point removed at the center of the black hole.
Right.
And with respect to this other, double four-legged Riemann thing, is there an interior solution? If there are the remains of the star, is there an interior solution, or is the only interior solution also a vacuum solution?
Do you mean interior to the star or interior to the horizon?
Interior to the horizon.
So
yeah.
I would say that the uniqueness theorems, which say that the solution is going to be eventually unique, apply in the exterior. The interior is a different business, and you will have all these chaotic solutions, and so the interior is not so well defined. So
when you say
you don't have a...
I mean, like the mixed master universe and things like that. I mean, do they occur in the interior of a black hole? Do those solutions? So those are when you say the interior of a black hole, it's kind of like saying what's inside our universe as opposed to outside, sort of thing. Is that right? Is that the kind of thing you're saying?
Right. Yes. So there are numerical simulations of what happens in the interior, and it's a lot more complicated than the exterior.
Right, but I mean, so the fact that things like Birkhoff's theorem only apply to the exterior solution doesn't mean that there doesn't exist an interior solution. It's just not classifiable in quite the same way.
Right. But the point is, what we're saying is, just to clarify the kind of physics of the whole thing, is the Schwarzschild solution is a vacuum solution. It's vacuum everywhere except at the origin where the equations, where you've punched a hole out of space-time, basically, right? But what you're saying is that there are other solutions that are not the Schwarzschild solution that have all kinds of crazy stuff going on inside the event horizon, but by no-hair theorems and so on, it doesn't matter outside the event horizon. It's still the same structure. Is that a characterization?
And by the way, I mean, the statement about the interior solution can be kind of arbitrarily chaotic. This has been proposed as a resolution to the black hole information paradox. This is Stephen Hawking's weather forecasting principle.
What, the information that the data is kind of kept in the
So the argument. So Hawking's argument, I think that was one of the last papers he ever wrote, was that effectively that there are only apparent horizons. There aren't true event horizons, and that what happens is that because of the chaotic solution on the interior, although you have effective loss of information, you don't have true loss of information.
Yeah. Okay. So I mean,
there's no loss of unitarity.
Yeah. So it's kind of going backwards. By the way, somebody's microphone is making funny noises there. I'm suspecting Jonathan here, but might be fine. I mean, that's kind of a funny wimp out because, the original Hawking radiation story was all about there is genuinely an event horizon. And, the most obvious sort of naive thing back in the 70s was, well, actually, maybe there really isn't an event horizon when you take into account quantization of gravity. And okay, I didn't realize that there was a leaky event horizon idea for how to keep quantum information. Okay, interesting. All right, but so you're saying for our purposes, we're talking about, okay, what we're interested in is, in the space-time level, we're interested in causal graphs where things go into a region and don't come out. At the quantum level, we're interested in multi-way causal graphs where somehow, I don't completely know how that transition is going to work, where basically we're going to have Hawking radiation from things that are in the branchial, sort of in the branchial direction can come out, but cannot come out in the space-time, in the space-like direction. But I'm not sure what that means for the structure of the multi-way causal graph. And we had started looking at some multi-way causal graphs before, but I think, okay, let's understand the main goal. The main goal here is to look at let's pick up a what's a good place to start? Should we start with string systems, or should we start with actual actual hypergraph systems? I think we should look at hypergraph systems because I think we can. And I think what we should do is
the only issue with that is currently our only real model for a singularity that's probably not general is that it's a normal form, and it's kind of hard to spot when a hypergraph is in a normal form.
I know. Yes, because of hypergraph isomorphism. But what I'm thinking is that what we're going to come up with here is a better test for kind of the fact that a part of space-time, so to speak, has a causal graph that has things coming into it. In other words, that what we'll be able to see is in the causal graph. Let's take a look. I have some examples. Go ahead.
Do we want to detect event horizons, or do we want to detect singularities? I think singularities are easier to detect, at least the normal form type.
Well, maybe, but I think the normal form type is very weird, and I don't think that's going to be the only story. But
no, I agree.
We need to understand. I mean, but you know why I was talking about Schwarzschild black holes first of all is because I think that the story of singularities and general relativity is a mess, which is the point I was trying to make in the Schwarzschild black hole case. That if we said, oh, we've got to model what happens inside a Schwarzschild black hole, it's not clear what we should expect. And even more so with a Kerr black hole. I mean, but let's, I mean, okay, so one approach we could take is to look at string systems, but I don't think we want to, where we can easily look at the multi-way causal graph, but we can look at the non-multi-way causal graph for strings, where we can ask the question, okay, so do we have an analog? I think we do have an analog. I mean, look, but let's just start doing something here. Okay, so let's here. I need to make this bigger. Let us go ahead and start actually. Okay, so let's say.
If we want to detect event horizons, my feeling is that probably the most effective way of doing that, at least that I can see right now, is by plotting graph communities, because the interior of the interior solution will be a densely connected subgraph.
Yeah, I agree, or something like that. Yes. Right. Okay. So but the question is that in? So we could do that for hypergraph systems, or we could do that for string systems. Let's do it for string systems first. Okay. So I think what we want to do here, which I need to go look at. Need to go to our convenient page here. Okay, enumerate substitution system rules. So I'm just going to get a bunch of substitution system rules here. And then I'm going to generate their causal graphs, okay? Their space-time causal graphs, not their multi-way causal graphs, because I don't think we need or want their multi-way causal graphs. Do you agree?
For the time being, yep.
Okay, so let's take a look at what these causal graphs look like. Okay, so this is now, I'm a little bit confused here. Generates a layered causal graph. Is this the multi-way causal graph?
When you explained this to me, you said it was not.
Okay, well, that's a good sign. Okay, yeah. Well, let's try just for the sake of, so I understand what I'm doing here.
But I think that, from my recollection, I think this corresponds to the leftmost evaluation order. If you see, it's a leftmost sequential evaluation order.
No, I think it's the /dot evaluation order.
Oh, is it? Oh, okay. Fair enough.
Okay, so then this is, let's just look at this graph. Okay, so this is one of these sort of generational multi. Okay, so there's, let's see whether we can label that graph. Oh, great. 1, 2, 3, 4. Terrific. Well, that's I see. We need an event specification to be able to do better than that. Okay, so what this is going to show us, so this is a a very, very connected graph, right? This is an example of a much less connected graph, right? Where if we were to take this graph, for example, and we were to do your criterion here. So this graph is running along, and we might argue that it's making a bunch of black hole-like things here, because I think you can get into those and not out. Let's take a look at the layered version of that picture, right?
Right, but each of those looks to me more like a cosmological singularity than a black hole singularity.
Okay, and why?
Sorry, cosmological event horizon, not singularity.
Well, let's look at this. Okay, so this is what the structure of this looks like. So what we see here is that there are plenty of regions we can get into that we are not expecting to get out of, right? So in other words, this is kind of treeing a lot.
Right. And so the reason I think that's happening, and I think we may have constructed this example specifically to do that at one point, is if you look at the rule, each time you apply that rule, the universe is expanding faster than the effective speed of light, right? The effective speed of light is no more than 2 characters per step, but the state is expanding by 3 characters per step. And so so this is a superluminally expanding universe that therefore trees out into different disconnected subuniverses.
Right. Okay. So
which is the cosmological event horizon case.
Right. So this case involves essentially superluminal expansion, which is similar to what we might think in an inflation. Well, I mean that's okay. Compare this with inflation. This is generating. This case involves.
Well, I mean, one doesn't just get superluminal expansion during inflation. One has if the lambda CDM model is to be believed, then one has superluminal expansion now.
I understand, but which means that there are, that there will be cosmological event horizons.
Yes, right. So each of these is its own. I forget. It's either the Hubble sphere or the particle sphere, or whatever these things are called these days.
Okay.
Each of these is its own causally disconnected observable universe.
Right. Okay. Well, let's take a look. Let's just look at some diversity of these different things. Okay. So we've got here. Let's get a bunch of these rules, and let's just go look at a few of them and see what they do. Okay. So we got those rules, and now should we let's pick a slightly larger thing here. Okay. And so for each of these rules, and I think we'd been doing the thing like this before, but I'm a little worried about this, so I'm going to put a time constraint around this. Let's time constrain it for 3 seconds or something, and let's try running this. Okay, so there we've got some very uninteresting universes that, they're really quite uninteresting. Let's try going just for 15 steps, just for the hell of it. Okay, those are super boring universes. All right, let's try something slightly more complicated here. Let's try. These universes that can't grow. That doesn't help this, right? So let's have universes that can grow here. Okay, so that's the one we were just looking at. This is one that seems to be producing a normal.
I don't think that is the one we were just looking at, because that looks more causally connected, unless I'm missing something.
Oh, maybe you're right.
Those aren't obviously event horizons, because there's
Okay, so given this, we can start making some criteria for is it causally connected. Okay, so let's take that graph, which is the first of this collection, and let's understand how we know that, how we know about its causal connection. Okay, so let's take this first. Let's say, take comma 1, for example. Okay, there we go. And let's say, that's a layered graph plot. Sorry, we need to get the actual graph.
Although I think layered graph plot will be useful, because one criterion we can use, at least to begin with, is we can just pick an event that's on, say, the rightmost branch of the layered graph plot, and then see if it's connected to the leftmost. Or
see if it eventually connects. Okay, so that's
right.
That thing. So this thing is just just your communal garden negative curvature hyperbolic like thing, right? So let us go ahead and take that. So what your criterion, so the question is, to what extent, so the question is, given that we're here, for example, given that we're in an event here, can we ever get to, see, it's not quite as simple as you're making out here, because, let me just, let's just...
Well, I mean, why can't we get a list of events on one arm, and then a list of events on another arm, and then do sort of a thread of find shortest path?
Well, okay, so first of all...
Or an outer or something.
Let's just get the thing here. Okay, so let's take this graph, and what's the graph layout is...
Layered diagram.
Okay, so there it is. I didn't give it an aspect ratio. So there's the object that we've got. Let me just give it an aspect ratio just to make it a little bit easier to see what's going on. Okay, here's our graph. Okay, now explain. Okay, so a piece of the universe over here, right? The claim is that it can still, if we look at the light cones that exist here, that piece of the universe over here is not fully disconnected from something over here. That is the future light cone of that event intersects the future light cone of some event over here, right?
Right. And we should just plot, we should highlight these. We can just use vertex out components and to view the light cones. Yeah, and we can, that might make it easier to see what's going on.
Okay, fine. Well, let's pick a, okay, so let's get a vertex list here, but I think we're going to have something that asks whether the future light cones intersect, right? So in other words, given 2 points, given two vertices.
Yeah, you're asking if there's a non-trivial intersection between the vertex out component of those two vertices.
Right. So let's get the vertex list of GGG, and actually we want to pick one of these vertices high up here. So I don't know exactly how we do that, but let's get the vertex list. Whoops, what did I just do? I don't know what I did there. Vertex list of that. Oh, great. They're just numbers. Well, what we want to do is go from the root, and we want to ask for those things which are at a certain layer relative to the root, right? So we want to ask for the graph neighborhood of the root. Right. And I'm going to, or the neighborhood graph should give us, of the root here, let's say the 4-level neighborhood graph of the root. So the claim is that that's the top of the graph, which it is, right? See that?
Yep.
Okay, so now, given that, we should be able to get, if we want to get, let's go get one of these guys over here. Let's try asking at level 4, for example, in here, is the future light cone, do the future light cones of everybody on level 4 intersect? Right, the future light cone of the node at the top, we know intersects everything because its future light cone is this whole causal graph, right? The question is, once the thing has evolved, do the future light cones still intersect? Make sense?
Yeah, of course.
Okay.
Yep.
All right. So then let's see. We want to get the out component, which is specifically at level such and such. So it's the complement of the out components. So here we would say vertex.
Well, for the neighborhood graph, we can just compute the vertex, any that have in degrees, that have out degree 0. Will give us everything on level 4.
Are you sure?
Yes, because we don't have CTCs.
In this particular case, you are correct.
No, in any case where there aren't CTCs, it's the case.
What about normal forms? What about something normal form at the step 2?
Yeah. Okay. Fine. Modulo singularities. Yeah.
Right.
Okay. You're right.
I think it's a hack to use the. I think we'll get burnt by that hack. I think.
But then, I mean, in fairness, I mean, you can make the argument that singularities also exist at level 4, even if they formed at level 2.
What about doing neighborhood graph, the complement of the neighborhood graph to 4 steps and the neighborhood graph to 3 steps? Will that do the right thing? I think it will. Because I think the similarity that was at level 2 will disappear by that point.
Fine,
okay,
fine.
What we want is a graph complement, if I'm not mistaken. Does the graph complement exist? Yes. Of this thing at level 4, comma, that thing at level 3. Oh, great. I better go find out how to use graph complement. Oh, not what we expected. Is it graph difference or something? What is it called?
There is something like graph difference. I forget if that's exactly what it's called. Yes, graph difference. That's what we want. But we can also do the complement of the vertex lists.
What the heck is that? That's a piece of total weirdness. All right, let's just do complement of the vertex list. And actually, this neighborhood graph, we don't even need that. We just say complement of vertex out component. Am I right? A vertex out component takes a level, correct?
Yes. Yeah.
Okay, so that should give us those things which are. So let's just highlight the graph. Highlight the graph for GGG of that list of components, and we can't see anything. What do we want to do here? Do we want to say, well, let's do
make the vertex size a bit bigger?
How do we do that?
You should be able to do graph of GGG vertex size goes to something. No,
I understand that, but why can't how do I do the styling of the highlight here?
I think you can wrap the whole thing in a style. I forget, hang on, I never remember exactly how that works. You might have to map style over it.
You know what? I think it's got to be a vertex size that's mapped over it. When in doubt, look at the documentation. Style green, great. But how do I do a large node there?
Vertex size.
Yeah, but how do I put that in there?
You can save, it's an option to highlight graph itself. You can save vertex size.
Oh, okay. What's going on?
Isn't it a number?
Good.
There we go.
Yeah. Okay. So those are the vertices at level 4. It's a bit weird. How did this one manage to get there? That one, there's a direct route that goes chunk, chunk.
Yeah. So there are two paths of different lengths that lead to the same event.
Right. So what we want to do here is look at let's just draw on this thing the light cones of each of those events, and just to see. Well, actually, we can go back. Let's do this. Let's take a look at. Hold on here. Let's go back a level. Here. So let's go out degree 3. I mean the thing 3 and 2, just to get. Okay. So there's our first few things, and we want to find out whether these remain causally connected or whether one of them is the sort of entry edges for a black hole, right?
Right.
Okay, so for these, so notice that these two are time-like separated, which is very weird. I mean, it can happen, right? But they are. Okay, so now let's draw the future light cones.
Well, actually, I think they're light-like separated. Because they're a combination of both time-like and space-like separated.
Why?
The fact that they occur on the same level tells you that there's a foliation in which they're space-like separated, or at least partially space-like separated. If you see what I mean. Yeah,
fair enough.
I think I think these two lie on the boundary of the light cone.
Okay. Boy, it's amazing that even with this rule, whatever the heck this rule was, it was something totally trivial. Let's just find out what it actually was, just before we here we can just get it with this. Let's just make sure we know what the rule was that we're about to study. So there's the rule. All right. Okay. That rule is enough to give you all of this. Okay, so let's keep studying this now. Okay, let's make these light cones. So what we're going to do here is we're going to, in the out components, how do I label? Because what I want to do is have the different out components here have.
I mean, can't we do a? We can use the out components to compute the induced subgraph, and then we can just highlight each induced subgraph differently.
All right, that's fine. Okay, so here what we want to do is...
Wait, do you want to plot the light cones, or do you want to plot explicitly the intersections?
Let's do the light cones first. I just want to see the light cones on this picture.
Sure.
Just to see how they... okay, so then... Oh, by the way, okay, the union of these light cones will be the whole system, right? Because we're picking everything at level 4.
Right.
So that won't be that exciting. So what we really want to do is show these light cones in different colors, and then we'll look at where they overlap.
Mm-hmm.
Okay, so for that, what we want to do is take, there's the list of vertices that we're dealing with. And so for each of those vertices, we want to take the future. So what is the future light cone? The future light cone is basically vertex out component to infinity.
Well, you can just do vertex out component.
Will that go to infinity?
Yeah, I believe so.
I thought it only went one level.
No, it's all vertices in the graph that have a directed path to from that vertex.
Okay, fine. So it goes infinite level. Okay, fine. So then what we're saying here is we're saying highlight graph of GGG, and then what we want to do is to map something with a different style. So let's say style hash comma random color of actually we want there a vertex out component, but actually we want the graph that's made from that vertex out component, don't we?
Yeah. So yeah, you want to do subgraph of vertex out component.
Like this. Map that over.
So,
yeah, mapping that over these things here, and obviously the overlap will be screwy. Oh, that's because we didn't give it the GGG to the out component. Okay, dandy.
That's kind of pretty.
It is, yes. Okay, so this is something where, and now if we really want to make it nice, we should show actually the overlap of the light cones in a different color, okay? But
right.
What's fundamentally going to happen is these light cones have successfully been knitted together here, if
right.
that makes sense. And what does it mean to knit the light cones? It means, because what we expect in the black hole case is that the light cones will be unknitted.
Right. And by the way, it just occurred to me that maybe an easier way of determining that is to find all the vertices on the last layer and compute their in components, and then see whether they eventually produce an entire layer.
You mean the in components here, whether these in components eventually reach all points here? So in other words, whether something here, is that right? No, wait a minute. Eventually, okay.
Well, it's the same problem as computing the intersection of the out components. I'm just thinking it might be easier to visualize.
Right. But I mean, so what will be the case is that any one of these eventual points will certainly have visibility to the root node. The question is whether there's visibility to another node out here.
Right. So eventually, if it's not inside an event horizon, there will eventually be a layer in the causal graph where it's connected to everything, where the in component is everything in that, it contains everything in that layer.
Yes, but that might happen only at the root node.
Well, in that case, that's telling us that that's probably an event horizon.
Okay, well, let's look at that, because that's similar to the homogeneity problem for the universe, right? In other words, given a point in the universe today, how much can it see of the earlier universe? Can it see another part of the earlier universe? Can it see the other side of the cosmic microwave background or something?
Right.
right? That's the operationalization of that issue. So,
by the way, sorry, I just saw we got a message on Twitch about asking about Hawking radiation, and we're getting there.
So Hawking radiation, yes, we're getting
eventually.
We're still dealing with the classical black hole problem. Hawking radiation will come about when we look at multi-way causal graphs and we look at branchial edges. We're right now still looking at space-time edges. Do not fear, we will get to Hawking radiation. But first we have to actually have what I think is going to happen here, okay? I think we're going to be able to get to causal black holes. I think we're going to understand something about the no-hair business because we're going to be able to see for our black holes what the mass of the black hole is. We can just count the number of causal edges going into the black hole, and that will be its mass, if I'm not mistaken.
Right.
I mean, it's really straightforward. And so now the question is, for example, what will its angular momentum be? Well, we just tried to figure out what angular momentum is, but when we look at the causal edges going into the black hole, we'll look at, imagine that we've got a slice of causal edges going into the black hole, and we're inspecting these causal edges. We will then should be able to determine from essentially the curl of those causal edges whether there's an angular momentum in the black hole.
Right.
And by the way, usually we talk about mass of a black hole, but the fact is black holes certainly, you can have a black hole tooling across the universe at half the speed of light if you want to, and it's going to have momentum as well, right? And its mass, somebody has a rest mass, and it ultimately has an angular momentum tensor, a momentum 4 vector, just like a random particle has a momentum 4 vector. Right? So for us, the test, one thing that's really kind of interesting is the mass of a black hole in our world is equal to, I think it is essentially the number of causal edges that go into the black hole. Isn't that right? Am I wrong about that?
Well, we have to be a bit careful because the interior of the event horizon has some space associated with it, and that space will have an energy, but that's not normally considered part of the mass of the black hole. So it's actually, I'd say, the number of causal edges associated with the singularity specifically.
Well, your claim is that the black hole is still maintaining space inside it.
Yeah, right. So all I'm saying is there's a huge amount of empty space between the event horizon and the true physical singularity. And if our sort of dimensional analysis is correct, the vast majority of the causal edges associated with the universe are associated with background space rather than with the actual mass of baryonic matter.
What you're saying is, okay, there's the rest of the universe. Most of the activity has to do with, there's a lot of vacuum energy associated with the maintenance of space.
Right, but I think there's also vacuum energy associated with the interior solution of the black hole.
All right, so the question then is, as we separate off, okay, so the fact that we have a black hole, the fact that we need to have a certain mass, we can have a black hole of any mass. And you're saying that the way that we assess that mass of a black hole is somehow the excess causal edges over what would normally be there.
Right.
Well, let's think about that. I think we need to get a more realistic black hole before we can discuss this. But I think the thing that's interesting, just to get a sense of the no-hair business, by the way, there's a question on our live stream about angular momentum, mass, and so on. With respect to mass, if you look at, for example, my technical introduction to the project, or at the announcement post, there's a description of how to compute mass from causal edges. With respect to angular momentum, we just talked about that on a live stream a few days ago, and there's a partial summary of that in the post that I just made live at the beginning of this meeting. But both of those are non-trivial questions that to ask. Okay.
By the way, sorry, you were just mentioning no hair stuff. I mean, one of the things that I think is going to be sort of interesting to figure out, because it's, as far as I know, it's still kind of an unresolved question in mainstream physics, is exactly what the cosmological extension of the no hair theorem is. So our model treats cosmic event horizons and black hole event horizons in fairly similar ways. Just, one of them is total disconnection, one of them is kind of one-way disconnection. And so if we can prove a no-hair theorem for one, it's likely that we can prove a no-hair theorem for both cases. And people have proposed that there are cosmic no-hair theorems in the context of things like holography, but that's still kind of an open question of exactly how that works.
But you see, one thing that's really weird here is, okay, so, we'll have a region of the causal graph that has this feature that edges can go in and it can't come out. Okay, so that's our black hole. Now, in what sense? So the basic point is that thing doesn't have features we can measure, and in a sense that's a trivial statement because everything's just going in. So there's no feature to measure because there's no measurement that is going to tell you anything. You don't get to have any feedback from your measurement, right?
Well, you can perform measurements. The only measurements you might be able to...
Gravitational field outside of the black hole.
Right. And there are also possibly more subtle measurements you can make that relate to the causal edges that are sort of ingoing, if you see what I mean.
Yes, right. But I mean, so the issue is outside the black hole, it has to be the case that the the shape of the causal graph outside the black hole depends only on sort of the total number of causal edges inside the black hole. And that will be the no-hair statement, and not on the configuration of the causal edges inside the black hole. Right?
Well, it'll depend a little bit on the configuration, because I think that's how we're going to get angular momentum and charge.
Sure, but those are... I understand. Okay, I think we need to go looking for more black holes here.
And I'm hoping this will tell us what charge is, maybe.
We'll see.
That's maybe optimistic.
Let's try and find a black hole first.
Right.
Okay, so now the concept is to look at the outgoing nodes here and to ask for each outgoing node. I still want to be able to make a partitioning of this graph, and there should be some graph theoretic partitioning thing that would allow us to know. Okay, so for each of these, we can say at what level, we can make a dendrogram basically that shows, that's the way to think about this. Let's make a dendrogram of this picture that basically shows at what level that guy merges with that guy. Do you see what I'm saying?
Right.
Okay, so how will we make that dendrogram? So the dendrogram, remind myself.
It's the layer at which you're making a hierarchical plot of the layer at which the vertex out components intersect.
Indeed, but I'm trying to figure out. There's probably an easy way to do that. So there's a dendrogram presumably has a nearness function, distance function, great, and a cluster dissimilarity function. Okay, the distance or dissimilarity to use. So the distance function, how does this work? So what we want to get, my idea is to get the distance function to be, in fact, the number of levels up you have to go, right? Does that make sense?
Right. Yeah.
Okay, so let's first of all, so we're going to try and make a dendrogram. So the first thing you have to do is to get the leaves here. And to get the leaves, we presumably want to... How do we get the leaves? We could get them from the complement of the out components. Okay, so how do we get the depth of the tree? How do we get the longest path? Isn't that
just graph diameter?
Yeah, I think something like that. Okay, so let's say graph diameter of GGG.
Oh, wait, hang on. Does graph diameter work with
directed graphs? I don't know. Let's find out what the undirected version is. 25. That's very big. That's much bigger than I would have expected. That 25 is a space-like distance. That's not a time-like distance.
Yeah, okay. Hang on.
But that's an interesting number, that the graph diameter is 25, because that's telling us how many hops, that's telling us that this graph is wider than it is deep.
Right.
Okay, so we need to look at there's a question here on our live stream about, is mass conserved? How would causal edges be counted inside and outside the event horizon? Well, you can, the question of defining a foliate, what we're interested in is the flux of causal edges through different space-like hypersurfaces, for example. And there is a question of how we foliate as we go across the event horizon. And that will determine what we mean by space-like and things like this. Yeah, the question of how you measure the distance to the event horizon, that's not so hard. That just is see, what we're looking at here is a causal graph. The spatial graph is a slice through this causal graph. In the case of this particular causal graph, we made it in the rather trivial way of using a string substitution system rather than a hypergraph substitution system. And so its spatial graph is going to be rather trivial. It's just going to be a string of characters. So there, our distance is just distance between characters. And the spatial hypergraph, the distance is a geodesic distance, and it's a little bit more complicated. Okay, let's try to get what the leaves of this tree are. How do we compute the leaves? I'm going
to again advocate my hacky solution of out degree 0.
Well, you're just saying select those edges which have out degree 0.
The vertices which have out degree 0.
Yeah, right. I don't like it because we're going to get messed up some other time with this. We're definitely going to get messed up. The question here is, but the fact that this is uniform and that everything has the same depth, well, that's one test right there, right? I mean, in other words, that, boy, we're going to need the things at a certain depth here, okay? So let me look up. I mean, clearly we can get it from the thing I just did here. How do we get the depth of the whole thing? That's the first question. How do we get the total number of layers?
I mean, probably the easiest way is to use the adjacency matrix and find the length of the shortest.
Actually, hold on. We're being totally stupid. The number of layers is equal to
the number of iterations.
Yes.
But that won't necessarily be true in general.
Only if you get a normal form.
Right, but that's the point. I mean, if your objection to my hack is that it won't work in the case of normal forms, neither will this.
No, I agree, but I want to find out what happens after that number of. Let's just first of all just take that number of steps of evolution. So we want to find those things which are distance 15 from the root. So how do we get those? Well, I mean, clearly we can get it by doing 15 here.
Is it 15 or 14?
I don't know. We'll find out. It's 14. Vertex out component, the level 14 vertex out component minus the level 12 or something vertex out. What the heck is going on here? Vertex out component 13. So that should be a giant list of vertices. And the vertex out component at level 12, I don't understand what's happening here. Understand this?
Well, they're obviously the same set.
Well, let's just try something much smaller. Let's try 10 and 9. Huh? We just got the right thing to happen here. So let's say we say 4 and 3.
Yeah, I'm not. Yeah.
Okay, so that's the vertex out component of this thing here. That has reached a certain level in this graph. I'm now very confused. So let's go ahead and make a table of t minus 1 here. And let's say a table of that. T goes up to 10, for example. Okay. What the heck is happening here? Okay, so what that's saying is, oh, this is the causal graph. And that's not necessarily the same number of, the thing we were doing was to compute.
Yeah, it's not a multi-way evolution graph.
right. It's a causal graph. And this is showing us the number of things specifically at each of those levels.
Right.
Okay, so fine. So what that's telling us is, so we can compute this to find out. So this is telling us at level 9, we've got those 589 nodes, which are right here. And those are the ones that we want to make the dendrogram out of, right? Okay, so how do we compute the distance, the up, down? I mean, this is sort of a sibling distance. This is how many granduncles or something. What is the cousin distance of these nodes, basically?
Right.
What nth cousins are they? Okay, how do we compute the cousinhood of those nodes? Hey, Jose, do you happen to know how to do that? Because for our trees project, we're certainly going to be doing that.
Not at the moment.
Okay.
I mean, this is what we do in branchial graphs.
Is compute that cousinhood.
I believe so.
But we're doing it only one level, though, in branchial graphs.
Wait. If two nodes in a branchial graph are of distance 2, that means that they are this ancestor distance of 2.
No, it doesn't. It only means that in certain specific cases. We thought that, and it isn't quite right. It's more complicated than that. It depends on the resolution time. If the resolution time is 1, you're correct. But if the resolution time is more than 1, it isn't correct. But okay, so here, is there not some way of turning this thing directly into a dendrogram? Okay, so for any 2 of these nodes, we want to find their distance, their cousin distance, so to speak. How do we do that?
We could do a reverse graph and then compute the intersection of their out components.
And just keep going until they hit. Just
well, no, because as soon as that's one way we could do it. Yes.
Because we need to know otherwise how far away the out component, how far away the first intersection of the out component is.
Which we can get from the layering, but I agree, it's probably easier just to iterate.
Okay, but anyway, the end result of this is going to be, we're going to have a dendrogram, and which I really want to see for this graph. But in our dendrogram, how do we recognize a black hole? We recognize a black hole because what we think is going to happen here is that our dendrogram is going to say these 2 nodes, we're going to see places where there's essentially a chasm in the dendrogram, where basically 2 nodes, you have to go far up to the root to be able to see them overlap, right?
Right, they're disconnected families.
Yeah, most nodes, we say, are going to be, and we could make a community graph out of this if we wanted to see, let's do that just for fun. So we'll take this thing here, and we'll make boy, why is it? Okay, that's weird. That's pretty weird. In fact, this is right here, something like our dendrogram. I have a strong urge to see if Charles could join us for a minute, because he may know how to get this.
But I mean, community graph plot is not, it's only minimizing the number of edges between partitions. It's not setting them to be 0.
I understand that. But that's telling us, but we're, the question is, okay. All right, let's see, again, getting the dendrogram. We need to get the distance, the essentially graph distance Oh, wait a minute. Wait a minute. If we reverse this graph, why isn't it just the graph distance between the two nodes?
You mean 1/2 of the graph distance?
1/2.
But it's not, no, because if we reverse it, then it'll be directed in one direction, but not in the other. If you see what I mean.
Yeah.
I think what you really want to do is. Oh, sorry.
What about the undirected graph? What about the undirected reverse graph?
That could work. I
think it's right. Well, let's try it. So let's take this graph and let's see. Okay, so we've got this graph. We've got the colored. Somebody's microphone is doing something weird there. We've got that colored graph, and now you say make the undirected graph out of that. Actually, first of all, we have to get the. So here we're going to get the thing at the 10th level, which we think is the 10th level? I think with t equals 9. This thing will be a great big long list. Okay, so that's our bottom level in that graph. And so now we want the undirected graph of the CGGG. And then what we want to say is we want the distance matrix for, well, first of all, we could just get the distance matrix for all those things. Right. So graph distance, how do we do that? I think we can ask for the graph distance matrix, if I'm not mistaken, between you.
Hello.
Is that Charles?
Yes.
Okay, we are trying to figure out something about a graph here. Maybe you can help us. Okay, we have a directed graph. There it is. Okay. And what we're trying to do is we're trying to make a dendrogram for the bottom level nodes in this graph. We're trying to show what their cousin number is relative to all the other nodes. We're trying to make a dendrogram of that. But we'd be perfectly happy right now to just make a graph distance matrix showing the distance to common ancestor of each pair of nodes here, which we believe we can get by just taking the undirected graph here and asking for the graph distance between pairs of nodes here.
Okay.
How do we get the graph distance for a this is for the whole of the graph, but we could, is there a way to get the graph distance for just particular nodes in the graph?
Yes, I think just the function graph distance, you can give a graph on the starting and end node, the source and target.
No, I understand that, but I want to get all of them at the same time. I want to compute all the distance matrix for a subset of nodes. I mean, clearly I can do an outer. Look, if I do this, can I get the graph distance? Do you understand what I'm asking? If I just do graph distance, do I get a graph distance function? No, I do not.
No, but if you specified one vertex, so it will give you the distance to all the other ones. So it's kind of a S, all type thing.
No, I understand. That's not quite what we want. I mean, we can just look. We can just get the graph distance matrix, and then we can select the appropriate pieces of that. Why does that look like that? Okay. Oh, that's kind of interesting in its own right. So what we want is the distance matrix selected for only those. Okay, so in fact, all we have to do is if we have this, which is, okay, what we have to do is just pick out those, okay, so lowest level is that. that's the lowest level nodes. And so what we want to do is to pick out of this distance matrix just those nodes that correspond to the lowest level, right? And we could do that presumably by saying just that lowest level, if I'm not mistaken. Isn't that right? That will pick out that submatrix.
Yes.
Okay, now let's say matrix plot of that submatrix. What the heck does this mean? So that's in fact, so that should be, if we pick out that thing, that's all the pairs of distances between all of those things. And let's see, so that's saying that some things, so if I just take that and I flatten it and I make a histogram, okay, what is this telling us? So this is telling us that very few nodes, so I'm afraid we're searching for black holes here. And this is telling us that most of those nodes are almost maximal distance away from each other. Right? Jonathan,
yeah.
So the question is, what will we expect to see if we would expect to see a bunch of nodes. What does this mean? I mean, this is telling us that most of those nodes, there's a factor of 2 here, but most of those nodes, we have to go almost back to the root before they're connected.
Right. So this is the signature you'd expect from a space-time that is causally connected, but only weakly so.
That's right. I mean, if we had exponential growth, we would expect much closer connection.
Right. Exponential growth in edges, not in space-time.
Wait a minute. Exponential growth in, well, this is a causal graph, so it's a little bit harder to know what's going on. Yeah.
Right. That's what I meant. So exponential growth in edges in the sense of dimensionality rather than exponential growth in terms of like the universe. Exponential growth in terms of the universe will become superluminal.
Right. But so the question here is, maybe we don't. So Charles, can you see any way to get from this graph to derive that dendrogram?
Well, I'm thinking about it right now. Directly, no, not on top of my mind right now.
Okay. But dendrogram, so, I mean, we can clearly use this distance matrix to compute. Well, we could, okay, we can just do it as a kind of a hack here. We can just say, this is our function for 2 components. So what we could do is this. We can take that distance matrix here, I claim. There's our distance matrix. And now we can say vertex list of this undirected graph. And then we could say dendrogram. And then we say distance function. If I'm not mistaken, goes to dm of #1, #2. Am I not correct? Am I confused here? And that's right. I mean, because that's just taking, that's saying use this distance matrix as the, oh, great. Okay. It's just absolutely full of stuff. How do I prune this? I probably want to say, well, here. Okay, well, let's just take a random subset. Okay, there we go. This is, I think this is going to work. Just we had too dense a dendrogram. Right, so this is showing us for Jonathan, you get what this is doing also?
Yeah.
It's showing us the ancestor list.
Right.
And I suppose if what we did here was, I'll tell you what, instead of doing that, let's do this. Let's say vertex out component just gives a list of vertices, right?
Mm-hmm.
Oh, actually, what we can do is use that lowest level list. Still a very complicated dendrogram. Ooh, that's cool. Okay, so what that is claiming is that most of these things only require going back one level to be connected, right? Yeah, let's do this. Let's take something that's fewer levels down. Okay, so that's claiming that in the top few levels, so we can do that by looking at the subgraph of the original graph. That is the vertex out component down to level 5. Okay, so this claims to be the dendrogram for the leaves of this thing, right? Anybody there?
Yeah.
Should we label it? We could label this subgraph here. We could say vertex labels, arrow, schematic, and hopefully, okay, 139 and 92 have a common ancestor after one step, right? Whereas 12 and 91, 12 is there, and 91 is there. They need to go far back in order to have a common ancestor, right?
Right.
What?
I'm not completely enthused by this approach.
Well, I mean, this is telling us how far back you have to go to get a common ancestor.
I know, but I don't like this idea of using the undirected graph.
Because?
Because I think that will give you cosmological but not black hole event horizons.
Okay.
Because the undirected graph doesn't make any distinction between the event horizon and the non-event horizon.
All right, it's okay. So that means we have to do the computation more honestly.
As I say, I think the correct way to do it is to compute the in component or the out component of the reverse graph, whichever you prefer, up to some k until iterate k until there's an intersection.
All right, so let's write a function called cousin distance, okay?
Right.
And so what we want to do is cousin distance between, and this is actually a useful function to have. This would be a good thing for the function repository. Cousin distance.
Like I say, the multi-way system code, the evolution branchial graph does this.
Okay, can we directly use that code, or should we? How should we do it?
I mean, it doesn't take that long to rewrite it. It's just as I say, it's just it's an iteration over vertex in component.
Okay. Well, so then what we want to do is we're going to say something like a fixed point list or something. Is that what we're going to say? Or we're going to say nest while and nest until or something, nest while?
I think I did a nest until or nest while.
Okay. But let's see what we're actually looking at. So we're looking at the out component, the in component of I. We're saying vertex in component of G, I,